Check, 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 check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, how's it sound on the camera? I can hear it in the room. 1, 2, 3, 4. You're not. Let's see here. 1 second. I know the closed captioning is working, so that's good. Oh, did that get unplugged? That's all right. That's okay. Okay, 1, 2, 3, 4, 5. Good. Now, how's the level? Good. Good for you. Okay. That's good. Okay. So that's good. This is one of the ones that was supposedly quiet yesterday, and I checked the attenuation, and it was the same as all the other ones. So one of the, you know what, one of the honestly, I'd rather us get this done early.
It's looking pretty good. I've had it on still.
Great. Wow, it's holding up. Okay. We're in good shape.
I'll power it down. This will be the one that we get to.
Is there a wire connection? Maybe a faster connection.
Yours has an HDMI to that.
I have all sorts.
Yeah.
So power.
Oh, that's fine. Yeah. Okay, here we are. That's your microphone.
Thank you so much.
Starting on, it's got to click into the picture.
This is great.
You're not sharing your screen anymore.
No. I can absolutely try. So Zoom.
Okay, good. And I'll do one quick thing here.
So what would you like?
Here, I can help with that.
It's okay. It's all good.
Well, here's a
Yeah.
easier way to do it.
No, it's okay. It's okay.
So you just-
All right. You know what? I think it's better maybe if I. Okay. I like to kind of be in control because that's why it starts squeaking. But it should be okay now. Just let me know if it kind of doesn't work. Just let me know. So. Sounds fantastic. Sounds amazing.
All right, I think we can slowly begin. Good morning, everyone. Welcome to the third day of the Quantum Summer School, organized by the Quantum Science Center. And today we have a JP Morgan Chase Quantum Day of Learning. We will have wonderful talks, and it's my great pleasure to announce our first speaker, Professor Lukin. Professor Lukin is at Harvard. His work focuses on both theoretical and experimental studies in quantum optics, atomic physics, and quantum information science. His work emphasis is on studies of quantum systems consisting of strongly interacted photons, atoms, molecules, and electrons. They're developing in his group new techniques for controlling quantum dynamics and studying the relevant fundamental physics phenomena. It's a great pleasure to have you today. And today's talk is programmable quantum systems based on Rydberg atoms array. Thank you.
So thank you so much. So it's a great pleasure to be here in person. So I think this school was originally it was planned and announced, I think, about 2 years ago. That has been an incredible time. And it's actually great to see you guys all here, you know, and also those, I guess, online. So what I will do today is I'll continue the discussion that you've heard about from several speakers, which basically kind of focuses on the subject of controlling quantum world. So in this kind of area, in this quest, what we are trying to do is we're trying to isolate and control some simple quantum systems, and then build more and more complex systems from them. And what we would like to do with those is to start studying new physics, explore new physical phenomena with these engineered many-body systems, in particular create and probe new states, new forms of matter, and then also explore new applications for quantum information processing, communication, and metrology. And I would like to start my talk by kind of stating that kind of despite all of this kind of great excitement, you know, and basically the news that you read kind of every day, this field actually faces two big challenges. So one of them is to answer the question if and how one can build truly large scale quantum systems, you know, systems containing millions of qubits. So it is actually at the moment, I would say, not really known if and how one can do it. And the second question, maybe even more significant, is if I were to kind of build, you know, give you, build a big quantum machine and give it to, you know, to you guys, you know, okay, so you are maybe an exceptional bunch, you would actually know what to do with them, but in general, people don't really know what quantum computers can or cannot do. So that's a challenge, the application challenge. So how can we basically use these machines to achieve useful quantum advantage? This is also basically a big, you know, outstanding questions. And actually, to my mind, part of what this, for example, DOE quantum centers should be doing is really trying to answer both of these questions, both how to build big machines and how to make them useful. So the kind of sorry, the way where the kind of field is, you know, can be understood by kind of thinking about kind of a quantum rivalry, and you kind of hear about it, you know, quite often, so you can understand different things. It could be competition between different physical platforms, or in sometimes people now really mean competition between different, you know, nations. But to me, it's actually much more fundamental. Now, this is basically a competition between two contradictory forces of nature. One is the kind of force of controllability, and another one is a force of scalability. And this competition of these two forces is present kind of in many areas of human activities, not even just science. So, for example, if you know, take a bunch of well-educated, you know, physicists, for example, you know, physics PhD and electrical engineering PhD students from Purdue, and put them into one organization, you know, by definition, this organization will be challenging to control. So, and, you know, it's kind of a little bit also the, you know, the part that it's too early for the jokes in the morning, but you know, but that's what's kind of going on actually in the quantum domain. So what we would like to do now, basically take, you know, well-controlled, well-isolated, you know, qubits, you know, and then put many of them together, and then really kind of still maintain this isolation, maintain the same degree of control is actually very challenging. So the current frontier is that we are actually now entering in a domain where we can execute the tasks which are beyond modern classical machines. We've controlled something like 100 qubit systems. And with these machines, what we are hoping to do is learn how to build both bigger and better quantum machines, but also start exploring kind of new algorithms and at least scientific applications. So in that sense, we are now in a very special kind of era which I actually, I don't like this term NISQ. I like to call it kind of era of quantum discovery. So we already have machines which are kind of interesting and sophisticated enough that we can really use them as tools for scientific exploration. And I think that's very, very special. So with that in mind, here is what I'd like to do today. So I'd like to kind of first talk a little bit in a pedagogical manner about how we can build scalable quantum systems using arrays of neutral atoms, which are excited into the Rydberg state. So Alex, you had already heard a little bit about that from Alex Kisling yesterday, and so I'd like to still kind of go and review a little bit the basics of this approach. And then with that, I will give a couple of examples from the recent work. So one of the examples will focus on exploring quantum phases and quantum phase transitions in two-dimensional spin models. And in particular, I'll talk about recent work involving probing topological spin liquids. And then this will make use of the kind of analog quantum simulation approach. And then I will switch towards the end to digital quantum processing, and we'll tell you a little bit about the new architecture for quantum information processing, and in particular talk a little bit about quantum error correction, one important ingredient for scaling systems up. Okay, so in this talk, we will focus on using cold neutral atoms as qubits. And those two have two obvious advantages. So first of all, these isolated atoms, which are basically trapped in vacuum tubes, have excellent coherence properties. And so, for example, you should think about optical clocks, modern optical clocks, which actually utilize these neutral atoms. They have really exceptional coherence times. It's actually an instrument which is, probably the most precise measurement instrument which humankind ever created, at least up to date. And then the other important thing is that it's easy to create large number of neutral atoms. So basically, in this room, there are a lot of molecules and atoms flying around. So if we could somehow grab them all and control them all, we'll have a huge quantum computer. But of course, you realize immediately that this is challenging. There are two complementary challenges. So first off, atoms in the gas phase typically interact very weakly, and if you want to, for example, execute quantum logic operations, you need qubits to interact. And then in addition, as I already mentioned, neutral atoms are hard to control individually in large numbers. So there are two approaches. So these challenges have been well known for several decades, and there are basically, broadly speaking, two approaches to address this challenge. One of them is the so-called top-down approach. So what you could try to do, you could try to use sophisticated atom cooling techniques to basically create, large arrays of atoms with low entropy. For example, in systems like optical lattices, and then to try to control them individually. But it's actually turns out to be challenging, at least in large numbers for multiple reasons. So first off, to kind of create this kind of arrangement requires a very complex experimental setup. But even once you have done it, so you basically the atoms here are separated typically by half of the optical wavelength. So individual addressing is actually very challenging. And one other very important but kind of technical thing is typically these methods require the so-called evaporative cooling, and actually to kind of let entropy be removed through evaporation is actually very slow. So actually the cycle time of these experiments are quite slow. So and at the same time, there is another approach, which is basically you can build these systems from bottom up using the so-called optical tweezers, laser beam focused at a certain location. So those techniques have advantages of very short cycle time, comparatively simple setup. And then by definition, almost you get an individual atom control. However, the problem is that these techniques, at least up until a few years ago, have been difficult to scale because basically, if you try to load these tweezers, you have a lot of entropy, and basically you need to get rid of this entropy somehow. So kind of motivated by this consideration, a few years ago, we started developing a new approach where we literally build atomic systems, atom by atom. And the idea here is the following. So we basically start with a gas of atoms, which is pre-cooled by using conventional laser cooling techniques, and shine focused beams of light, which attract the atoms to the point of highest laser intensity. And so we focus the beams so tightly that each of these optical traps, we call them optical tweezers, can basically capture at most one atom. If two atoms are captured, they just ejected from the trap. But instead of one of these traps, we actually start with many, actually by now thousands, and then basically, try to trap atoms as it's shown here in each of these individual trap. And so in practice, basically, what will end up with the arrangement where each trap, costs either one atom or zero. So there are these empty traps, and this is all distributed at random. So the system has entropy. So to get rid of this entropy, what we literally do is we take a picture of atoms, basically figure out which atoms are full and which are empty, and then basically eliminate the empty trap and rearrange the rest of the atoms in the desired configuration. So in such a way, we basically end up with the system with no entropy, but it's completely classical. So basically atoms here sit typically a couple of micrometers away from each other. They don't interact with each other at all. So they don't talk to each other. So to make them talk to each other, what we do is we excite the atoms into the so-called Rydberg states. And basically by doing that, we literally increase the atom size by a factor of up to 1,000, and then they start talking to each other. That's how we engineer interactions. And this is actually our joint project with my colleagues at Harvard, Marcus Greiner, and at MIT, Vladan Vuletic. So just kind of a short review about what are these Rydberg atoms. So these Rydberg atoms are basically hydrogen-like atoms with large principal quantum number. And from the kind of introductory quantum mechanics course, you basically remember that the radius of the electron orbit scales as a square of the principal quantum number. So, for example, when n equals 100, this size of the atom becomes basically a fraction of the micrometer. So it's kind of it's really ginormous. And so as a result, these kind of states, they have very high polarizability. So for example, there's polarizability enhanced compared to the ground state by a factor of 10 to the 9. And because of large polarizability, also if you start with two of these Rydberg atoms, they really feel each other's presence. And actually this van der Waal interaction, for example, here, scales as 11th power of principal quantum numbers, and it's 14 orders of magnitude larger than the van der Waal interaction in the ground state. So 14 orders of magnitude is a large number, and we can make a good use of that. So that's kind of the idea. So, and in specific way, how we use it is this idea of Rydberg blockade. So how does this Rydberg blockade work is the following. So suppose you have two atoms which first are far away from each other, and you just try to drive them resonantly to the excited Rydberg state. So if they are far away from each other, then they will just undergo independent Rabi oscillations. They don't interact, they don't talk to each other. But if we now start bringing them closer and closer, then eventually what will happen is that this interaction will really take over. And this, what it will mean is that, when you bring the atoms, sufficiently close to each other, then this doubly excited state will be just shifted far away from resonance. So what it means is if you excite the atoms resonantly, then at some point you will be able to excite, either one of these two atoms, but never both simultaneously. So that's the idea of this Rydberg blockade. Simultaneous excitation is blocked at distances smaller than this blockade radius, and actually it is the mechanism which allows us to entangle atoms in a very robust way, in a way which is sensitive to motion and position of the atoms. So this Rydberg blockade radius is typically in a range of few micrometers. So it's very accessible kind of length scale. Okay, so to summarize the way how our quantum processor will work, is the following. So we'll start with some random arrangement of atoms. We will then create a desired configuration. Then we'll shine pulses of light on that, changing atomic internal states, sometimes changing hyperfine states, sometimes exciting atoms in a Rydberg state. And then at the end of the day, we will just, make projective measurement of atom state, figure out in which state it is. That's the idea of this kind of workflow in this system. So so this is one example actually how this entanglement works. So suppose you have a pair of atoms which are sitting very close to each other at distance smaller than blockade radius. So we excite these atoms using two colors, so-called two-photon process, but it's not so important. And then if we excite them under these kind of conditions of Rydberg blockade, so we can create at most one excitation, but never two. And so if we look now at this kind of like a probability to excite, for atom to be in a ground state, for one atom to be excited or for two, what you see is that basically the probability of two excitations is completely extinguished. It's basically in the noise. And at the same time, these states between 0 and 1 excitations undergo the kind of Rabi oscillations. And actually, once you create this one excitation, you don't know which one of the two atoms you excited. So you basically should create an entangled state. And we can actually verify that indeed this entangled state is created by basically changing the energy of transition of one of the atoms, for example, shining of resonant beam of light, basically shifting the levels slightly. And then what will happen is that basically the phase of this state will change. So there will be basically oscillations between these two states. And then you can kind of measure it directly by trying to stimulate the original state back, and then basically you can that way prove that you actually create an entangled state and extract fidelity and so on. So that's kind of the approach to create entangled states. But one thing that, so we can use now the system in kind of different ways. And these different uses in practice differ by how you encode the qubit. So in particular, and which atom you choose. Yes. I see. Okay, so yeah. Yes, I will. Yeah, so first off, I would like to very much encourage questions. And in fact, I will even stop a couple of times to wait for questions, but please feel free to ask. So the question here is, how do we actually change the phase of this state? So the way how we change the phase of the state is the following. So basically, imagine that you created this state with one excited atom here, right? And basically what you would like to do, you would like to now introduce a phase shift, which will be different for one atom versus another. And the way how you do it, you shine off resonant laser beam on one atom, which actually acts as a kind of local magnetic field, right? It basically shifts the energy of one transition, but does not shift the other, right? And immediately from that, it follows, it's like kind of, basically it's like local magnetic field. What it will do, it will just introduce a relative phase, during the time evolution between these two atoms, right? That's how, and that's what happens here, that basically this phase change is shown how how, does it make sense? It's like a Zeeman shift, exactly, absolutely. It's like a local Zeeman shift, so. Okay, so this is was one example of one type of encoding. So where you basically encode qubit in the superposition of ground and Rydberg state. And we will see that we will use this encoding sometimes. In other cases, what we will do is we'll actually encode atoms in the atomic spin states, the so-called hyperfine states, and then basically in these states, the atoms will just be completely non-interacting. So if we would want to turn the interaction on and off, what we will do would excite the atom from one of the state to the Rydberg state. And that way we turn the interactions all on and off on demand. So one other important practical consideration, which I skipped, is the choice of atoms. So basically in today's presentation, I will focus mostly on using alkali atoms, which are hydrogen-like atoms like rubidium, sodium, cesium. there are other atoms possible. So, for example, alkaline earth atoms, strontium and ytterbium. So they have kind of somewhat different to the leading order. It's very similar, but they have some properties which are kind of special and more favorable, some other properties which are less favorable. So, but all of those are now actively explored. Okay, so one type of application that I will be using these machines for is the idea of these programmable quantum simulators. And basically this comes from original work of Feynman, who basically conceived quantum computers by thinking about, how to model quantum dynamics. And, he basically realized that modeling, numerically modeling quantum dynamics is actually very hard. So if you have n coupled quantum systems, then it requires a solution to solve exactly, it requires solution at least to the 2 to the n coupled differential equation. So there is an exponential scaling, which actually makes it prohibitive to basically do exact simulation beyond the system of something like, I don't know, 40 or so or qubits. And the alternative approach could be to implement the model of interacting system on a quantum machine, which has some kind of standard sets of operations and programmable interactions. And this is actually exactly the one use of this type of approach, which I illustrated. So in fact, actually, if you read this some of the original Feynman's papers carefully, he envisions a device where you start with basically kind of rows of atoms, initiate some in one stage, turns the Hamiltonian, and then basically watches how zeros and ones evolve, and then kind of make a measurement. And this is actually, kind of pretty much exactly the approach we are implementing, 40 years or so after his original ideas. Okay, so here is how it kind of works in practice. So let's consider, for example, a row of atoms equidistantly spaced. And suppose that they're excited to this Rydberg state. So you could ask, what is kind of the system Hamiltonian here? So the system Hamiltonian is shown here. So it actually will have 3 terms. One is this Rabi driving. So it's basically effectively like kind of a spin flip term. Another one is laser detuning. This term is basically effectively acts as a local chemical potential. N is a number of Rydberg atoms on each side, 0, 1. Then there is this interaction term. And to understand, maybe to get insights into kind of what's going on from the point of view of many body physics here, what we can do, we can just ask what's the ground state of this Hamiltonian, and we can actually parameterize it in terms of 2 variables. One of them is this laser detuning, this chemical potential. Another one is the interaction range, basically how many atoms are blockaded, of the nearest neighbor. So if the interactions are negligible, if this term is negligible, it's clear that the ground state of this of the system will be determined solely by the detuning. If detuning is negative, then you want all atoms to be in the ground state. If detuning is positive, basically to minimize the energy, you want all these n's to be equals to 1. But of course, a state like this is not compatible with Rydberg blockade. So even if just nearest neighbor is blockaded, you will not be able to excite all atoms in the ground state. So in fact, the state that you will be able to excite, which minimizes energy, is a state where every other atom is excited. So it's up, down, up, down, up, down. That's the state with the broken Z2 symmetry. And that's basically an antiferromagnetic state. And if you now increase the range of blockade, then every 3rd atom is excited, and then every 4th atom is excited, etc. And actually, it turns out that one can explore this phase diagram very easily by just preparing all atoms in the ground state, fixing the range of blockade by positioning atoms, for example, appropriately and exciting the appropriate state. And then just try to kind of adiabatically sweep, change the detuning to enter into this ordered state. And this is kind of what's shown here. So you start with all atoms in the ground state, and then, you change the detuning, and here you stop at different points and measure. So here, you basically entering in this antiferromagnetic state, this up, down, up, down, up, down state. And actually here is a point where you basically have a lot of noise. So this is a point of phase transition, of quantum phase transition, where two kind of orders where all atoms are down and antiferromagnetic orders start to compete, and there is like a lot of noise. It's actually really kind of a picture of quantum noise, if you want. And if you then, for example, change the distance between atoms, if you bring them closer together and you get this state up, down, down, up, down, down, up, and then there is, this is also a state with Z4 symmetry broken. And basically this is all you can kind of, all of this phase diagram you can explore by just, changing, one control knob in your experiment, in this case, atom position. So in this case, these programmable interactions result in desired symmetry breaking. So, that kind of concludes my high-level kind of overview of basic ideas which go to this platform. So I will now talk about some of the more recent developments. But maybe it's not a bad time to stop and ask if there are any questions. Is everything clear? All right, I will then keep going and we'll tell you about the kind of modern generation of this of the machine, which we are calling generation 2 atom array. So it's actually we have confusing terminology. So now generation 2 and generation 3 of system 1, and now we have system 2 also in our. So, but in this generation 2. Is approach which is powered by this optical device, which is called special light modulator, which is basically a computer-generated hologram where you can deflect the reflected beam in a certain angle, and by just making the appropriate hologram, what you can do, you can create this kind of arrays of laser beams in 2 special dimensions. And if you then focus this array into this vacuum chamber, then what you can see is kind of array, in this case, of thousands of optical tweezer traps. So one disadvantage of this special light modulator is that actually it's slow. It has kind of relatively slow update rate. So if we want to sort atoms, if we want to move atoms around, we need to have a second channel. And so for that, we utilize a system of 2 crossed acousto-optic deflectors. So acousto-optic deflector is basically a device which uses one input, laser input, and then basically a microwave input to kind of deflect the beam using acousto-optic effect. So it's a device similar to the one which is used as a kind of barcode scanner in a supermarket. It's actually pretty much this device. So we use 2 of these guys in a crossed geometry such that we can sort both rows and columns of atoms independently. And then, so this all computer controlled. And so this actually, one other thing that I want to mention. So this atom array 2 is actually, generation 2 was an upgrade which we completed, pretty much like at the beginning of March 2020, and then you all know what happened. So this is actually a historical picture where basically was a last time when we were kind of allowed in our lab under normal kind of operations, but we had so we had to completely shut down everything, but we had 1 week warning, and we were told that we should be able to leave servers operating. So in 1 week, this system became a server. And actually, from what follows, all of the data that I show is what are data taken remotely. And then actually, there are some people on this picture that you already have seen. So for example, can you recognize this young aspiring graduate student who looks like Karl Marx here? So this is, famous Dr. Kisling, who have given you a nice presentation yesterday. So anyway, so this was a remarkable effort by this group of remarkable people. So, but the bottom line is that we now can create basically an artificial crystals of atoms in almost arbitrary special arrangement, what's shown here. So we can also create an arbitrary pattern. So this is the traps, the atom, the pattern which we want to create. We press a button, and here is the underlying atomic pattern. And so in practice, up to now, we were able to fill about 600 traps with some like 60% filling. That means that we have about 300 sorted atoms, and each trap filled with probability a little more than 99%. So, and kind of using this approach, we can start exploring various different aspects. And one easiest is to try to kind of extend this idea of programmable quantum simulator now into the two spatial dimension. And if, for example, you have this type of lattice, and you have nearest neighbor Rydberg blockade, then it's clear that what you will create is basically something like an antiferromagnetic pattern in two spatial dimensions. It actually looks like this, so it looks like a checkerboard. So for this reason, it's called the checkerboard phase. But even in this very simple 2D square lattice geometry, if you start changing the range of blockades, so it turns out you already create a wide variety of different phases. So in fact, it has quite complicated phase diagram, which has been predicted by Subir Sajdev, our theory collaborator, one of his students, Ryan. And basically, by now, we have actually observed most of these phases experimentally. But it turns out even the simplest possible transition into the simplest possible phase into this checkerboard is a kind of a classic, quantum phase transition, which is known as a 2+1D quantumizing phase transition. Apparently up to this work, it has never been observed. So let's see how we can solve this problem. So we create atoms in this square lattice array, as shown here. Adjust the Rydberg blockade appropriately, and then just do this detuning sweep. Change the detuning from negative to positive, and then once in a while we have a picture like this. So it's basically a completely ordered 2D ferromagnetic pattern. So admittedly, this is not what happens in every experimental shot. So typically you have some defects, but then what you can do, you can evaluate statistical quantities such as, for example, correlation function, this up-down correlation function. And you see that we have correlations across pretty much the entire array. Another thing you can do, you can look at macroscopically, you can analyze images one by one. And in fact, in this analysis reveals that these patterns with perfect ordering, even though they don't occur very often, are still the most probable from all of the states which you create. And in fact, the probability to have this perfect ordering is basically decays exponentially with system size with the rate 0.97 to the power of n. So that means that we have, 3% kind of error, in quotes, per atom during the entire evolution. But this 3% now includes everything, includes imperfect preparation, includes, for example, quantum fluctuation in the residual phase. It includes also, of course, technical imperfections like spontaneous emission. But basically this initial state and the final image here, correspond to completely classical kind of states. So the question is it a quantum phase transition or what is it? And so we studied that, and the way how we studied this is by using dynamics to basically measure something which is called critical exponents. So basically, it turns out that phase transitions, can be described in terms of universality classes, and the only thing which characterizes these classes are these critical exponents. So the way how we measure this is to go across the phase transition at different speed, and basically, if you go slowly, then you have correlation spread across the entire array. If you go quickly, then only short-range correlations can nucleate. And for example, you can see it in terms of growing correlation length. So if you go quickly, only short-range correlations are created. If you go slowly, the correlation grows to a large size. And actually, what this universality idea of the phase transition tells us is that if we now rescale the properties of all of these curves with their critical exponents, they should all collapse, because close to phase transition, basically there should be no any kind of physical length scales. Everything should be sort of mixed soup of the fluctuations. And if we do this rescaling, and we indeed see pretty nice collapse, and actually from this collapse, by optimizing it, we can extract this critical exponent, in particular this correlation length exponent, which is very much consistent with the value which has been theoretically predicted. So, and this value is actually very different, for example, for quantum phase transition versus classical. And so by doing that, we can actually verify that it's really quantum fluctuations which drive these dynamics, and also benchmark the system and study, verify what we actually observe this quantum phase transition in 2+1 spatial dimensions. Okay, so this is kind of basically a description of the system and a kind of current state of the art. And with that approach over the last 2 years, we enjoyed a wide variety of different experiments. We studied different phases. We studied non-equilibrium dynamics. We started to study topological phenomena, and I will talk a little bit about it. So Alex already talked about recent work was trying to basically accelerate the solution of combinatorial optimization problem. And we also are kind of now making progress towards, basically more universal programmability, I hope I can tell you. And actually, Alex already also mentioned that we now have a second machine in town, which is across the river, and now startup company Query Computing. And this is will actually be available on AWS Cloud this year. All right, so I would like to now talk about some of these recent developments, but again, I maybe can slow down here and ask if there are any questions. Yes. Yeah. Yes, so basically we can do that, but in this case, in this data which is shown here, the size, the total size is fixed, and what we do is we basically we just change the speed, and the thing is we have to make sure that our system size here is big enough that for our slowest speed, it's a speed and not a size which limits this, and in fact, what is kind of interesting, the interesting phenomena here, which actually depends on the system size, is associated with bulk versus boundary ordering. So the boundary of the system can actually order first, and this would correspond to basically, phase transition in 1D, effectively 1D. And so for this specific data set, so this system was big enough, around 200 atoms, such that this boundary ordering does not really play a big role. But actually, it turns out that for some of the other phases, which I have shown, boundary ordering is actually central. In fact, if you study that you see that it's, you are driven, the phase transition is driven by boundary. And it's kind of a little bit of a question, what happens if you keep, growing the system size? You could say eventually boundary will become irrelevant, but it is something that we are still trying to understand, because, so this is basically similar, if you grow crystal, for example, often, to grow crystal, like if you grow diamond, for example, what people they start with diamond powder, right, to nucleate the growth, and then you can grow a large sample from that. And so likewise here, sometimes what happens is boundary nucleates the growth, and then, drives the transition in the bulk. And actually, for example, for the phase which is briefly shown for this phase, it turns out, it's just one of these kind of, more so complicated phases, which is some kind of sublattice and some, kind of quantum fluctuations in the middle. So here, for example, we believe that boundary drives the transition. Yes. Sorry, can you repeat it? Yes. Yeah. So So the question is how should you think about universal scaling exponents? So basically, the idea of this universality of the phase transition is the following. So initially you start with some kind of physical system. It has some kind of length scale like lattice, size and so on. But if you go close to the phase transition, what happens is that you you basically start, you have a lot of fluctuations. Your system is like a soup of the fluctuations. And typically this kind of fluctuations would have some sort of correlation length. But if you go right to the point of the phase transition, if the system is very large, this correlation length, at least theoretically, should diverge. How it diverges is characterized by this critical exponent. In fact, in this case, characterized by this critical exponent nu. And it actually turns out that close to the phase transition, system forgets about what Hamiltonian it started with, right? And it's kind of, that's the idea of universality. So the only thing which at the end matters are these critical exponents. And there are two here which are relevant. One of them is a correlation length exponent. Another one is basically dynamical critical exponent. Z is basically how gap closes, how rapidly gap closes with system size. Yes. Yeah, so yes, the question is, can we extend it to 3 dimensions? Indeed, the answer is yes. The problem is that, and people have done it, the problem is that, if you go to 3 dimension, you will lose at least a little bit of degree of parallel control. So here we basically can sort all atoms in parallel. We can read them out in parallel. But, you basically lose, that, kind of, 2D is very natural geometry for us. It's open geometry, right? So you can have additional, layers, and people have done it, but then you lose a little bit of parallelism. There is another way to make it effectively 3D. And that's, if I have some time, I will show you how to do it. Yeah. Yes. Yeah. So yeah, so the question was, so far these interactions are, mostly nearest neighbor interactions. Can you have longer range interactions? So the answer is yes. And in fact, some of these phases, so for example, here, for example, the Rydberg blockade already extends beyond nearest neighbor. It extends to first and second nearest neighbor, and it drives this non-trivial phase. And actually, in the example I will show you now, this is central. Right. In fact, you need to extend blockade over 6 nearest neighbors. Okay, so let me go on. So I will try to talk at least. So how much time do I have? I don't know. It's like 15 or 20 minutes. Okay, good. All right. So 12. Yeah. Okay. Okay, 20. Okay, I'll work. Okay, good. All right. Thank you. So, all right. So, okay, I'll try to give 2 examples from, I would say, frontiers of the field. So, one of them is an example from many-body physics, and that revolves about a goal, which is a long-standing goal in a many-body physics community, involving realization of topological spin liquid. So, this is the idea which was originally proposed by P.W. Anderson in 70s. So, and the idea was that, somehow that should be states in nature whose properties are not determined by some kind of local ordering, but instead are determined by the topology of the system. And actually, I was recently told a story about, by someone who was at the time in Bell Labs, who told one, Anderson by the time was very famous physicist already. And he gave the talk about this idea of the spin liquids. And actually, apparently, he gave a Bell Lab seminar, about that. And then people after the seminar said, Phil, this is great, but, it's okay, don't talk about that. So, he was apparently perceived as kind of really crazy. So that's actually why his original paper was published in some kind of proceedings of Material Research Society. But actually, but kind of the original kind of idea where in this kind of states should occur are in this systems with frustration. So imagine, for example, you have a system with anti-ferromagnetic interaction in a triangular lattice. So you can try to put, for example, this spin in one location, spin up, and then this has to be down. But where do you put this spin, right? You can basically not orient it without violating one of the constraints. But actually, this idea, then became popular, and it created a lot of work in the condensed matter community. And so one possible kind of resolution of this frustration is to basically create this ordering where basically each pair of spins you put into a form of a singlet. So it's some so-called dimer. And then basically you cover all of the lattice in these dimers. And of course, this is just one way how you can orient the dimers. So in practice, what you should have, should have a number of equally likely, basically a superposition of the states where dimers cover all of these lattice, a so-called dimer covering. So that's the idea of this resonating valence bond, so-called RBB states. And basically about 20 years ago, this idea was given by kind of another boost by Alexei Kitaev's work, who basically pointed out that states like this can be actually used to encode qubits in a robust way. And that's the idea of the so-called toric code. So it's basically a system of the qubits, a system of the spin, in which locally there is no order, but basically, all of the kind of information is encoded in non-local strings. So for example, the toric code is an eigenstate of products of all X operators living on one lattice and Z operators living in another sublattice. And so these products are sometimes called stabilizers of the toric code, something that I will come back later on. Well, but despite all of this interest and remarkable efforts, there is basically no conclusive experimental evidence of this state existing in any system, at least up to last year. Okay, so we were kind of very motivated to look for it, and in particular, kind of early in the pandemic, two groups at Harvard, the group of Subir Sachdev and group of Ashwin Vishwana, came up with the specific, hardware efficient way to realize these spin liquids in our platform. And the key idea is that to arrange the atoms on a frustrated lattice and utilize Rydberg blockade to create this highly degenerate, superposition state. So in particular, the system that we'll look at now will be the system like this. So you put the atoms on the links of the so-called Kagame lattice and then arrange the Rydberg blockade that each excited Rydberg atom blocks 6 of its nearest neighbors. So basically, from here you can see that at most you can excite a quarter of all atoms, and it turns out that you can map this kind of Rydberg blockaded model into the dimer model by just associating a dimer with each Rydberg excitation as shown here. So for example, if this Rydberg atom excited, it means that there is dimer here, and due to this blockade, this constraint, the dimers cannot touch each other. So that's the idea. So once you have a dimer here, you cannot have a dimer on an adjacent lattice. And this theory work that I already mentioned, basically showed that at least under certain conditions, you should be able to create a state which is basically superposition, equally weighted superposition of all of these dimer covers. So let's see if we can implement this system. So we start with atoms living on the links of this Kagame lattice, and then try to arrange this kind of adiabatic evolution of the type shown here. And then, we take a picture. So this is now a picture in forms of the dimers. So what we see is that we have at least kind of an approximate, dimer covering. It's not perfect. There are some defects here. But basically, what can you say about this? So how can you basically detect and study topological order? So one way is to look at some kind of global observable. In particular, if you do this adiabatic sweep and stop at different points, what you will see is the curve like this, and you see that there is around this 1/4 filling, there is kind of a kink in the curve. There is a kind of a little bit of a plateau here. Something is happening, but what is it is very unclear. So to basically study this topological order, we have to study topological observables. And in this case, we in particular study the string operators similar to the ones for the toric code model. So it's product of basically Z and X strings, and the Z strings are actually very easy to understand. So if you have a dimer covering, and if you, for example, make a loop around one of the vertices of the lattice, so this vertex should cover, go across exactly one Rydberg excitation, right? So what it means, if you just look at products of sigma Z operators, right? So what should happen is that you should have a basically expectation value exactly equal to -1. And actually, if you now make a bigger loop, right, what will happen is that the expectation value will be -1 to the power of number of these enclosed vertices. So, and this is something which we can measure, and indeed, we find across the large fraction of the array, the expectation value of this product of these Z operators non-zero, in fact, has a right type of parity. So basically what it shows is that at least we are making a transition into approximate kind of dimer phase. But the key thing that we need to show now is to understand whether we create a superposition of these different dimer coverings or just, statistical mixture. And in order to do that, we have to probe the off-diagonal coherence. So in this case, we actually have to probe this X operator, which actually is defined in this way. If it acts on one of these triangles, it will flip around this excitation. It's kind of, the definition is kind of a little bit non-trivial. Some looks like a zoom. Yeah, I think there looks like a zoom problem. So yeah, I think it's probably okay. So, but okay, the key property here is that if you make a closed loop of these X strings, then this, if you apply this closed loop of X operator, what it does, it will take one dimer covering into another dimer covering, like it's shown here. So did it? Okay. Okay, let me just. Okay. So it looks like it's frozen, actually. No? Oh. Yeah, here. Now it's better. Okay. All right. Oh, good. Yeah.
Okay.
So, okay. So, okay. So basically, it turns out, to make a long story short, and like if you measure non-zero expectation value of that, it's like measuring sigma X for 1 qubit. So if you measure expectation value of sigma X for 1 qubit, you basically see that you have a superposition between 0 and 1. And so to make a long story short, we can actually make a measurement of these so-called X loops, and we do it by turning them into into Z loops by basically making like a collective rotation on these triangles of the qubits. I'm not going to describe in details how exactly we do it, but the bottom line is that we can measure the expectation values of these X loop operators, and again we see that they are non-zero across a large size of the array. So this basically gives us a signature of coherence between dimer coverings. So now, how did we actually convince ourselves at the end if we have a topological phase or not? So basically, we did it by essentially comparing what's going on closed loops versus open strings. And so, for example, if you look at this Z expectation value, the signature is quite dramatic. So if you look at a loop at the closed loops, you see some non-zero expectation value of the signal. If you look at the comparable open loops, it's just dead zero. And it's actually similar things happens for this for the X loops. So it turns out one can actually formalize it a little bit in a language of lattice gauge theory in terms of this kind of string order parameters, which are basically the ratio of open loops to closed loops. And from here, by analyzing them, you can actually identify these quantum spin liquid topological phases from trivial and other types of phases. And in fact, indeed, it turns out that there is a parameter regime where all of these order parameters behave appropriately, and it basically means that we are kind of entering the onset of this quantum spin liquid phase. So as already mentioned, these quantum spin liquid phases are connected to topological qubits, and we could not resist by trying to at least make a baby version of the topological qubit. So let's see if I could maybe. So in this case, this is an array with non-trivial topology. We made a little hole here, and actually it turns out that in case like this, it's possible to define basically, so it's like this kind of coffee cup and a donut. So in this case, it's possible to define two non-commuting strings. One of them is X string going around this hole, and another one Z string going from inner boundary to outer boundary. So these two strings actually define a qubit. And so if we create a ground state of the system, it should be doubly degenerate, and there are two possible superpositions you can create. So actually our adiabatic procedure should create this state, create a state with sigma X, this loop being in a +1 state. And in fact, this is what we see. When we create a state, we see indeed that this sigma Z string from inner to outer boundary, vanishes. Sigma X is non-zero, and there are other kind of correlations which actually also indicative that there is a correlation across the entire array. So this actually is an indication that we can really make some steps towards topological qubits. So okay, it's kind of quite exciting time in this field. So because these topological spin liquids is something that people thought about for many decades. And now one can really create and touch them and probe them. And in fact, some of the ideas that people kind of dreamed about. So this is a picture from Scientific American's, cover 15 years ago. I think the artist who drew it thought that physicists became completely crazy, So this is the kind of stuff which we can now do. Really, we can create these excitations, these anyons, and braid them around. And this really becomes a new tool, which is complementary to conventional numerical techniques, and analytical techniques, to really study these effects. And, there are a lot of exciting opportunities. For example, we're thinking about how to use methods of quantum machine learning, a little bit along the lines what you'll hear in next talk to analyze it. We're thinking about simulating lattice gauge theories and also using insights from these experiments to engineer like new real world materials. Okay, so I think I will, so do I have still 5 minutes or so, or is it? Okay, so let me just as an outlook, tell you about some of our most recent work, which kind of goes beyond these analog simulations. And the idea here is the following. So far I've talked about qubit encoding and ground and Rydberg state. And while very convenient, it has some limitations. Instead, what we can do is we can consider encoding a qubit into the superposition of two spin states, for example, hyperfine states, which can be driven, there is a microwave transition between them. And if you need, you basically can excite the one of the states to a Rydberg state to execute quantum logic gate. And it turns out that, it's actually one can make those gates. So for example, the most natural gate is a so-called controlled Z gate, CZ gate, where you basically just imprint a conditional phase onto the state 1-1. And actually there is a way to how to do it, with high fidelity. I'm not going to kind of talk about it in details, but it's essentially involves two Rydberg pulses with proper detunings. So what can we do with a system like this? We can, of course, build a conventional gate-based quantum computer, but maybe more significantly, we can now imagine doing something very, very special. So far I told you about, basically, the way how our workflow is, we, start by positioning atoms, and then start turning interactions on and off. Using this hyperfine approach, what we can do is we can basically, perform some kind of manipulation using this method, but then we can stop in the middle of computation, store our atoms in this hyperfine states, and then move the qubits around to basically change the geometry and the connectivity of our system on the fly. So here is some simple demonstration of that. So suppose you started with a bunch of pairs of atoms, you entangle them and you verify that you have entanglement by measuring some kind of parity. Then you basically move these atoms, far away from each other and ask if entanglement has been preserved. And in fact, here indeed it is preserved almost perfectly, right? So that gives rise to this idea that you can have this architecture where you basically, bring some atoms together, execute some gates, store them, move the atoms, and continue this this approach. So what can we do with that? So here is a simple example. It's a generation of the so-called cluster state, where you basically start with atoms, prepare them in superposition, and then basically execute the controlled Z operations, in this case in parallel, on nearest neighbors. So here is how it works. So you basically start and make this entanglement operation on these pairs and move the atoms, one of these atoms in a pair to the next one, and then basically do another set of gates. And basically from here you can measure things like stabilizers and verify that you have entanglement. So it's kind of very natural. But the question is it the only thing you can do? Can you generate more complex states? And in fact, this is what we have done in a recent work. So not only we've done these experiments with 1D cluster states, we generated this so-called STEAM code, which is actually an error correcting code. We also explored topological error correction. And we also have explored this kind of hybrid digital and analog evolution. So I will not have time to talk about this. So let me just briefly, describe what is it kind of about. So this will include a toric code on the torus, kind of going towards 3 dimensions, as was asked before. So okay, so what is one slide? What is quantum error correction? So that's a method to basically fight noise in quantum computers. And it's kind of is rooted in the ideas of classical error correction, where you basically just make many copies of the state. So instead of, for example, 0, you make the copy of 0, 0, 0, 0. Instead of 1, you make 1, 1, 1. But the problem is in quantum mechanics, there is no cloning theorem. So you cannot duplicate quantum information. So instead, what you do, you basically use entanglement to store information non-locally to encode logical qubits, and basically you use the so-called stabilizers to basically detect the presence of errors and to correct and protect logical qubits. And and these are of course building blocks of universal fault-tolerant quantum computer. And so one specific kind of way to encode this information is through the use of topology, as I already indicated, and in particular. In original work of Kitaev, he kind of envisioned using, qubits on a torus like this to encode the information and basically using this topology to protect it. So that seems quite hard to implement. I'm so sorry, there is a Zoom keeps squeaking for some reason. So I'm nearly done. So should I just talk? I think it looks actually not too bad. So far. I don't know. All right. So to implement this in our system, this torus geometry looks kind of hard. Because we just have 2 dimensions, but actually it turns out that this torus can be understood in terms of this graph, which has just non-local connectivity. The right side of the graph connects to the left and top connects to the bottom. And we can implement the graph like this by using these so-called ancilla qubits, which are basically, which are used to kind of measure these stabilizers in the following way. So basically what we do is we use the approach, which actually was suggested about 20 years ago by Peter Zoller and Ignacio Chirac. And at the time, they actually had a lot of ideas, which actually most of them have been implemented relatively quickly. But there was one of these ideas which, was viewed to be kind of very, completely crazy, which actually, people thought this will never be done. And at the time, there was these magnetic hard drives, I guess now they're not so common anymore. And the idea of Peter and Ignacio was to replace a hard drive by a qubit and let qubit kind of moves around. So basically we implemented this idea, but instead of moving one qubit, we now move the entire array of these ancillary qubits. So here is a movie which shows how it works. And so what you see is 8 ancillary qubits, which basically go around stationary data qubits and interact with them. And then eventually we move them to this separate zone where we can read them out. So that's a way to implement this kind of graph with this non-local connectivity. And in fact, in this case, we can actually, this is an error correcting code where we can encode 2 logical qubits. And so these logical qubits, in this case, one goes around one dimension of the torus and then the one another. And in fact, we indeed measure non-zero expectation value of those. But now we also have access to all stabilizers, so we can correct the errors. And in fact, for one of these qubits, we correct them to basically 1. Another one is we correct them, but it's not quite to 1. So basically, it shows that one of them is actually better protected than the other. And I leave it, as a homework problem to figure out which one of them is better protected. Okay, so this is actually, really kind of quite exciting time. And, because we now can really start implementing these error correcting codes and doing it very, very efficiently. And I think there are exciting opportunities for both fault-tolerant quantum computing, but also for approaches combining analog and digital quantum dynamics. Okay, I want to conclude by just going quickly through this list. So there are a lot of open questions. So it's an active frontier of research. There are a lot of technical kind of challenges, which we still are working on to kind of build larger and more programmable systems, including individual addressing, including fast readout, including hardware efficient error correction and detection, and also then eventually scaling up the system, basically connecting different modules potentially. But I think maybe I sort of used up my time. So here is, what I showed today. So I did not talk about quantum optimization, which I think you heard about it from Alex. And I would like to thank you for your attention and thank all of the people whose blood and sweat resulted in this.
Professor Lukin, thank you so much for the great talk and wonderful opening of the morning session. I think we have time for a couple of short questions.
Yeah.
Even RVB spiliquid to check whether some superconductivity emerges. How can you charge this kind of transport?
So this is, so the question is, what if you dope the system, if you introduce some holes, would this give rise to superconductivity? So the kind of in our case, we implement spin models only. And the reason is that, our traps are far away from each other. So the tunneling will be basically prohibited. So it is possible to combine these techniques with tunneling by, bringing atoms a bit closer together. And there is some work, in particular in a group of Adam Kaufman, for example, evolving that. So it would be very interesting to really study these questions and to understand, if there are some emergent phenomena. So we cannot do it right now. We can study, still spin models with defects, and this is what we are doing. We cannot study the kind of the charge transport, but I think it is possible in principle, and it might be possible in practice relatively soon.
Any more questions?
So the question is about phase transitions, like in the quantum spin liquid.
Yeah.
Many times when you do a quantum many-body experiment, or quantum simulator, true one that cannot be simulated, you get data and you don't know what you are looking at.
Yeah.
For example, when Emmanuel did the many-body localization, you look at the results and you see the same, pretty much, especially his recent results.
Yeah.
How can you tell?
How can you what?
How can you tell there is a phase transition in your data?
Oh, so okay, now there are different things we can do. So first off, the way how we know that we enter this topological system is by measuring the string observables, by measuring these non-local observables. So the kind of knowing that we actually cross a phase transition, we have also different methods. So we can, for example, measure gap. And, we can see that, the gap at some point is, has minimum. We can also measure, as I showed you before, we can measure like dynamics by going, quickly or slowly across the phase transition. We can look how correlations build up. So here is in topological systems, it's harder to do it because the correlations are non-local, but actually still there are ways to do it. And we did a little bit of that. It's not yet published results, but so what we can do, we can go into the topological state and then, and then come back and then see how many excitations you created. But actually what's kind of interesting, Moti, is that, even though we had a theory guidance to where to look for the spin liquid, we actually made a small, I didn't have time to talk about it, but we actually made a bit of a discovery here because we found that this topological phase is present across much wider range of parameters than was predicted theoretically. And our understanding here is that what we create in this case, we actually create a state which is long-lived, metastable state, but not necessarily the ground state. And we can see it by looking at this string operators.
So you see, there is an inherent problem in Feynman's vision. And you wanted to do a quantum simulator of true quantum many-body system. You look at the data, and you can't get much. So I need to carefully look at yours, but I looked at Emmanuel's data on the many-body localization. The way that they did it, this is poor man's solution. Okay. In other words, what they did, so let me just explain for the audience so they know what it is, so it's not between us. So you mentioned Philip Anderson, so it's known Anderson localization. The effect is for a single body. In other words, one single electron. Think about a lattice, that you have one equation, it can be solved numerically on the computer in the lattice of what happens, and this gives you indeed, when you put some variance in the depth of the potential, this gives Anderson localization. Next question was, what do you do if it is a quantum many-body, just like Misha talked about, okay? And of course, there's no solution. Nobody knows even to compute. In one dimension, you can compute up to 23, give or take. In 2D, where this becomes interesting, nobody compute anything at all with any classical computer, including all the computation power on Earth, classical computer. So this is really where things are. So what Emmanuel Bloch did is he prepared the lattice and then created an edge. In other words, he populated half the lattice, and the second half was empty. The population of every site was just with one atom. And he wanted to see whether the edge will spread. And he saw some, okay, it looked okay. Can you say something? So we had an idea, actually, if you want, we can discuss later, how to actually have a smart way of knowing it using AI.
Yeah, but no, but okay, but maybe
Same
what,
goes for you.
okay, hold on. So I should actually, so what is important, for example, for this project, the big part of that was really developing this kind of positive signatures of the phase.
No, I understand.
And,
we
and
do
this
what-
is actually, and in fact, what we used these ideas from lattice gauge theory to define it. And actually, I completely agree with Moti that this is a kind of frontier, so this definition can be refined. And in fact, we use some ideas now already from actually kind of quantum machine learning to improve, basically to improve to find a new order parameter. And actually, I can explain a little. The idea is that, since this is an error correcting code, you can actually use insights from error correction to have more and more crisp definition of that. But it's a very interesting question.
So
Indeed,
the reason that I raised that is
Yeah.
because Feynman thought about quantum simulator is a wonderful idea,
Yeah.
but then you get data and you don't know what is there. It all looks the same. So if we can discuss that.
Yeah.
Yeah, we have a project on this. That's why.
Oh, okay, yes. Sounds good.
Yeah, I think it's all
Okay.
interesting question that can be, I think, and all other questions discussed later during the
Yeah.
panel discussion in the afternoon. And with this, I would like to thank again Professor Lukin. And we will move to our next talk given by Professor Suzanne Yellen. Professor Suzanne Yellen is a Vice Director of the Joint Max Planck and Harvard Research Center for Quantum Optics. Her research group studies theoretical quantum optics and quantum information science. And their current research directions include quantum control of ultra-cold polar molecules, investigation of novel coherence-based optical elements, single photon nonlinear optics using dipolar systems, coherent metamaterials and negative refractivity, coherent control and condensed matter system, as well as superradiance. I would like to welcome Professor Yellen. It's a great pleasure to have you today, and the floor is yours.
Okay, thank you so much. Well, it is my pleasure to be here in person. This is a treat indeed. I have to put a disclaimer in before I even talk. This is a very experimental talk, not because I turned experimentalist. I'm still kind of a cold-blooded theorist, and there's nothing I can do about that. But because that's actually the first time that I give a full quantum machine learning talk. So this is a school, and I'm of course giving you only my own view of this. But the talk is modular. I can stop after I'm through a quarter of the talk, no problem. Please do ask questions. I will try to answer them to the best of my knowledge. Okay, so I would like to, by introducing the people who actually kind of did the work first, the people you see at the top, Rodrigo, Taylor, and Abigail are grad students. Actually, Taylor is not. Taylor graduated a week ago. And Jonathan Liu is actually an undergrad student. And the other highlighted people are the people who also contributed to the work. Kaying and Gebre are undergrads, summer undergrads. Sona and June are postdocs. And Jean and Anima are working on one project on our NVIDIA and Caltech collaborators. And I will just build this in the order, but so let me start a little bit from the beginning. So you've probably seen by now a lot about machine learning, so I have only one single slide about machine learning. And I already make the machine learning a relevant case for what we actually want. So you could imagine these two arrays here as, for example, this Rydberg spin system that you just have heard about. And this could be in an ordered or a disordered phase. I have to say these pictures are not very clearly ordered or disordered, but let's assume they are divided by some particular parameters. For example, the ordered one in this case would be that they like spin, like to cluster together. And here is our quantum machine here, which is right now somehow parametrized. And the parameters in our case, basically throughout the whole talk, I hope, are always called theta. So please remember, 3 parameters that we adjust is theta. To start with, we give it an input, and the quantum machine, not quantum, that's not quantum, the machine just guesses, oh, this is probably in the disordered state. But we don't know this. It just needs to make an initial guess. And so you put some kind of algorithm in, like, for example, what Sasha does, and that goes through there and compares that with what the system in principle knows already, and figured, oh, no, this is actually not disordered. We are actually here in the ordered phase. And the main thing is really kind of going around this circle here a couple of times, every time kind of adjusting these parameters. And I'm going to show you how we do this in particular. So I don't want to go into any more details here. So the question is here, of course, you have a computer, you do machine learning. Of course, then you have a quantum computer. Can you do quantum machine learning? That's the whole question. And I know Sabre has given a talk about this yesterday, and they are really kind of trying to solve some very relevant real systems or real problems with that. Of course, the question is, can we do this? And I will give you a little bit of an overview about the type of questions that you potentially could ask. So the big question is, of course, can quantum computing enhance or speed up the machine learning algorithms? And that is really a big if. So far, there are some kind of interesting theoretical proofs of parts of that. But to my knowledge, nobody has yet built a quantum machine that can do machine learning faster or more efficient or whatever than any classical learner. So the goal for me as a researcher in this case is really not so much stand in front of you and say, quantum machine learning, that's what we want to do. That's the greatest thing on earth. But what I want to do is, let's see what questions can be asked that might be potentially interesting for a quantum machine. And second, then go ahead and figure what can we do in order to potentially make this better? Where are the improvements? And in particular, in the talk that I'm giving today, we want the improvements not in 50 years when somebody can build a universal quantum computer, but we want them today. Okay, so this is why my talk is titled NISQ machines. So, and the plan here is I will give you various examples, in fact, up to 4 if I get that far. If not, it doesn't matter. But let me tell you. So the first is the question, can we actually can the machine find the symmetries of a quantum state if we don't know a priori what the quantum state is? We get this handed. And then we are supposed to figure out what kind of symmetries do we find here. You all know symmetries are very important in physics. They are even more important in quantum physics. Second question, can we actually use quantum physics to elevate brain-inspired computing? So you probably have heard about brain-inspired computing. I will talk a little bit about this. The third question is, can we solve classical benchmarking problems better if we introduce a little bit of quantum to it? And I don't know what to do. Okay, and finally, can we actually generate quantum states of a complicated many-body system? So the question is really, can we replace experiments at some point, which might be complicated or something like that? So this is the goal. Okay, I'll try. All right, so, and some early questions that come up there and lessons that we have learned. So if we say quantum, My problem is I don't know what to say without my slides. What about quantum mechanics makes the learning potentially better, faster, less resource, needing less resources, etc. Right? So there are three obvious candidates. The first one is entanglement. That's everybody, whoever does quantum physics and says, oh, what is great about it? Entanglement is always the first thing that comes, right? Second, interference. Interference, of course, is much simpler. It's also not necessarily quite as quantum as entanglement. And the third one is the fact that we have non-commuting operators, and in particular, non-commuting bases. And so there are and this is not all our findings, entanglement is a great resource. Unfortunately, in quantum machine learning, that leads to the so-called barren plateaus. And we have done a little bit of work about barren plateaus, but I don't want to talk about this. Barren plateaus is basically the problem that if you have a quantum system, you can very easily, much easier than in classical machine learning, run into places where you, for example, can't do a gradient descent anymore because your landscape is really completely flat. And this happens in particular with strongly entangled systems. So bioentanglement is great, and we definitely need to include it, especially if we solve quantum problems where entanglement is part of it. We have to deal with those barren plateaus. Interference is much simpler, also works very well. Please do note that interference is not always quantum, right? You can have interference between two light fields. It's just E&M, no quantum. But as part of quantum, it's still very important. And this non-commuting basis turns out to be a great resource, but one has to keep in the back of one's minds that, of course, if we use, for example, bits in the z direction and bits in the x direction, as the surface of the Bloch sphere, that, of course, our measurements in both spaces are probabilistic, right? It's always only a projection in this direction. It turns out it's nevertheless a great resource, and sometimes this probabilistic nature is actually good. So all of that will somehow play a role in what I'm going to tell you today. But I just wanted to throw this out here up front, because these are really probably right now the biggest questions: which of these resources are actually useful? All right. This was my title. The many-body systems part should be relatively straightforward. The reason why I switched places with Misha in terms of the talk is that a lot of our work has been modeled to use the Rydberg array as a machine. Okay, so this is basically, if I say in general many-body system or spin system or something like that, you can think about the Rydberg array. And NISQ is noisy intermediate scale quantum. So that means that are the quantum machines that are available now, or at least kind of the quantum machines that are available now with some kind of modifications that can be done in the next year or so. Okay, so this is really the kind of small scale stuff, etc. Mostly, not fully, actually, also the stuff that we might still be able to actually simulate on a classical computer, because the problem is that it's not that I say, oh, I have an interesting problem, and I have like 5 people with quantum computers come to me and say, oh, please try it on mine. If any of you ever tried to run something on a quantum computer, you will know that this needs a little bit more planning than that. Okay, so that's the first one. So this is the symmetry classification, and we did the working title of our paper here is Interactive Hybrid Quantum Machine Learning for Black Box Circuit Symmetry Classification. So the hybrid is always the clue for we use the quantum computer only for these particular parts where the quantum is faster. Everything else is done on a classical computer. And this is led by Jonathan Liu, who is an undergrad in my group for the last year. And as you can see, there are quite a couple of people we have used. In addition to Jonathan, Kaying and Gebre, both are were summer undergrad students, and Sona is a kind of quantum machine learning postdoc in my group who is involved in a lot of these. Okay, so I have also stolen a good part of this part of the talk from Jonathan's group slides. So you will see a difference in kind of style of slides. And one of the reasons why I start with this one is because I think it's a very relevant question. I also think that there is the most kind of base level explanation in that. Symmetries are everywhere. And the first question is, how can we describe a symmetry in terms of whatever kind of encoding, math, language? And the very simplest way is the way how we do this here. We have some operation, U, which, for example, if we look at geometric symmetries, would be just, for example, somehow rotations and mirror images in 3D. Of course, in general, this can be much more complicated, and this operator U is normally much more than just three-dimensional, because if we exchange many body systems, etc., these operations can be relatively complicated. But in general, what we have here is a unitary operation that describes some kind of transformation, and we have a symmetry of our state psi if psi is an eigenstate of that operator. Okay, so this is how we define symmetry. Now the next question is, here's an example. Let's take the so-called GHZ state. I put this here just as an example. And then the next question is, we actually do have to somehow parameterize our symmetry operation. Because in general, especially if we do a many-body system, this might be an n squared or even 2 to the n squared kind of operator. Okay, so this is not very practical. So we have to kind of limit our parameterization. And one of the ways how we can do this, especially if we want to find the symmetries of a GHZ state, is in the way that is shown here, namely where we say, okay, we can take the Pauli X operator between any of those, for any of those bits, and also put the face on it, and that will always give the GHZ state back. So for right now, we use a parameterization of this type here. This is a choice, and we took it because we knew that we can get the symmetry of the GHZ with that. In general, we of course want to have many more parameters, this choice of parameterization is really the difficulty. But for now, we do this kind of simple case here. So symmetries are everywhere, and this is of course already a kind of a fairly complicated list here. There's the so-called stabilizer formalism, like the story code that Misha just talked about. Obviously, we can use it to characterize state, and if we are deeply in the quantum, it also potentially can help us understand the entanglement structure. So the question is, of course, how do we find them? Okay, and the way how we are going to do this. Let's assume we get handed a state psi, right? That might be from an experiment. It might be from some kind of black box. We don't know where it comes from. Somebody hands this to us, okay? Here we say it's an oracle that hands us that state. But the point is the state just comes from somewhere. We know it's a physical state. It's a state of L qubits, but we don't know anything about it. And what we are trying to find is the symmetry. And what we do here is we assume for this particular problem a universal quantum computer, which is made of single qubit rotations around the 3 axes and Z0 gates. And it turns out that most symmetries, not all, most symmetries can be actually represented or parametrized with logarithmically with L. This is not something we came up with. There are papers about this. It turns out it's not true for absolutely all states, but it's a good start. So this is where Jonathan's artistry comes in. So our, A is usually Alice, but I mean, who cares? Alice is everywhere. So it's baby Arthur. So Arthur is still very small. And Arthur is by the oracle, which is here shown in terms of this plane, a state, which we know is the GHZ state, but Arthur doesn't know. Arthur fortunately has a helper, Merlin. And so the point is that Merlin is great. He knows everything and so on, big wise guy and magician, etc. But turns out he is also not particularly trustworthy necessarily, okay? So Merlin just kind of says, okay, let's tell baby Arthur that x times 1, this is the unitary operation for a single qubit. I just tell him that this is a symmetry, which it actually isn't. And thinks by himself, it tricked him, okay? Baby also, of course, since he doesn't know it very much yet, just a priori believes him. Turns out it's not such a good idea. So we need to teach Arthur how he can verify a symmetry. So Merlin hands him a symmetry, and the question is it actually really a symmetry of the state here, okay? Then can we take this verifier machine to actually learn a symmetry from scratch? So he doesn't need to, the machine doesn't need to be handed a symmetry. But can guess some itself. And finally, of course, we want to have the full classification machine. So, and the idea of the last point is make sure that you don't learn the same symmetries over and over. It's kind of a little bit boring, right? Okay, so now I have to wait because I really... Okay. So the first question is, can we verify symmetries? So the easiest would be to do the so-called swap test. So remember from, sorry, a couple of slides ago, what we are trying to compare is U, namely the symmetry operator times psi, with psi itself. And it should not change. So that means we have to compare two quantum states. And the easiest way to compare two quantum states is the so-called swap test, where we need a swap gate. Which actually is relatively efficient once you have a swap gate. Turns out swap gates are really not that easy to make. For the first, we decided, okay, let's not go with something difficult as a quantum, as a swap gate. So let's take the so-called KL divergence that stands for Kullbach-Leibler. These are two people, and make a quantum version of that. So the idea is here that we take this KL divergence for these two states, psi and U psi, and see whether they are the same except for a phase. But in order to make this quantum, and in particular, remember my third point about different bases, let's look add this divergence over different bases. And it turns out that in at least in the simple cases, 2 bases is actually enough. But if you want to get better, you do it in 3 different bases, etc. So like not just in Z, but in Z and in X, or in Z and X and Y, or whatever, right? And that's what we define as our QKL divergence. And this one, just in case you were wondering how this KL divergence looks like, that's a formula how this looks like, where P and Q are probability distributions. The one is the target one, the other one is your guessed one. And I didn't want to go into details, but just so in case you know that this actually exists, and it's actually usually relied on heavily. So that one we can actually do. So now, as you can see, Arthur has gone up quite a bit, also got himself a quantum computer. And now Merlin tries it again and says, oh, we have this great symmetry here. Why don't you take that one? And Arthur said, you know what? Just go home, Merlin. I can do this myself now. Okay, I don't need you anymore. But then he said, okay, well, I can verify it, but I can't guess it. But by that time, Merlin is already kind of skulking and has gone. And so Arthur has to come up with a test state, a test symmetry himself. So he goes to the wizard convention, WUA, as you can see. Sorry about this. This doesn't teach you anything, but I liked it and I left it in. So the point is you need some verification function. This is what is usually called the loss function. This is why this function here has an L, which connects the state psi with the symmetry operator U. And then we try to do this turn this into a learning scheme. And the most obviously is the so-called variational quantum algorithms, and introduce a parameterized quantum circuit. And here I just very briefly want to give you the very, very kind of low level of what the variational quantum eigensolver does. The solution that we want to find is this vector of parameters. For example, the parameters that parameterize our symmetry operation. Here I have another example, because this shows up again afterwards, namely a Hamiltonian that has whatever coupling constants that are parameterized by theta or something like that. And then we want to minimize this loss function, and the loss function can be, in our case, it's this QKL divergence, but it could be as simple as just the energy eigenvalue. And then we update these parameters on each step, usually just by using a gradient descent method. This can, and then of course we go ahead and repeat this until we have a good solution. So in principle, we have a classical part which calculates the gradient descent given that it has a number of parameters, step by step, and a quantum machine which actually evaluates this loss function. Okay, so this is really the 2 elements, and the classical computer updates the parameters, gives that to the quantum machine evaluates it, and gives the updated value of the loss function back to the classical machine, which then calculates gradients, etc. So this means the idea is that this evaluating is actually hard for a classical computer, but it's supposedly easy for a quantum computer. That's really the whole idea between all this variational quantum algorithms. And this actually, sometimes it's called VQE, which stands for variational quantum eigensolver. Sometimes it's called VQA, which is variational quantum algorithm. Sometimes you will see QAOA, which is the quantum approximate optimization algorithm, which is one subclass of VQA. Okay, often they are all used interchangeably. They are all different, but for now, I'm not going to go into these differences here. Okay, so back to the symmetries. So our quantum machine is just a kind of as universal as possible quantum computer with the elements that I introduced before, namely the single qubit rotation and the C0 gates. And this is not completely universal. but we can already do a very large class of operations with that. So as I say, because we have finite number of parameters only that we can actually deal with, this is good enough. And what we do then is we find the loss function from that. So we put the CEDARs in, and please do note that the CEDARs are really just the angles on these rotations. We don't change the C0 gates. And this turns out to be relatively universal, okay? And then we update this classically in the way that I said before. Okay, so Außer now has the magic glove, namely this quantum machine, to do that himself. And this is what I basically just said. And the point is now we want to do this in random basis. So we have to do that a couple of times for one basis, then we do it a couple of times for the next basis, etc. And at the end, we get this loss function, which is our QKL function. And finally, he can do this all without Merlin, and then goes ahead and finds his first symmetry. The first symmetry is more likely than not the identity operation. Anybody surprised by that? Because we have done nothing in order to kind of say, oh, identity operation doesn't count, right? So identity operation will always come out. And the problem is then he tries it again and gets another identity operation. He tries it again and gets another identity operation. Okay, so the next step is basically how do we make sure that we don't find symmetries that we have found already? Because of course, the kind of symmetries that are easy, the machine will very likely find first, etc. So, and this is actually the part which is still work in progress, and which I therefore will not tell you exactly how to do this. We have a way, and we still are trying this out, but this can be done. That's just a second. That's just a question. How can we actually tell whether we found the symmetry already or not? Yes. Yeah. I mean, the point is, oh, sorry. The question was, so we find the loss function by going to different bases. What if we don't find the right basis? So the point is, there is no right and wrong basis because it has to be the same state in all bases, right? Otherwise, it's not the same quantum state. So if we know something about it, we already choose our basis smartly. It actually turns out that the best is to choose the easiest basis, which is usually the basis the computer works in, the quantum computer works in, and something which is slightly turned off from that. You don't want to go too far because this is technical. The point is you have to, at the end, try it out, okay? But the point is you have to go at least in 2 different bases to make sure that you actually have a quantum state and not just a projection in one direction, correct? Okay, but the point is there is no, with the basis, you can do 10 and you can still not be sure you have it all, right? I mean, that's the thing about learning. You can never be 100% sure. You just try to come as close to the target as possible with as little resources as possible. And so in our case, the number of bases is a kind of a resource, and we stick with 2, but we don't have to. Yes, at least for, the question was 2 is sufficient. So 2 is sufficient, at least for, probably for most problems, probably not for all. Okay, I cannot say more than that right now. Unfortunately, I don't know more. Okay, and at the end, what we get out is something like this. Turns out there are actually 2 symmetries for this parametrization for the GHZ state. The one is basically everything that is the identity or the identity with some phase, which is still the identity. And the other one is this kind of X operation, okay? And we have run this 100 times, and This is the symmetries that we found. This is the identity operation, and this is the, sorry, this is the identity operation, and that's the X operation. Okay, and so we can say with some certainty, at least within our parameter regime, that's all what we can find. Okay. So, and of course, at the end, we want to go to something much more complicated and to a lot bigger systems, etc. Turns out this is a pretty resource-intensive calculation. So I think we have gone to like 5 or 6 qubits so far. That's about what we can. Okay, so that would be. I think I have a short summary for this one. Are there still some urgent questions regarding that symmetry kind of question, or some of the general? Sorry, I did not stop up to here. Okay, then let's go on to a different. So this is basically a bit as far opposite in terms of quantum machine learning as you can possibly go. And this is about quantum reservoir computing using arrays of Rydberg atoms. So that's the working title of the paper. This one is actually on the archive since a few months. And my student Rodrigo is leading this one. And here, this is a suggestion of how can one do quantum reservoir computing with already all the parameters of the Rydberg arrays put in. And I show only very little. There's a lot of results in there. I don't show all of them because otherwise I'm here for 3 hours. So the first question is this kind of brain inspired, right? So taking inspiration from the brain to reveal the power of quantum computing. So on one hand, we have these NISQ technologies, which is at best a few hundred qubits with decoherence, which in principle is scalable and is also used in an analog. It can be used in an analog way. And of course, all of these are the so-called programmable quantum simulators moving towards full quantum control, but don't quite have it yet. On the other hand, is the brain. The brain works actually pretty well. The brain consists of neurons or neural circuits, which we kind of just plot like this one here, which we know to be very resilient to noise and disorder. Even that anybody can sync up something like that is a good proof for that. It's obviously analog, and it evolved to really excel, and in particular excel at learning. Not so much classifying, etc. That too, but learning is just, the brain is just completely unparalleled. The question is, can we do quantum algorithms that inspired by brain that actually reveal a quantum advantage? And that's still the big question here. And the second is that there's an analog computational power in the NISQ devices, as I say on the left side, which actually really works very much to our advantage here. So we don't have qubits. We have nodes that have quantum interactions between them. That's what we need in this case. So there is, of course, the question, why do we think that brain inspired and quantum go together well? Both machine learning and quantum computing rely on fundamental linear algebra operations. And the idea is that quantum computing can speed up. I think this is somewhat understood by now. And the question is, can the quantum hardware make quantum machine learning inherently good at capturing quantum features in the data? So can a quantum machine learn quantum data better than a classical machine? So I'm actually leaving that out. That's a little bit of history, and I'm sorry, I just leave this all out. So obviously you cannot study quantum machine learning without having an idea of how quantum foundations work. And in particular, can we use the quantum dynamics, the analog quantum dynamics, instead of the circuit model, which is this brain inspired? And second, is it NISQ friendly? So here is this idea of the brain inspired. So the neurons in the brain do computations, and they are nonlinear computations. In particular, for neurons, in order to work, there's always what is called an activation function, which is highly nonlinear, which is either if it's below a certain threshold, nothing happens. If it's above a certain threshold, the neuron fires. Okay, and this is sounds trivial, but it's really a highly non-trivial operation. And neurons are very good at this. Obviously, a single neuron can only do that much because it either fires or it doesn't. And it gets some input, and it basically calculates as part of this input and how this works. Cognition is actually emergent from interacting neurons, and as a result, it is robust to input noise and robust to geometric imperfections, and obviously robust to the fact that for each of us, the kind of wiring in the brain is a little different. So can we do this with quantum? So here is our machine. So this is the idea of recurrent neural networks is built on the brain. And please do note it's classical. So that's a classical example, okay? So the idea is on one side, there's an input which then evolves somehow in this machine. And after that, we get an output on the other side. And this can be described by having a function which has a index n, where n stands for the individual neuron. And there are two inputs for each neuron. The one is its connection with all the other neurons, and the other one is external stimuli. Okay, and we can write this so that it looks like a Hamiltonian. And the idea is, with this activation function, that was the website that was too fast. With this activation function that I was talking about before, if this function h is larger than 0, we don't do anything. Or we don't fire. In that case, we don't do anything. If this is smaller than 0, we fire or we flip the spin. Okay, that's the classical way how a brain works, or that's classical way, how a brain-inspired neural network works. So that has a very obvious way how to do that for quantum. Here is again our Hamiltonian. This is now a little bit more complicated. So this Hn is the same function that we had before, but now we use a quantum spin. And in addition, we have a sigma x operator with a Rabi frequency. That's basically, the Rabi frequency that you would send in to switch your atoms in the Rydberg array between the ground and the Rydberg state. And the update rule in this case is that we do something with this Rabi frequency omega. So the point is, if you look at this total Hamiltonian here, if this Hamiltonian here is much larger than the Rabi frequency, even if we have a pi pulse, not much happens, because not much happens. If this is much smaller than h, then the second half dominates, and what we will get is a pi pulse, and we will flip the spin. So it's again the question is our h, is that large or is it small? It's again it's external biases and internal kind of interactions, and but that is more general in this case here. First, it has interference and freedom of measurements, which might be an advantage or a disadvantage, can also be used for error detection. I'll show you an example of that. And the unitary dynamics in principle can produce training speed up compared to the classical case. So here is an example. That is, let's assume we want to calculate the parity of two spins, sigma 1 and sigma 2. So we put this in there, we get some answer out, and this is how that works. We have sigma 1 and sigma 2, there are two spins. We have another spin here in the middle that we initialize somehow. Let's initialize that for -1, and we know that it's initialized at -1. And our output Hamiltonian is now a very simple form. It's just some kind of parameter J times just the sum of these two spins. So obviously, if the two spins are the same, this H output can have, if we choose J large enough, can be easily much larger than our Rabi frequency. And nothing happens. Why nothing happens? Because in this case, the Rabi, the only thing what this kind of putting this field, this Rabi frequency on is it will kind of turn the system around the z-axis, which however will pretty much average to a very high probability to project on the positive z-axis. If on the other hand, they are not the same, then obviously what we get here is just 0. So our H in this case is 0. And that means that the output, of course, is much smaller than omega. And what omega does is just do a pi pulse. Okay? All of that purely quantum, purely with what Misha can do in his experiment. Sorry, I should go one back. So are there any questions regarding this kind of really simple operations? Okay, so this one, I'm sorry. Can be used for detect single bit flip errors. The way this works, we have our pulse with the sigma x somewhere in the middle between the input and the output, and we are kind of comparing the spins pairwise and see whether we have an error there. And the way how this works is that we just put the pi/4 pulse in between both of these slots here. What happens? We start with a pi/4 pulse. So here this is done visually. So we flip that basically, for example, to the y-axis, and then we do this Rabi operations. If there is no error, the pi/4 pulse around -c will just flip the system back and nothing happens. If, however, we flip this and the spin here is flipped by whatever, for example, by an error, this pi/4 operation will kind of finish this flipping here. And if any of these A1 or A2 are not -1 anymore at the end, we know there was an error before. Okay, so this is to do an error detection via quantum machine learning. It seems a little bit of overkill, but that's something which we can do. Another thing is, as I say, here one can potentially get away with a lot fewer resources. Here is our network again, with a couple of potentially hidden neurons that we don't have access to. I'm not going into the advantage of that, but that evolves somehow, just by itself. In the classical recurrent neural network, it has been shown by the paper that is cited on the bottom that the number of time steps necessary to flip all the spins once, just using this procedure, is of the order of 2 to the n of the visible neurons. In the quantum, flipping all the spins is easy. You just put a pi/2 pulse in for all of them, and all of them flip done. Single time step. And this potentially might, so this is how this flipping works. And this potentially gives a particular speed up because we don't have from one configuration to the next, we don't have to necessarily have 2 to the n flips, okay? And so this quantum RNN can potentially speed up the training. So what I will do is I will, because I think I should probably take like 5 more minutes or so, I will finish this and just give you an idea about what our other things are. So these are the applications of classical neural networks. The first is they're very good in making decisions upon visual input. The second is that there is an associative memory. So we can learn. I meet you now that you are whatever 20, and I meet you again in 20 years, and I will probably recognize you. Okay. And then there is a very sorry. Oh, what did I do? Okay. There's a very large class of things, for example, memorizing various different kind of scenarios that come into the brain, and we call them at will. And in order to do this, it is good to have a combination of so-called inhibitory and excitatory neurons, namely some which kind of get a positive input if they are same, and some which get a positive input if they are opposite. Okay, and this one gives a much larger class. Turns out that with this Rydberg interaction, in principle, you can do this negative and positive interaction, which is super helpful. And it turns out that with qubits, you can actually replicate this. And here is the idea: how can we use the Rydberg atoms? We have the input, which as Misha told you, is mostly in terms of Rabi frequencies and detunings. And then we get some output, where we just read out a part of the network and make some kind of operations on that. And what we get out is this, what we call Y out. That can be whatever, expectation value of the energy, or a susceptibility, or whatever. The way we find the loss function, this is a little bit of a different loss function. It makes kind of sense. We just basically look how far is Y out from our Y target. If that's big, and this one, is basically the same thing that we had as this, or this one can be described through this HN function that I introduced before. And if this loss function, if this is great, then we don't want to change anymore. If it's not great, we try again. Okay, and there are two tasks that we particularly calculated. The one is decision making. So here is we put in two different detunings, and the decision is what is the sign of delta 1 minus delta 2. And we can learn this within the output is a so-called psychometric curve. And the question is here, the only parameter here is how sharp is this transition from actually delta 1 is smaller to delta 2 is smaller. And this black curve is the experimental, so the machine learned curve. We know where these extra kind of funny spikes come from, but I'm not going into this now. The other one is a memory capacity. And here, as I said, we put in a couple of different pulses over time and want to see whether we can, after a certain time, or after, let's say, 5 or so of these pulses, we can still get this original pulse out. And forget about this. This one basically gives you the accuracy of how this can be done. This is, in this case, only 2 pulses, so we have only 1 pulse in between. And this blue and red is indifferent. The one is the ordered phase of the Rydberg array, and the other one is the disordered phase of the Rydberg array. And it turns out that they work both similarly well, and we are kind of in the 80–90% range. So it's not perfect, but it works fairly well. This is also only at 1 time. Obviously, if you wait longer, it gets worse, etc. Okay, so let me ask whether there are some questions. We have a couple of other, for example, multitasking is something that the brain can do very well, and long-term memory is something that the brain can do very well. So we tried this out too. It works fine, but I'm not going into this right now. So here's the conclusion of this RNN part. And because I'm pretty much out of time, I would like to take 2 more minutes to at least kind of show you the other two, the idea of the other two tasks that we do. No questions. Okay, so the next one is very different. This is really take a classical problem. In our case, it's max cut. Max cut is this kind of ridiculous problem where you have a many-body system and there are a many node system and there are vertices between the nodes. And the question, if you kind of make one line through all of these nodes, and close it again on itself at the end. How many of these connections, how many of the vertices can you hit exactly once? You are not allowed to hit it more than once. Okay, and so this actually can at the end be connected to things like traveling salesman problem, etc. They are in the same complexity class, so that's why it's a benchmark problem. And what we are trying to do is taking a classical algorithm. In this case, it's Markov chain Monte Carlo, and put a little bit of quantum in it and see whether we can do better. Okay, and I'm not going into, this is also on the archive since December. I'm not going into any of the details here. So perhaps I show you just the one, namely the goal is here to find a really efficient hybrid algorithm to solve the max cut problem. And the idea here is just look only at this figure. Typically, classical optimization landscapes might look like that. They have a global minimum that is probably somewhere here and a lot of local minima. And the problem with all machine learning, this is classical and quantum, is how can we make sure that we are in the global minimum and not in one of the local minima. So what we are basically doing here is we find that a variational quantum eigensolver is very, very good in finding the global minimum if we are somewhere in a close neighborhood of the global minimum. And the Markov, the MCMC is the Markov chain Monte Carlo, which is basically a Monte Carlo metropolis type of algorithm, which I'm not going into depth today, or at least not, yeah, is very good in sampling everything and making sure to find at least the neighborhood of the global minimum. It doesn't necessarily find the global minimum, but it finds somehow the neighborhood by really very, very efficiently sampling basically all space. And this one works very well by just basically combining these two. And I'm sorry, here this is, so the VQE finds the local minimum. The MCMC finds the global minimum, and we are basically doing this once, going here until we are satisfied, and then going into this one once more. And what this gives at the end is something like this. So there is also a temperature. It's just an e to the minus I beta of whatever kind of minimum we want to find. And the point is, this of course needs to be optimized. If it's too much, we might find this global neighborhood, but we will immediately jump out of it. If it's too small, we will not even find it. It will still get stuck around the local minimum. So here is one of the examples where we still somehow get stuck in potentially in one of the local minimum. But if we make the temperature large enough, this is basically the MCMC part. And then we go into the VQE at the very end. And as you can see, the accuracy that you can get here is extremely high. And it's actually, and that one I don't show you here, but in principle, it can be considerably faster than if you do either only classical or only VQA. And the last one, I don't even want to show you more than just the title. and the idea. This is what Abigail did. She does reconstructing quantum states. So it's basically trying to find many body phases. Like, for example, this is similar to what Misha said, but a little bit simpler case. So it's basically doing the quantum analog of this one here. Okay, so what is this one here? These are all not people. These are all phases that the machine produced itself. Okay, so I'm not giving any privacy away or something like that. All of these people don't exist. There is and if you want to try this yourself, you can go to this website. This person does not exist.com. And this is what a generative model does. Sorry, again. This is what a generative model does. So that is the model that not only learned to whatever, for example, differentiate a human face from a dog face or from a t-shirt, but can actually, you tell this, okay, why don't you give me a picture of somebody who might look like perhaps a kind of a half Caucasian, half Asian woman, and in her whatever 20s, and produce me a nice picture. Okay, and we want to do the same thing where we say, okay, we want, for example, a quantum spin liquid state. Please, computer, produce me a quantum spin liquid state. And we cannot do quantum spin liquid states. That's hard, but we can do some of the simpler kind of Rydberg array states. And with that, I will just stop. Thank you.
Professor Yellen, thank you so much for a very interesting talk. We have time for one short question.
Be nice in the first one when you talk about the symmetry. If one can discover a new symmetry that we did not thought about it for different phases.
So what you want to discover, a completely new symmetry?
New symmetry that we are not giving to the machine.
So the point is, what we give to the machine is the way how we parameterize, right? That might or might not give any new symmetry, okay? The point is, a priori, we know nothing. Here, I just gave you a GHZ because I know as the all-knowing power that this was GHZ. I also did not know this, right? But the idea is really to find whatever symmetries are allowed within the parametrization. Okay, of course, we can go all out on the parametrization. We say, okay, we put all degrees of freedom in. In that case, we can find any symmetry. It will just take very long and a little bit bigger quantum computer than what we have right now. Yeah.
Maybe one more short question.
Hopefully short question. So you started to draw an analogy here between, coming up with different quantum phases and these generative models. What other sorts of like classical machine learning models are you trying to draw analogies to in this sort of quantum space?
I gave you 4 examples right now, right?
Yeah.
This is, I think, from what we have done so far, this is pretty much it in terms of analogies. But yes, I think this is what most people do so far. They try to do, I think also what Sabre was talking yesterday about chemistry. I mean, quantum chemists, they are pretty good, right? I mean, that's done on a classical computer. So the question is, can be done better? So this is of course, and you ask a very good question. When do we come up with tasks that we haven't even tried so far, ever, okay? We are not, so far, we are not.
Thank you.
All right, let's thank Professor Yellen once again.
Thank you.
And now we will have a short break and we will resume with our next talk at 11:15. We will have our special guest from JP Morgan Chase with their wonderful talk. Yep, thank you. Another short announcement for the students traveled outside of Purdue. Please reach out to the business representatives at the registration desk about reimbursement. Thank you. Like it doesn't matter what you take.
They used to have for the last semester.
Sorry for interrupting. While we are present.
All right, good morning, everyone. Welcome back. This morning it is my pleasure to introduce the JP Morgan presenters. First of which is Marco Pistoia. Marco Pistoia, PhD, is Managing Director, Head of JP Morgan Chase's Future Lab for Applied Research and Engineering, or FLAIR, where he leads research in various areas, particularly quantum computing. He joined JP Morgan Chase in January of 2020. In May 2021, he was nominated for one of JP Morgan Chase's 45 Distinguished Engineers, which is the highest title available in that firm. Dylan Herman is a quantum computer researcher at JP Morgan Chase's FLAIR labs. The focus of the FLAIR quantum program is to develop quantum algorithms for financial applications and quantum resistance cryptographic solutions. Dylan received his bachelor's degree in electrical and computer engineering and computer science from Rutgers University in New Brunswick, New Jersey. He joined JP Morgan Chase in 2018. His current focus is on quantum algorithms research applied to machine learning and optimization. Would you please give it up for Dylan and Marco.
So, thanks very much for having us here today. So actually, this is the JP Morgan Chase Quantum Day of Learning. So we were very happy to be here to tell you about our research, and there will be another panel this afternoon. So I just want to make sure that you guys know that JP Morgan Chase is not only a bank, but very technological company. We have so much going on, and as a matter of fact, it's unique in the industry to have a bank with a research lab. It's the Future Lab for Applied Research in Engineering, FLAIR for short. Okay, oh, much better. So, as I mentioned, Dylan and I are part of the Future Lab for Applied Research in Engineering. I'm the head of research at JP Morgan Chase. And it's unique in the industry to have a research lab in a bank. And we do research in different areas, particularly quantum technology. So it's not just quantum computing, but also quantum communication, which is another branch of quantum technology that has to do with cryptography, to create solutions that are resistant to quantum computing attacks. So I would like to give you a quick overview of what we're doing and why we're working on quantum computing. The reason is that quantum is a very disruptive technology with the promise of becoming like a solution that can speed up the execution of applications with high complexity and also increase the accuracy of those solutions. So as a matter of fact, as you can see from this report by McKinsey, you can see that finance has been identified as the first industry sector to benefit from quantum computing among all the industry sectors that are there in the world. And these benefits from quantum computing will materialize not only in the medium and long term, but also in the near term. And the reason for this is that we have an abundance of use cases. Dylan will present a few of them. So in finance, there are so many use cases that have high complexity, exponential complexity. So they lend themselves to the computational power of quantum. And additionally, in finance, time is of the essence. It's necessary to solve the problems fast because the market is very volatile. So unlike other domains where you can afford maybe a little bit more time, in finance, you have to get answers in real time. However, as good as quantum is, there are two risks that this technology poses to our industry, but also to our society. The first one, first of all, it's maybe this is not a risk to society, but a risk to companies. The risk is to be left behind. So right now, quantum computers are not yet powerful enough to solve problems that we solve every day using classical computers, of course, with approximations and so many other things. So quantum computers have not yet surpassed classical computers. So somebody can say, well, we have time, you know, like we don't have to really work very hard right now. Let's just wait for quantum to arrive and then we will transition. Well, transitioning from classical to quantum is actually very, very challenging. It's not like moving from your applications from one programming language to another or from one operating system to another. It's a totally different paradigm, as you guys know. So it requires having, first of all, identifying the applications that need to be transitioned. It also requires having a team of experts in the company and having like an overview of the quantum ecosystem to choose the right partners. So it's a lot of work, and it's very important not to be left behind, because otherwise, you know, when quantum advantage becomes a reality, then a company that has not transitioned to quantum computing will be caught off guard. So one of the solutions that we have found, for example, right now, as I mentioned before, it's very important to identify the right partners. So JP Morgan Chase has been the first company to form a partnership with Honeywell Quantum Solutions, which has now detached from the Honeywell International company and has become an independent company after merging with Cambridge Quantum. It's called the Quantinuum. So by using a unique feature of the Quantinuum computer, we were able to accelerate the execution of certain algorithms. So Dylan will present a portfolio optimization algorithm that takes advantage of this particular feature. The feature is called the mid-circle measurement and reuse, and it also allows for quantum conditional logic. So in essence, what happens is that in traditional quantum applications, you can see at the bottom left corner of the slide, you can see that all the measurements have to take place at the very end of the execution. But using mid-circle measurement and reuse, and also a quantum conditional logic, you can measure a qubit during the execution in isolation. Then you get the classical value, 0 or 1. You reset the qubit and you can now reuse it. So effectively, now you have almost like an extra qubit because you have used it up to this point, but now you can reuse it. So it increases the computational power of the computer from a logical perspective. And also it gives you the ability to use the value that you have read in making decisions, conditional decisions during the execution of the program. So you can actually do quantum conditional logic. One thing that we discovered when we wrote our first paper on quantum option pricing, which was published in the journal Quantum Journal, is that the algorithm for option pricing is called the amplitude estimation. This algorithm has quadratic speed up. So in other words, the complexity is still exponential, but the exponent is divided by 2. So it's actually significant. However, the application layer, which consists of all the processing to basically create the distribution that is passed as an input to amplitude estimation, ends up having exponential complexity itself. With this algorithm, we were able to reduce the complexity of that application layer. So the application layer sometimes is totally classically executed. In our case, we execute that using a quantum computer as well. So we have the distribution loading executed using a quantum computer, and then amplitude estimation executed using a quantum computer. But now with this new technology, the application layer is no longer the bottleneck of the execution. So Dylan will talk about more other algorithms that we have created. We have actually several. You can see here, if you go to our webpage, it's hard to remember the URL, but if you Google JP Morgan Flare, it will be the first entry. So you can see all of our publications. We publish extensively because we believe that this is a time in which researchers have to collaborate with each other. It's not time to compete, but time to collaborate and get feedback from the scientific community and so on. Our publications in 2 years and 3 months have received over 550 citations, which is, I think, a good result for a new research lab. And we also have patents, so we keep ourselves, visible in the scientific community. But Dylan will give you more details about the algorithms. I just wanted to talk more about the second risk of quantum computing. This is the one that is a risk to companies or universities or labs, the government, but also a risk to society. In other words, quantum computing, being such a powerful technology, has the potential of breaking today's public key cryptography. We know that public key and private key, the two keys that we use in asymmetric cryptography, are actually linked with each other. You can compute somebody's private key from the public key. Theoretically, it's possible, but it requires such a complex series of operations that a classical computer will actually take trillions of years to be able to compute somebody's private key from the corresponding public key. What can somebody do with somebody else's private key? Everything. They can decrypt data, they can impersonate that person, digitally signing documents on behalf of that person, and so on. So it's really a serious threat. However, there are two solutions. One is called the post-quantum cryptography. Post-quantum cryptography consists of new cryptographic algorithms that are supposed to be resistant to quantum computing. So far, there are, I think, 7 or 6 algorithms that are finalists, considered finalists by the National Institute of Standards and Technologies, NIST. These algorithms are not broken by quantum computers because nobody has yet found out how to break them. However, we are also, so this is actually not a research direction for us. I think this would be a research direction for cryptographers. In fact, there are cryptographers all over the world that are working on post-quantum cryptography, trying to find algorithms that, cryptographic algorithms, classical cryptographic algorithms that are very difficult to break. RSA and Diffie-Hellman and the elliptic curve algorithms that we're using today are actually vulnerable because they're based on mathematical problems. The security of those algorithms is based on mathematical problems that are known to be difficult to solve. For example, the factorization of large numbers into prime factors. But this is a problem that can be solved efficiently using a quantum computer. In fact, Professor Peter Shor at MIT created the very famous Shor's algorithm, which takes its name from the creator of the algorithm, of course. With this algorithm, you can actually factor large numbers in polynomial time as opposed to exponential time. Now, how many qubits do we need to break RSA and Diffie-Hellman? So it was thought at the beginning, the first intuition was that it would take 20 million qubits to break RSA with a key of 2048. Then recently, Google and an academic institution in Sweden proved mathematically that it might take just 8 hours with a computer having 1 million qubits. But last year, there was another paper that was published that showed that with just over 13,000 qubits, you can break 2048 RSA, 2048-bit RSA in 6 months. So it's becoming like a serious threat. But the research that we are conducting is in quantum key distribution. So quantum key distribution is a technology that uses the power of the principles of quantum mechanics to secure the communication between two parties. It has been mathematically proven to be unconditionally secure. So nobody can break quantum communication, quantum key distribution, because to break quantum key distribution, you have to break quantum physics. And we actually, this is so interesting. I'm very excited because I'm part of this project, and we were the first company worldwide in collaboration with Toshiba and Siena, two other companies that collaborated with us. We were the first company to prove the ability to create a quantum key distribution network capable of supporting real-world applications, especially mission-critical blockchain applications. We secured an application that JP Morgan Chase uses for payments. We achieved 800 gigabits per second of encrypted data. We achieved also the creation of 258 keys per second that the two parties in the communication can use to exchange encrypted data. And the algorithm used for encryption was a symmetric algorithm, so it doesn't use public key encryption. And it's the AES algorithm with keys of 256 bits. Overall, we were able to demonstrate the ability to multiplex the channel where the keys are exchanged with the channel where the encrypted data is communicated, and with additional data that we actually put there on the fiber just to create more challenges like interference and so on. And we were able to transfer 2.4 terabits per second. So this is actually real world standards. The only limitation of this is that we achieved a distance of only, I can say, 100 kilometers. We need to do more research to extend the distance to thousands of kilometers, of course. But the research is going on right now. So as I said, 100 kilometers, however, is already sufficient to secure communication in metropolitan areas. So I wanted to quickly show you how QKD works. So the two parties, as you guys probably know, are usually known as Alice and Bob. And the attacker, the evil one, is Eve. So in quantum key distribution, you have two channels. The red one is actually the quantum channel where the keys are exchanged. And the green one is the quantum secured channel. So the one in which the encrypted data is exchanged. What happens is that Alice and Bob can actually exchange the same key by using the principle of entanglement. So the key is not exchanged as a series of bits, but as a quantum state. And so the fact that you cannot measure a quantum state unless you want the quantum state to collapse guarantees that Eve, if Eve wants to learn the key, she has to make a copy of the key, she has to measure it, and that will interfere with the communication. So these are the series of experiments that we conducted. So the first four are experiments that we conducted to verify that the communication was stable. So we tested the distance, polarization fluctuations. We tested the bit rate and so on. The fifth one was a little bit more interesting, maybe from a security perspective, because we verified the ability of quantum key distribution to automatically detect an eavesdropper. As I mentioned before, when there is an eavesdropper, the quantum state collapses, and Alice and Bob have an opportunity to stop communicating. This ability is not there in traditional classical cryptography. And the sixth test blockchain application is the one in which we secured a blockchain application that, as I said before, is used in production at JP Morgan Chase. So just to summarize everything, I think this is a moment in which it's crucial to become quantum ready and also crypto agile. In other words, transition the assets of a company to quantum computing, and at the same time, make sure that your infrastructure is secure. So there are so many job opportunities now. Since I'm talking to an audience of academic people and students, I wanted to say like quantum is opening up so many opportunities because the quantum stack is very diverse. It goes from, say, the cloud-based interface, applications, algorithms, circuits, and hardware. And then we have, of course, the security aspects with cryptography and so on. So it's important for a company to identify the applications that need to be transitioned to quantum. Also in these applications, which ones are going to be the applications that can benefit from quantum first before other applications. It makes sense to actually start to address those applications because it's almost like the first wave and you can already make progress by addressing those. And then it's crucial to keep monitoring the quantum ecosystem. At JP Morgan Chase, we have access to 7 different quantum computers from 7 different vendors because we don't know which technology will be the winning one. So we just want to be on top of everything. So in our quantum stack, we have integrated circuit transpiler that allows us to recompile our circuits to different hardware without having to rewrite the code. So from a software engineering perspective, we also did, like I think we contributed some new technology by having this type of compiler integrated. And finally, it's very important to have a team of experts in the company. So we have a very large quantum team, quantum communication and quantum computing. And we're very excited to tell you about this. Now, Dylan will go into the quantum algorithms, but I also wanted to let you know we're hiring. So you will see at the end our email addresses at the last slide. So please email Dylan and myself if you are interested in applying for a position in quantum computing or quantum key distribution at JP Morgan Chase. Thank you. Dylan.
Great. Test. Okay, cool. All right, yeah, so I'll be talking about some quantum algorithms research that we've been doing. So the first one is related to portfolio optimization. So as Marco mentioned, we have a variety of use cases, and one of them in particular that deals with the asset wealth management group is regarding portfolio optimization. So portfolio optimization has a variety of formulations. So it can be formulated as a combinatorial problem in which you were able to choose from a variety of assets that minimize both your risk and maximize your return. Or it could also have continuous valued variables, which can formulate as a convex problem. And so this is some work in which we was presented at the American Physical Society regarding trying to bring quantum solvers for portfolio optimization to the near term. And so here we have the formulation of portfolio optimization that we dealt with. So this is simply known as the mean variance portfolio optimization or Markowitz portfolio optimization. And so in this case, it's a convex problem. And so the valued outputs are it's particularly a quadratic program. And so here we have a risk, or quadratic form risk that we're trying to minimize, along with constraints that constrain the budget and both the return. And so here, because it is a convex problem, we can formulate it in terms of taking Lagrangian and using the method of Lagrange multipliers to formulate it as a linear system. And as you may know, quantum potentially provides exponential speedup in certain cases for solving system linear equations. So we wanted to see if we can apply portfolio optimization to this. And this is actually based on a paper by Patrick Rydberg and Seth Lloyd on applying the HHL algorithm to portfolio optimization, specifically this problem. However, we wanted to try to bring it to more the near term. Specifically, we were able to run experiments on the Quantinium hardware. So as Marco mentioned, we have access to Quantinium, formerly Honeywell Quantum Solutions. And so we'll also have some results to display on running this algorithm. So you may be familiar with the quantum linear systems problem already, but just to kind of review. So the quantum linear system problem is an analog of the typical linear systems problem. However, in this case, you produce a quantum state as opposed to an actual classically accessible vector. So in this case, we have to figure out what do we do once we obtain this quantum state. So we have an exponential speedup for solving this particular problem. If you're trying to solve this exponentially large system and actually produce the quantum state, that a quantum computer to do exponentially faster. However, to actually read out this state, we need to pay a cost. So we need to figure out what can we actually do with the state without performing a full tomography. So HHL has a few assumptions, and of course, there have been a variety of improvements beyond HHL, but HHL was the first quantum linear systems solver. And so as long as the system is sparse and robustly conditioned, so it has certain conditions, requirements in the condition number, HHL can obtain a exponential speedup. And so here is just an example between a conversion between the classical linear systems and the quantum linear systems problem, in which you produce the quantum state solving it. So there's a few potential things we can do with this vector without reading it out. If it is sparse, potentially we can sample from it and obtain a variety of the weights. Alternatively, we can compute various observables or expectation of observables on this quantum state that can be useful for a variety of financial metrics. We could also compare candidate portfolios to the quantum the state produced by the quantum computer. So this is an overview of the NIST-HHL framework. So this was actually based on a hybrid variant of HHL that is more catered towards the near term. Unfortunately, it does not gain the full exponential speedup of HHL. However, potentially in practice, we do gain some benefits. As of course, there are a lot of heuristic algorithms that we can only see by actually doing benchmarking what their benefits are. So the hope is that this is one of them. So the idea that this was based off of was a hybrid version in which they split up the components of estimating the eigenvalues of the matrix and performing the actual inversion that produces the quantum state. So here in the framework, we start off with estimating the eigenvalues. So here we utilize the mid-circuit measurement and reuse technique that Marco had mentioned. And there's a variant of the quantum Fourier transform that was produced, or the inverse quantum Fourier transform that was produced many years ago that was able to reverse or rearrange the order of the measurements so that you don't have to defer them all to the end, but you can reuse a single qubit. And in this case, when you're trying to just estimate a single eigenvalue or produce a distribution of eigenvalues, you get this non-unitary variant that can be useful for producing the distribution of eigenvalues. So that's what we first start with here. We called it QCL QPE. This makes use of a second technique that Honeywell or Quantinuum also support, which is known as quantum conditional logic. It's kind of the quantum if statement. So you can measure a state and utilize these measurement results to perform classically controlled gates. And that allows you to implement this variant of the inverse Fourier transform. And second, we use these, now that we have this distribution of eigenvalues, this is where the exponential speedup is gone. However, we can now post-process eigenvalues to more efficiently figure out how to invert perform the inversion. And by doing this, we reduce the cost that's required to do with typical NIST implementations of HHL. So if we have a fault-tolerant computer and many qubits, we can actually do arithmetic. And this allows us to compute things like arcsine and other trigonometric functions that are required for performing this inversion. However, unfortunately, NIST devices are very small, so we want to see if we can improve the current version of NIST, which actually requires exponentially deep circuits. So in this case, by post-processing, we're able to figure out exactly the controlled rotations we want to produce the quantum state. So this is just a comparison of the two versions of the quantum Fourier transform. So you have here the standard QPE on my left. And so the standard QPE, known as the coherent QPE, requires a number of qubits that is linear in the bit precision you actually want to estimate your eigenvalues. And of course, this can grow a lot because the actual precision required to estimate these eigenvalues can be a lot. So on my right, we have QCL QPE, which is the semi-classical version I mentioned, which makes use of the quantum conditional logic and mid-circuit measurement reuse. In this case, the actual qubit required to estimate the eigenvalues, which is linear in the bit precision, is reduced to 1. And so as you see, all the measurements that were deferred to the end are now in the middle of the circuit. And these two are equivalent at the cost of now this being non-unitary and no longer invertible. For our cases, this works. So the second thing we introduced to this paper is a spectral norm scaling technique. So this is also a technique that can be used beyond this HHL, but we included in this HHL. So one particular, I guess, issue with a lot of these algorithms that make use of the quantum Fourier transform is the need to make sure that the eigenvalues are within a certain range. So because for actually performing the quantum Fourier transform to estimate the eigenvalues, you need to simulate the evolution that's generated by this Hermitian matrix. In our case, it is the linear system matrix. And so once we can actually simulate this evolution, we can get the eigenvalues. However, unfortunately, the eigenvalues are not necessarily normalized. So we created a NIST-friendly technique for estimating the maximum eigenvalue When you estimate the maximum eigenvalue, you can now scale things properly. And so once you have this eigenvalue less than 1, this is because of the periodicity of the complex exponential. And another case is that with the distribution of eigenvalues we have, they can be very concentrated around the center. So you see in this case, they're concentrated around the center. But however, we potentially have a lot of qubits that are useful for precision. So we can kind of spread them out or scale our eigenvalues so that the maximum eigenvalue is represented by close to 1. We can make better use of the qubits that we're using for our precision, in which case is the QCL-QP, so is 1. However, because even though with QCL-QP, we're using 1 qubit, the circuit depth still grows at the same rate as the original QP. And so this is a technique that is an iterative process in which we estimate the eigenvalues, and we perform this kind of scaling technique. So as you see, as you get a better estimate of the maximum eigenvalue, we can scale the distribution properly. And so as I mentioned, we execute some experiments on the Quantinium device. So here you'll see on my left the this HHL framework. And on the right, we did a couple of benchmarks of the QPE. So because, as I mentioned, this HHL is split into 2 steps. So we have the eigenvalue estimation step and the actual inversion. So in this case, we benchmarked the different variants of the quantum Fourier transform. And so in this case, we can see we could do, even though it's small, we can use a higher precision for the actual eigenvalue estimation. And the thing is that all that's required in this inversion step is that the inversion step needs to be able to separate eigenspaces, which doesn't necessarily require the resolution that's required to estimate the actual eigenvalues. So in this case, we can use a higher precision QP for the first step, which is QCL-QPA. And then in C, when we actually perform the full HHL, we can use a lower resolution that is just required to figure out what controlled rotations to perform. And so here we utilize the probability fidelity. So this is just taking the probability distributions of measurements and just comparing them. It's one metric. You could use a variety of other metrics. This is the one we just chose. So in this case, we could see it's slightly higher with the quantum conditional logic one. And so after determining the required bit precision for QPE, we went through a full end-to-end example. So in this case, we now have the eigenvalues from post-process. And so by post-processing, we can now determine the controlled rotations that are required to create the inversion state. So when you simulate the evolution, you have now your input vector that's decomposed as a superposition of eigenstates with their eigenvalues. And your goal is to invert them. And so that's a rotation gate. And so in this case, what we did is we produced the quantum portfolio state, which is a set of weights. And these weights tell you whether you should go long or short in a set of assets. And so in this case, it's not combinatorial. It gives you the proportion in which you want to invest in each asset. And so in this case, we compared utilizing a swap test, which allows you to perform the inner product of 2 quantum states. So we loaded the actual solution computed with a numerical solver, classical numerical solver, onto a quantum state and perform the inner product. And this allows us to tell how well it's working. So UCR, as I mentioned in the NISC error, there's a not really efficient or asymptotically efficient version that is typically used for this last controlled rotation step or the inversion step. And that requires controlling on every single eigenvalue that QPE can estimate, which can be very resource intensive for NISC. So that's called uniformly controlled rotations. They're also used for techniques for preparing arbitrary quantum states. So however, in our test, because we have the eigenvalues and perform this estimation prior, we can more finely tune and figure out what controlled rotations perform. And so we see there is a slight improvement. And even though this is small, we see as we scale up larger problems, this difference should become larger. And so that's the end of the first talk, which was really a financial problem, portfolio optimization. So this is in the realm of quantum machine learning. So this was some recent work done in collaboration with IBM Quantum and of course us. So this is regarding the expressivity of certain variations of quantum machine learning algorithms. So here, I'll start with the description of what's called the Boolean hypercube. So you may be familiar with this, but a Boolean hypercube, you can think of it as just a higher dimensional cube in which each point is a set of bit strings. So in this case, the 2-dimensional Boolean hypercube is just 0, 0, 1, and so on, which is a square. However, if we go to 3 dimensions, we have an actual cube, and this can go beyond 4. And so as we increase the number of bit strings, we create these higher dimensional hypercubes. And so on these types of structures, we can create functions. So we can consider real valued functions of Boolean inputs. So here's just an example of a real valued Boolean function. And so some work we did here. So this is regarding a specific set of Boolean functions on a Boolean cube called k-juntas. And so to kind of connect this back to a financial problem is in machine learning, typically you have as a variety of features, you have a larger number of features that are passed into your model. However, not all of them are important. So a k-junta is an example of from computational machine learning that tries to abstract this problem in which you have a variety of input features, but only a subset are important. So in this case, we have a function on a variety of bits, only depends on at most k of them. And so typically what we form with periodic functions is for analysis. You can also do this in discrete domain, such as finite abelian groups. In this case, you have the Boolean cube. And so this allows you to express any function on the Boolean cube as a linear combination of these simple characters here. And so just an example, the degree of a function on the Boolean cube is the maximum Hamming weight across all of these powers. So just talk a little about what variational quantum machine learning is. So you may be familiar with this. This is the hybrid technique of machine learning that is used in the near term. So in this case, this is definitely the variational paradigm for all variational algorithms, is that you have a quantum circuit that is classically parameterized. You have these control parameters in which you use to construct the circuit. You run the actual circuit. You obtain some expectation of a observable, and this information is used to update your parameters. In the case of machine learning, some of these parameters are also input features. So in this case, we have this variational quantum circuit, which is used to prepare the state, and then we can use the information that's the expectation of the observable to compute our loss function. And so this allows us to update the parameters, and it's a very easy model to use in the near term. So specifically what we studied were called linear quantum models. So there are two types of linear quantum models. So the first one is similar to the variational quantum circuit, in which you have some sort of embedding that encodes your feature inputs and constructs a quantum state, which is good in the near term because it's difficult to prepare arbitrary quantum states that encode vectors, like typically in machine learning, you have real valued vectors. In this case, you have some arbitrary quantum feature map that forms some nonlinear encoding on your input. And then you also have another parameterized circuit that is your model. So you train these parameters, these theta parameters that represent this linear model. And it's linear because it's a quantum analog of linear quantum models in which you take your input data, you map into some feature space, and within that feature space, you want to find a linear decision hyperplane. And so the second is known as the quantum kernel method, which instead of actually utilizing this variational circuit, you compute the inner product between these states. And so this is very similar to the kernel methods in classical machine learning. And these are both linear as they can actually be shown to be equivalent in a certain sense. And so the first thing we started off with was looking at types of quantum embeddings, so these U's that embed your input data that are feasible for the near term and also catered towards these functions of Boolean inputs. And the reason we looked at Boolean inputs too is that any discrete feature can be viewed as a set of Boolean strings because they can map to integers and then map to finite Boolean strings. And so in this case, we start off with a very simple one, which is called a phase embedding. So in this case, you use a single qubit per bit. And so this grows linearly with the dimension of your system or the number of bits you have. And so in this case, we show that any function of Boolean can be represented exactly by this variational circuit, assuming you have a strong enough quantum circuit. And so this is one embedding. However, it can be typically efficient because for each bit, you have a qubit. Another one looked at is known as the quantum random access code. So this is quantum random access codes are an example of quantum advantage where you're able to efficiently encode a higher set of bits in a single qubit and recover them with a higher probability than you could classically. So in this case, you can code 3 bits in 1 qubit. We weren't exactly using the QAC for its purpose, but we're using it as a quantum feature map. And so in this case, for 6-bit inputs, we utilize 2 qubits as opposed to 6. And so this allows you to encode them in a single qubit state. And so we then looked at is combining these into ensembles of models. So in machine learning ensemble is a model built off of other models, and you combine their outputs together. In this case, we looked at an ensemble of these QRAC-based models. So QRAC is quantum random access code. And we try to study what types of functions on the Boolean cube these things can learn. And so we found an interesting result. It's not the exact same as the phase embedding. However, they can express a variety of these junta functions, which depend on a subset of the inputs. And the idea is that with you can express any function of degree n over 3 with n over 3 qubits. And so potentially this provides some sort of saving for these functions. Whereas in the case of this previous embedding, you require n qubits per bit. And so this shows that given a powerful enough circuit, you can represent these functions. And so here briefly, we have some experiments. So these are experiments executed on the IBM quantum computer. And so here the goal was just to study, can these functions actually express these functions in the Boolean cube, or the ones we're looking at? And so the idea was not to study generalizability, which is of course important in machine learning, and it is true learning. In this case, you just wanted to numerically show that the theorems we derived showing the full expressivity of these functions. And similar work has been done also in the continuous domain with continuous valued inputs. So here we have an example of showing the alignment between for each possible. So if you have 3 bits, there are 8 possible inputs. And so for each input here, we show the alignment between the predicted value and what the actual value is. And we also plot the Fourier spectrum. So while the Fourier spectrum is inefficient to actually compute on demand, in this case, we just show it to show the actual alignment, that you can compute the Fourier spectra of this quantum model and show that they align with what the expected value is. And so there's also the expression. So it's a simple function. And so this is a low degree function, even though it depends on all inputs. As you can see, the powers in these negative ones are all a single one, only a single bit. So it's an example of low degree. And so, yeah, thank you. I went through quickly the use cases that we have. And so there's a variety of others we didn't get a chance to go through. And so we have a website here, and I'll pass it off to Marco.
Thank you. Thank you very much.
So for this HHL, so how do you avoid the use of QRAM?
So in this case, yeah. So the actual simulation, the Hamiltonian simulation technique is performed classically. So in this case, you have the Hermitian matrix, you compute the unitary, and you actually have the actual unitary matrix that you involve, and you can deconstruct it. So in this case, yes, it's not, you don't actually have QRAM, and you can't solve large scale problems with this.
So you don't.
Yeah, you do not. Yeah, you
Will
don't.
not be kind of practical.
Exactly. Yeah. So in this case, yeah, it solves more problems.
Anybody else?
I'm curious about your quantum blockchain. So does that mean, I mean, the blockchain kind of provenance is the integral point of the blockchain itself, right? So is the blockchain that you are studying, is that living only in the quantum net, or do you have some kind of a translation between the two? So how does that work?
So the one that we created was a very simple blockchain, I have to say, because it only contained 2 nodes. It was in a lab. I have to say the lab was a perfect replica of the environment that we have at JP Morgan Chase. So, sorry, is my microphone working? Thank you. So you only had 2 nodes. So what we enforced is confidentiality of data, which is a requirement in permissioned blockchains. So sometimes in many blockchain applications, confidentiality is not a requirement. Everything is publicly available in the sense everybody can read the data. However, for payments, for an application like payments, confidentiality is a requirement. So what happens is that you want to assure that all the nodes in the blockchain have access to the information, but nobody outside of the blockchain has access to the information. So this is achievable using quantum key distribution. Now, there is more that needs to be done. We actually wrote a paper and the link was in the presentation, but I forgot to highlight it. So it's on archive right now. So for blockchain, confidentiality might be a requirement, as I mentioned, for permission networks, but for non-permission networks or for permission networks too, integrity and provenance, as you mentioned, are also a requirement. So as of today, integrity and provenance and no repudiation are all properties that are guaranteed by public key cryptography. So what can we do, given that we have a quantum key distribution for confidentiality? How can we assure provenance, no repudiation, and data integrity? We can use post-quantum cryptography, or we can use some new work that has been done. There is some recent research that explains how to achieve digital signatures using quantum key distribution as well. So that's actually part of our future work. Thank you.
All right, do we have any more questions? All right, join me in thanking our speakers one more time.
Thank you.
We'll be back at 1 o'clock, just like on the schedule. So we're losing just 5 minutes from lunch. So be back here at 1 o'clock. Thank you.
A poster at the poster session and would like to keep showing off your posters, we have boards around the hallway where you can pin them up, and they'll be there throughout the rest of the week. All right, folks, if I can have your attention, please. Hey, y'all, we'll get started here. Hope you all enjoy your lunch. We'll be starting off with the panel discussions soon. But first of all, we would like to welcome Professor Meyer for some remarks. So Professor Teresa Meyer is the Executive Vice President for Research and Partnership at Purdue University, where she oversees $670 million research enterprise of the university and support holistic engagement with federal, industrial, and global strategic partners. Prior to her role at Purdue, she was the Vice President for Research and Innovation at Virginia Tech. During her 22-year at Penn State University, she served as the Associate Dean for Research and Innovation and Engineering, the Site Director of the NSF National Nanotechnology Infrastructure Network, and the Director of Materials Research Institute Nanofabrication Laboratory, which enable cutting-edge materials techniques to be shared among researchers in the academia and the industry. She's widely recognized for her work in advanced manufacturing of nanoscale electronics, optical, and biomedical devices, which has been supported by the NSF, DOD, DOE, NIH, and industry. Without further ado, Professor Teresa Myers.
Thanks, Morris. Doesn't sound like this is on. Is this on? Okay, great. Well, thanks for that very lengthy overview. As you may have heard, my own background, although not directly in quantum, is certainly closely associated with the work in quantum. This morning, I was giving opening remarks at a microbiome symposium, and it was a little bit more difficult stepping outside of my own field. But I want to just spend a couple of minutes welcoming all of the attendees, our guests, all of the students who are here and postdocs who are here for the summer school to Purdue. We're really excited. We've been making significant strategic investments across multiple colleges, the College of Engineering, the College of Science largely, to really enhance our support for the quantum initiative that's really very much aligned with the high emphasis that the nation is placing and the world is placing on quantum, both for really looking at the quantum science and technology aspects. And we're really proud that we have a diverse group of faculty who are really spanning the gamut from theory to experiment in many of the core aspects. It was a real privilege to have collaborated with Oak Ridge, Microsoft, and many other partners to be a core partner of one of the DOE quantum science centers. And that's core to the summer school that we're hosting here today. It's a pleasure for me to serve on the governing board and advisory board of that initiative. And I think, again, it's really injecting significant resources and really inspiration into the community at large. Of course, we have many other initiatives and related programs that I hope that you are hearing about as well. I'd also like to take a moment to thank the sponsors of this summer school, JP Morgan Chase, IBM, and Cold Quantum. I tried to make sure that I covered all of that. Your support overall is greatly appreciated, but particularly your support of the summer school, because at the end of the day, we do great research at our universities, but our number one priority is the education and training of our next generation of talent for the country and for the world. So we're really thrilled, again, to have everybody here. I hope you've found it to be a really productive and inspiring environment. And I hope that you're taking away, not just an overview of quantum, but understanding how different communities are working together from academia, from industry, and from the national labs. So with that, I think we're going to move on to the panel. Oh, one more. Thank you. I want to thank Sasha, Vlad, our other faculty, and of course the students and staff who, these are large, complicated events to organize. And we just really, on behalf of Purdue, we really appreciate your support and leadership to pull this together.
All right, at this time, if we can have all the panelists come up and take their seat. So as just a breakdown of what's gonna happen the next 45 minutes. You should review my grade in 606. You can have a very thorough breakdown of my grade if you like. This is your chance to grill me. So again, my name is Morris. I am a student of Professor Shalive and Bodhiseva with work focused on single photon emitters. And here we have Professor Suzanne Yellen from Harvard, Professor Michel Lukin from Harvard. We have Dr. Pistoia. I should have checked that before. From Chase. Professor Klimek. I took his class. So he's giving me a hard time from Purdue. Okay. And of course, we have Maria from Microsoft. Welcome. And of course, Professor Meyer here at Purdue. So I'm going to warm up these panelists for about 10 minutes or so, and then we're going to open the whole floor up to any Q&A. So this would be your chance to ask any follow-up questions from any particular lectures, maybe something, if you want to stick to the theme. Our theme today is from quantum science to quantum industry. So if you have questions about the whole integration going from basic research up to the growing nation quantum industry, this is your chance to ask that as well, while our distinguished guests are here. So I guess we have panelists from all sorts of backgrounds with deep roots in basic science, or perhaps deep roots from other industries. So I just want to ask, at what point in your career, start off maybe from Professor Yelling and then further down along, at what point in your career did you begin to direct your research or perhaps your work to quantum computing and information? If you haven't yet, what's intriguing you about the field?
Well, to be honest, that crept up on me. My background is theoretical quantum optics, and especially in the early days, quantum information, especially kind of the one towards application, building quantum computers actually was pretty well embedded into quantum optics. So I remember I was part of my first quantum information workshop during my first year of my PhD students days. And these days, obviously, you can't really do without quantum information anymore. So I think it really ramped up since that time. And it's if my talk today somehow suggested that this is really, you cannot really divide quantum optics from quantum information.
Yeah, I guess, yeah, we were kind of privileged to be a part of the, so we kind of grew up as students at the time when, like, Shor's algorithm, was invented. People started to think about quantum error correction, and it has been kind of fascinating, to see how this, grew from basically a field, which is definitely, fundamental basic science, to something where, you know, there is some industrial component, you know, there are some, you know, people start building quantum machines, kind of non-trivial machines, you know, which start performing non-trivial tasks, you know. So I think, I guess we'll talk about it more, but, you know, I would say it is important to emphasize that basic science is not done, you know, and I think there are a lot of questions which still remain to be answered. And I think that, you know, at least, you know, many of us believe that it's, you know, the combination of fundamental research, cutting edge fundamental research in the universities, the industry, and also government labs. That's what it would take to really make these ideas, you know, practical and useful for humankind at the end.
I got my PhD in math, and in 2015, and my first interest at the beginning was actually not in quantum. I was working on creating mathematical models of programs, and then using linear algebra constructs to verify whether those programs would work correctly. And there are several layers of exponential complexity when you build the mathematical models of programs, because you have to take into account possible paths of execution, all the possible paths of execution. And when you do that, you end up with unfeasible paths of execution, which lead to false positives. So I became interested in quantum computing back then because I wanted to reduce the complexity of the static analyzers of programs and make that complexity potentially polynomial. At the time, I was working for IBM Research in the Watson lab in New York, and there is a big effort in quantum computing at IBM. So I was actually working in the quantum computing space, leading a team of researchers working on quantum algorithms and applications. And so that's how I started. And 2.5 years ago, I moved to JP Morgan Chase to do pretty much the same job, you know, leading the effort, the research in quantum algorithms and applications, and also quantum key distribution.
Professor Klimek?
Oh, I graduated here in '94, and the thesis title was electron-electron and electron-phonon interactions in quantum transport. So quantum was sort of my research work. And I went to Dallas to TI, and we built models and tools for real quantum devices. And at the time, I remember workshops that started with quantum computing. We had local workshops at TI and in Dallas. That seemed quite far away. And in 2002, I made a pitch to ARDA, which was one of the funding agencies for quantum computing. If you really want to build a device, you got to stop drawing stick diagrams of devices, but you really got to calculate how a real device would work with quantum states that I extended, etc. So that's how I got started in quantum computing, really.
Maria?
For me, I'm actually a classically trained software engineer. I did have a surprising amount of physics in my curriculum, which I worked very hard to forget after graduating. But it never occurred to me that quantum computing can be a career at that point. So I actually learned about quantum computing a little over 5 years ago when I interviewed for Microsoft Quantum team, who were at that point hiring software engineers to work on the compiler for the quantum programming language, which later became C#. So that's kind of how I learned about it. And the fascinating thing about it for me is not just its promise, but also what a wonderful brain teaser it is. I love puzzles, and this is a good one.
Professor Meyer, you got more to add?
Great. So I won't be able to speak to my own experience in translating science to industry, but instead I thought I would just share from a national perspective, and maybe you've already covered this, but I think it's really it was very exciting when DOE launched the Quantum Science Center initiative, that the leader, Chris Fall, who at the time was overseeing the development of the program, very intentionally said that rather than this just being a big center initiative that would span the interface of the DOE national labs and academia, but very intentionally brought industry in. And quantum in particular, as we think about, really we're still driving the fundamental science while at the same time thinking and having initiatives that recognize the importance of being use-inspired, understanding and thinking about what some of those really important end goals are. And so not only are we seeing very, very significant investment from large companies, one thing that's not represented on the panel is really the growing amount of investment from the venture community, which I can't really think of another field where you're pushing the envelope and really the boundaries of the fundamental science and trying to drive breakthroughs at a very early stage that are receiving such significant investment from everything from venture, which is driving small companies through large companies, and that foresight on the federal government, again, to really bring industry in as a core partner.
And I guess to that point, from the investment point of view, maybe I know several panelists here have either worked with startups, co-founded startups, or worked with industry partners. Like, is it less risky now to get into a startup with quantum technologies, quantum computing, or do you still have to make all these considerations that Professor Meyer was describing? Perhaps if there's a volunteer that wants to.
So first off, I have to actually make a public disclosure here that not only am I a professor at Harvard, I'm also the co-founder and the, what's it called, stockholder of Query Computing. I do not have any executive role there. So, yeah, I would like to answer this question by kind of going back to the kind of beginning of my talk, where I try to maybe in a somewhat provocative way to kind of indicate two big problems that this field of quantum is facing. And one problem is certainly how to build large-scale machines, which is really a problem that we do not know how to solve. We have to be very honest, And the second problem is, once we have these machines, apart from few very limited use cases and scientific applications, which I think there are plenty of, we really do not know how to kind of take advantage of this quantum power. And so with that in mind, I think it is kind of intriguing to wonder, what is kind of going on? Why are all these venture firms investing, and whether there is real opportunity here and what it is. So my answer to that is twofold. So first off, in this field, we like to think that it's a marathon and not a sprint. So I think it will take, at least a decade, or more of investment, of substantial investment in this field for this quantum to really start kind of bearing fruit, for solving kind of everyday problems, like financial problems that, Marco has to worry about, So at the same time, I do think that there is a special time now, there is a special moment, and this special moment is in that machines are being built, which are large enough, programmable enough, and what's most important, quantum enough, that we can really start kind of using these machines to, learn how to build even bigger machines, but also start to explore in a kind of responsible, down to earth, but nevertheless kind of, scientifically rigorous and exciting way, I would say, exploring some of these, applications, and many of these things were mentioned, today, quantum machine learning, optimization, all of these things, they are, there are, machines of scale now of volume where we could really try to kind of run these algorithms and frankly make discoveries. And in that, my thinking is we are now in this field where classical computers have been in, I would say, 1950s. I used to say 1940s. I'm sort of progress. So, and who could imagine in 1950s, that we will all have a computer in our pocket, So, I mean, but that was a time where these machines were kind of functional enough so that one could really start, running basically scientific experiments on them. And most of these things that people did were initially really focused on science, but, things like Metropolis algorithm, so people really had no idea, how well it will perform. And it took, 40 or 50 years to prove anything about that, so, but this was a time where people really ran some things and really figured that they work very well. And then from there, you could actually make a roadmap, if you really want to accelerate certain specific, algorithm class, you should do X, Y, and Z. And I think what is very special is that we are in a moment where this is possible. And I hope that this view, I mean, it's for us very exciting as scientists. I do think that industry, plays and will play a very important role, both from the point of view of really pushing engineering innovation, something that, we can do on the universities at a decent level, but maybe not at a level where industry, can do, but also in terms of connecting to real world problems, connecting to customers. And I think we have to be very realistic. I mean, I do not believe that, financial market optimization next year will benefit from using quantum computers. But nevertheless, it is kind of inspiring to see, people like, Marco, who's sort of building groups, building expertise in this, so these are basically our customers. They, they know what problems really need to be solved and kind of working through industry, working, with startups and with academic groups to try to sort of identify path forward. I think it's very exciting. And I hope that's what, ventures capitalists are sort of recognizing, but, that's hopefully this was.
If anyone else want to chime in, yes, Professor, come to the mic right there.
So, I mean, time scale plays a role, right? And different fields have different time scales. When I joined TI, I learned that there were 3 time scales. There was, and my customers were experimentalists that wanted to build devices, right? So their first time scale was minutes to seconds to run a simulation and get intuition on the screen right there and now. Then there was the lunchtime or overnight time scale. I'll put something in the computer and in the morning I have a result and I'm going to go in the lab and build it. And then there was the Gerhard, the geek time scale. I'll ask him a question and he says, I need a month. And by the time he comes back with an answer, the answer was irrelevant. And you can name it months, you can name it years, but those things exist. You have to have something in the near term that you need to deliver. And if you're in industry, you have that pressure that you actually, whatever you do, there must be an outcome. And I guess what made me successful at TI was I could build a software product that was serving both the academic need to be the geek, but also the immediate purpose of really designing something, right? And I don't know where the balance of that is in quantum computing, but there must be a balance, and industry drives that balance for sure.
Awesome. If any other panelists have something to add, if not, I actually do have a question in terms of stay grounded in realism amongst the hype. So we're coming to a stage where every actor from, perhaps your startups are growing and you're now hiring people from, you need circuit people, you need software people that may not have been, interacting with any quantum systems before. So what are some common communication misconceptions about quantum sciences, quantum mechanics, or just more technically quantum computing as a whole that you as experts in the field would like to refute, correct, or what's your usual elevator pitch as you're hiring people, as your groups expand, if anyone wants to pitch in on that? No? Oh, no, yeah, no, you're fine.
So okay, I do. Okay, so then first off, I mean, there are kind of multiple facets to this question, and I do think that this, certainly this kind of quantum industry, are at the point where they really benefit from influx of people of the type that you are saying, that the people who really are kind of experts in various engineering kind of subfields, which actually is needed to really build, truly functional systems, to basically graduate from university experiments to things which really work 24/7 and can be used, for example, on the cloud by customers, right? And, in that way, I do think that sort of educating this technical, professionals, in the field of quantum, I think is very important. And it is also very important on the other side, that for people who kind of build quantum machines, we have to start doing it, in a way which is kind of, professional. And this is, that's where we hope that will be a big boost eventually. But in terms of, how, where the field is, and how grounded, we are. I mean, we are, of course, by nature, should, are and should be optimistic, and, but at the same time, I do think that there are a lot of challenges. So balancing these two things is an important, consideration. But, the good news is, I would say, in the domain of scientific applications, quantum machines are already at the point where they can become, they became a tool of scientific discovery. This is it's already happened, right? And so far, the types of discoveries that, people make, are those related to understanding, complex physics of many body systems, understanding quantum materials, maybe eventually some applications to chemistry also could come along, but, they are not, what directly, banks, for example, sort of necessarily would, relate to, but, they could have important applications in sort of in other parts of industry, So this is where the field is, and extending these things into domain, which is more, kind of solving everyday general purpose problems. I think it's an important task, but again, this is more of a scientific problem, but, that's a,
I'm of course of this panel probably the person with the least direct industrial experience, but let me roll this up from the opposite direction. So we are with our quantum problems now at the point where we need real world input. So like what Misha just said, for example, we have a program on quantum chemistry, and of course our quantum chemistry is more like what you heard yesterday. How can we do quantum chemistry on a quantum computer? But for us, the important input is really from the people who do that every day. So we are actually talking to chemists who up to that point have absolutely no idea of quantum computing. And in fact, secretly sit at home in their offices and laugh about all of these people who want to do chemistry on a quantum computer, because to them what we can do sounds ludicrous so far. Also, some people who you really badly need to do good quantum is people who are excellent programmers. That was in the beginning not so much the case, but by now, I mean, even if you've no idea about a quantum computer, you can get in it pretty quickly if you are, at least on the theory side, if you are an excellent programmer. And I think this kind of reaching out and daring to go out in the world, making yourself honestly subject to being ridiculous. I have seen that quite often. And nevertheless persisting and seeing, okay, can we find common ground? Can we find some problems that you actually really so far cannot solve? And some problems that are really more in in our domain than in your domain. So this kind of dialogue and being able to have this dialogue and being willing to go into that and admitting to start with of your field, I really know nothing. Please educate me. And this, I think, goes very much both ways. And I found that industry or university, that's really where the most, one of the most important frontiers these days.
So I see you jumping up. There you go.
Thank you. So I see there is a lot of synergy between the industry and the academia. So definitely quantum is a scientific field right now. And that's actually very exciting because the industry, we collaborate with partners in the industry. We don't feel like we are competitors, but we are collaborators because we are doing science. So we publish our work. For example, it's kind of unusual. When I joined JP Morgan Chase, I remember I announced to the bank that I was going to publish my work. And they were like, publish it? Why do you want to let the community, the external world know our trade secrets? I said, they're not trade secrets. This is science. And I think it's very well understood now that in order for us to advance in this field, we have to let the community know, the scientific community know what we are doing. So the scientific community can expand our work, extend it, or give us feedback. That's one thing. And also the industry can, I think, as has been observed already, the industry can feed inputs to the, for example, to a startup, like letting a startup like QERA, for example, know what we need. And so the efforts of building a quantum computer can be improved perhaps by knowing that we need certain types of problems to be resolved. Now, we are excited to see that some problems already have a potential solution. So in the work that we're doing at JP Morgan, we have already built algorithms, say for portfolio optimization or derivative pricing or machine learning. Of course, we cannot use those algorithms in production, but the algorithms are there. So it's a very important thing. Over time, we keep those algorithms very well organized in our repositories. The code is very well written. I agree with the observation that software engineering is very important at this stage. We keep these algorithms up to date. So as the hardware evolves, we might tweak the algorithms to adapt themselves to the new hardware. And when eventually, a few years from now, quantum advantage becomes a reality, we will have the algorithms right there. So I think it's important to, this is maybe the subject of this panel, like the transition from science into business. It's important to have that target in mind.
Thanks. I think it maybe getting back to your question, you know, in fast moving fields, and I think particularly as, you know, the world is evolving to bring this tighter connection between industry, academia, and others in areas that are still at a very early stage of scientific discovery. You know, certainly we're seeing this really the popular press leading sometimes the scientific publications. So, you know, for all the students in the room, I think it's just really important, particularly in the quantum area, to ensure that you are balanced and watching the popular press, but also making sure that you're tracking the scientific publications, because there certainly have been some releases that perhaps were a bit premature, or you know, in fast-moving fields, maybe being a bit speculative and really how the outcome, how the very, very early results could drive, you know, very, very large transformational advances. So just understanding, you know, the work that needs to go on and making sure that we are reading the content in the right way.
So I think just checking the time, I'm going to start opening up to questions from the audience. If you have questions to start asking, I will take them and I'll fill up the space in between. Any more questions? So hands raised.
I think it's a more of a software versus hardware question, but I'll try to phrase it in the context of quantum computing. I think we all recognize that quantum computing is really important, and in the long scheme of things, it's going to have a very big impact. But in the shorter time, there's always this application and program or algorithm development which is happening, as well as the hardware updates and modifications which are happening. Is it something of a concern to people who are leading research labs or people who are overseeing fundings and research and so on and so forth, that there could be a point of discontinuity where your application development has happened, but hardware is lagging behind, like what we see in the industry or in conventional classical computers, so on and so forth? If it is a cause of concern, how do you guys plan to address it? And if it is not, what are your reasons for so? Thank you.
Thank you for this question. So I think I can provide the perspective of my team at JP Morgan Chase, because we, as I mentioned during my presentation this morning, we have access to 7 quantum computers from 7 different technology providers. So I think it's very important to monitor the quantum hardware ecosystem just to avoid the risk that you mentioned, which is like, what if the hardware evolves and we are not ready to catch up with that evolution? And we have embedded, so we have the full software stack of quantum computing implemented. We created almost like a product for quantum computing. It goes from like a cloud-based access that doesn't require any installation, including, you don't even have to install the libraries, you don't have to install the Python editor, and everything is pre-configured. So all the team members share the same Python environment. There are no inconsistencies between the results of 2 people executing a program. Then we have the application, the algorithm, and the circuit layers, and then access to the hardware through our stack. Now, at the circuit layer, we have embedded a compiler that allows us to recompile our circuits to different computers. So this again is done in order to prevent us from having to rewrite the code, and which is a very expensive activity. And so this way we don't fall behind. So I think by keeping in mind the fact that the evolution of the hardware is really fast at this point. Quantum companies are improving their computers often. Every few months there is a new release, new qubits, new characteristics, but also new companies are coming to the horizon, and it's important to have a flexible approach. So I think I can feel right now less concerned knowing that we have this solution in mind, because we're mitigating the risk that you have highlighted, which is actually a real risk.
Any panelists has more for looking good, right?
So kind of just to complement the answer. So I certainly, many of us kind of quantum computer builders are of opinion that at least in the near term, the kind of real breakthroughs, in terms of pushing the scale, system size, and, really testing algorithms will happen using this approach, which is sometimes called co-design, where you basically find clever tricks how to implement complex problem in systems which are limited in size to say a couple hundred qubits, limited also in depth, in circuit depth, and I mean, this is absolutely, and this is what is, we believe that's what it takes, it will take to really push this kind of frontier. And this is absolutely a challenge. And I guess you've maybe yesterday, in the presentation by Alex Kisling, you have seen an example of that. So it basically allows you to, test something like quantum optimization at scales which are orders of magnitude beyond what you can do sort of on fully programmable, kind of standard devices. And I think that's absolutely a challenge for, people like Marco, but I would say, for both, us and you guys, you should look at every challenge as an opportunity, right? I think that's really an opportunity to be creative and basically with good understanding of, how different hardware platforms work and good understanding of problems you want to solve, you can really make something special. So you can basically enable, I would say, big leaps in progress, and I think we will see many examples of that in the coming years,
If there's no other follow-up, any other question, any second questions from the audience? Yes, Mina.
Hi. There was some talk, and maybe I think this might be the right panel to ask this question. The first day of quantum school, there was some talk when I think, is that Professor Chris Monroe's talk? IonQ. There was some discussion on which quantum computer will win out and how in the silicon classical computing era, somebody decided that we're going to do the classical computers on silica and moved ahead with it. And that's why we have silica-based quantum classical computers now. Is there any thoughts on whether there might be use for each type of quantum hardware for a specific type of applications? Or are we only looking at universal quantum computing for every type of hardware and seeing which hardware does that best and going forth with that? Are there any thoughts on that?
I'll try to give an answer, but I think I have people that are really more qualified than myself. So I think actually there can be actually a great opportunity for hardware specific computers. For problem specific hardware in a sense. So hardware that lends itself better to certain problems than other. So I would like to actually suggest to Mikhail gives an answer here because the QERA computer is particularly suitable for optimization problems.
I completely agree, and it's absolutely will be true in the near term, but even in a longer term, as we start, thinking about bigger devices which will utilize, things like error correction, absolutely there will be hardware specific approaches. And in fact, even let's say from the engineering point of view, there is great opportunity in terms of how you optimize, even like an implementation, given a platform, how to compile these, algorithms, which and do it in a way which is efficient. I think in the next decade we will see a lot of examples of this type.
I have more question to Marco as well and a comment. So when I got started with computing, it was on 8 kilobyte on a Commodore, and to get any performance out, you would actually program it in assembly, and right, you were on the machine, and a different machine, you write a different assembly code. There was no compilers that would actually do a good job. I mean, there was BASIC, and it was slow, and it would run everywhere. So maybe it's similar, right? You say you have a compiler, but all the compilers I know for the NEMO stuff we worked on, we write code optimized for a certain platform. The compilers in general suck. I mean, they compile a working code, but.
So the compilers that we are using are actually, the compiler that we're using is actually something that is actually hardware specific. So it's not like a technology specific. It's not that we are compiling a circuit to work on a superconducting qubit computer versus a ion trap or like a Rydberg atom. It's just specific to particular hardware because there are certain operations that only certain computers support. So the optimization is at the level of the hardware.
Very brief comment. After, don't know, 80 years of classical computers, which were, as we just heard, very kind of hardware specific to start with and try to be more and more platform agnostic. Please do remember that we are now at the point where there are CPUs and GPUs, and everybody who does some serious computing writes their code to either the one or the other. And I mean, there are other examples, but I think this division of hardware and software, this will probably go up and down, but it will never be completely divided up, I think. That would be very surprising.
Professor Kais has a question.
I mean, maybe this is not so related, but we all assume that the quantum theory is the correct theory because so far we don't have any experimental results that contradict the theory. Now with this new machine, is there any plan to or future plans to test the theory itself?
Anyone ready to take up that? So Luke, and I think your eyes sparkle.
No, that's a great question. So, look, I would be delighted as if an outcome of this exercise, which we are doing now, of the building big machines, we eventually will find the reasons why, big quantum machines cannot be built. The kind of fundamental physical reasons. So that would be an amazing, scientific discoveries. I would say it's highly unlikely. We do not see any indications of that so far, but that would be an amazing scientific, discovery, if it happens.
So, you know that in secret, of course, we plan these kind of, gravitational wave computers and so on. I mean, I think it's a little hard to ask. Can you disprove the fact that this computer should work on this computer? But I'm pretty sure that what will happen is that it will include not just abstract quantum theory, but that as the evolution of, for example, unification of forces and theories happens, that this will be eventually involved as well.
Just to kind of add as an example, people who are building, cutting edge modern atomic clocks, there is actually a limit which one could foresee, which would, limit the clock precision, which is associated with basically fluctuations of the gravitational background. I mean, this is a limit which is, at a ridiculous clock precision level, but nevertheless, there will be a limit to how we can define time. And it is not unlikely that this limit will be reached within next decade or two. So, I mean, things like this absolutely, are present. I mean, we don't believe right now that this will pose a limit to building quantum computers, but this is the kind of, you pull and you push, you always discover new things. Right?
Any last questions? And on that note, we're perfectly on time. So if we would like to take a moment to thank all our panelists here. You'll be hearing from 2 more of them this afternoon. If I'm sure all of them are receptive to hearing from you. If you think of any follow-up questions, my name is Morris. We have Professor Lukin, Professor Yellen, Dr. Petoya, Dr. Klimek, Maria, Dr. Meyer here. Can we give them a round of applause, please? Thank you. Thank you.
Great moderator.
That's right. Ethan's going to introduce.
All right. Yep. Hello? Nope. They can't hear me yet. Can y'all hear me? No one can hear me because I'm silent. People on the live stream should be able to hear me though. All right. Hello? Are we good? No, maybe. Yep. Hello? Ah, no. Yeah. Hello? Gain's all funky. All right. Good morning. Good afternoon. I always say good morning, so I forget sometimes. It's my pleasure this morning to introduce Gerhard Klemek, formerly of Texas Instruments and NASA JPL Caltech. Professor Klemek developed models of nanoelectric devices, genetic algorithm-based optimization, and image processing. NEMO, the nanoelectric modeling software built in his research group, established the state-of-the-art in atomistic quantum transport modeling. He helped create nanohub.org, which now serves over 2 million users and published over 525 printed scientific articles. Please join me in welcoming Professor Klemek.
Do I need to move somewhere? Where I go? Can you hear me now? Is that better? All right. All right, so I'm going to try to split my time between nanoelectronic modeling, quantum transport modeling, and then an overview of NanoHub and how we measure impact. The first part of the talk is really inspired by somebody that called me a while ago and said, what's the future of modeling? And where are we going with these devices and what problems need to be solved? And there were a bunch of people advising this Institute of Defense Analytics. So they wanted to hear part of that. So I took this presentation from there. And my response to him was sort of, well, we're at CMOS, we're at the end of the road. And I know why and how, and I can describe why and how. And all I can do is open a can of worms. So he said, okay, give the talk. Cans of worms are fine. Okay. Not good. Let me walk up there while I advance and change my batteries. So the key element is, of course, it's kind of hard to predict the future, especially when you don't know much about it. So what I'd try to do is then really give you a perspective on decisions that were made to model these quantum devices in the field and what came out of it. So let me try to do that then. All right, battery works again. All right, so what I have is an intuition of what happened over the last 25 years of modeling quantum transport. And just to give you a preview, today's transistors are designed in full quantum transport with quantum transport simulation out of equilibrium. That's quite far away from where we were a while ago. And how did we get there? There was certain goals and strategies and what challenges were picked on the way. So I'm going to try to highlight that. And the key element is really going in modeling beyond just a specific device, but really building up a framework that can be used in many different devices, and that these approaches are transferable to you just don't write a code and then a paper and a code and a paper, but you really build something that can build up. So the idea there is really, why are we doing this? We really want to do quantitatively and qualitatively guide experiments and really understand them and really work with experimentalists. But we also wanted to design and engineer real devices and do that in the same framework, in the same modeling setting. And we didn't just want to be descriptive, like fitting parameters and that in a very narrow range we can guide, but really be fundamental. So we can really guide experiments from physical concepts, not just from engineering fitting. And these devices shouldn't be stick diagrams. They should be realistically extended devices that have contacts, that have doping, that have electrostatic potentials and irregularities. And these things should transfer from one problem to the next, not just one custom tool for any given problem. So what that really meant was that you have to have multi-physics and multi-scale segmentations in the same code to really bring it all together and partition your device. You have to be smart about your basis sets, just like when you do communications and signal processing, you choose your basis set wisely in order to have good outcomes that are scalable. And you should be able to compute something in time. I mentioned on the panel, right? There's different time scales of delivering results. So you have to balance compute times and accuracies of the models, et cetera. And ultimately, it needs to be usable and accessible to experimentalists. That was a key element to really give experimentalists a tool that they can design their devices and not just me, the theorist that designs their devices. So to me, these are goals that are going beyond a single device or a single problem setting. And to me, that's the frontier of modeling. And it has been for a while. So I want to home in a little bit on the frontiers of modeling in industry. And I want to highlight that for the last, well, until about 6-7 years ago, the major workhorse to design any transistor is actually drift diffusion. It's highly calibrated. It's really macroscopic transport. That's what we teach in semiconductor devices. People in the 90s developed ballistic transport with Monte Carlo tools. But when I went to grad school, early 90s, it was not clear what formalism you should use if you really want to look at quantum transport, where you have atomistic dimensions and where quantum problems are important. And in physics, typically, what's being taught even in grad school is equilibrium. Everything is in equilibrium. But we wanted to do things where we have a quantum mechanical Hamiltonian and it's out of equilibrium, where we really shuttle electrons through the system. It's an open system, out of equilibrium, open boundary conditions. This is non-Hermitian. And really, the mechanism that emerged was the non-equilibrium green function formalism. So at the time, that was not clear. Today, that is the standard methodology in the field of quantum transport for electronic devices. And you can rederive Boltzmann, you can rederive drift diffusion out of that. But what it really allows you to do is have a unified model. If you can describe a Hamiltonian of a system, you can open system, you can really model any of these devices that I'm sketching, a chunk of silicon, a carbon nanotube, a molecule. Really, that's the method of choice if you really want to transport electrons through a system. All right. So this is a chart on the right from my friend Mark Stedler, who is at TI. He and I were actually office mates here at Purdue. He's now working there in the TCAT group. He's a vice president leading this group over there. And he had this talk in 2019 and reviewed quantum transport, actually simulation, at Intel. And he has these two lines, 1994 and then 2019. And to give you a perspective, a 2019 research-based transistor, TSMC 5 nanometer presented at the same conference. That is a transistor that is vertical, it's a FinFET.
It is 6 nanometers wide. It's about 48 atoms. That is small, very small, countable number of atoms. And I want to compare that to the 1994 transistor, where everything there was in continuum. You didn't even consider the existence of atoms in a system like that. Versus here, you have to do quantum transport. You have to do ab initio calculations, and you see that box in blue, it says NEGF, non-equilibrium green function formalism, integrated in an industrial pipeline. So going back here, 94, that was the device that was being produced and modeled. Meanwhile, there's another thing that went on in 1994. There was a device, the first nanoelectronic research group in existence in the United States was actually at Texas Instruments. And they looked at devices like these, double barrier structures, and here is an STM. That at the time, the STMs are really novel. We had to beg and plead to have somebody actually examine our devices like this. This was a resonant tunneling diode. And if you just turn it slightly, you can kind of see at least a visual resemblance between these two materials and these two devices. And why am I showing you this? It's one of my, number one, it's my old friend. It's a resonant tunneling diode. Here's an animation taken from NanoHub where you can visualize an RTD. You apply a bias, you pull the central resonance into the sea of electrons, current rises, current drops when you're out of the bandpass filter. That was the device, the quantum device of the future in the 90s. It was operating at room temperature. That was the only real quantum electronic device operating at room temperature. The goal of this device was to reduce this so-called valley current, the current when it's supposed to be off, and to increase the peak of the current. So to increase the peak to valley ratio. And I'm showing you here sort of a curve out of a paper from some research group. And if you just write down the layer structure like this of what they've grown, it looks pretty harmless. But if you really look at it on a computer and visualize it, you have a 15 nanometer central device, 555 nanometers, embedded in some 500 nanometer contacts. So is it a 15 nanometer device or is it a 500 nanometer device? The key element is actually a 500 nanometer device, and you have to model the whole thing in order to get any reasonable result out. So the state of the art at the time when we started was like, oh, let me highlight here. In this curve, you didn't see this little wiggle. I'll explain it to you in a minute. So state of the art at the time was, okay, we'll attach a flat band boundary condition to the end of the device, and we're going to shoot electrons in there with a scattering experiment. You get the blue curve. Or you just throw away the contacts completely and inject directly at the barriers, and you get the green curve. And this is on a log-log scale. Your IV curves look completely different, and you have to plot them on a log-log scale in voltage and in current to even put them on the same scale. That is how bad the state of the art was in predicting a device like this. And what happened is we developed a methodology where you can segment the device in the central region and a contact region, and you get something of this reddish curve that's laid in there that actually then has some details in the structure, and we can actually get the current voltage characteristic right. And this little wiggle in the structure really comes from the extended contact. It actually has quantum states in it. You actually have multiple coupled quantum well. Your central resonant diode really filters the states that are in the emitter. So you have an energetic filter that really is dominating this device. All right. And there's 3 curves shown. One is in a single effective mass model. I talk about that. And the other 2 are in a full band model. And I'll tell you why that is needed. So the key element is when I started, everybody said this valley current is from scattering. Everybody was working from a physics perspective. Scattering was a cool thing to examine. Phonon scattering, phonon echoes, all those kind of things. It turns out to be completely wrong. It's really a fundamental fermionic emission problem, and I'll show you why. So obviously in this audience, I don't have to describe how you get bands in a solid, but I want to remind you that crystals have symmetries. Also, the basis states that we have symmetries. Nothing in these systems is really spherically symmetric. So the question is really, what does free propagation mean? And normally in electrical engineering, we write down an ansatz for the Schrödinger equation. We get some spaghetti diagrams of a dispersion. And that the first thing engineers do is they say, well, let me just forget about all these bands and just put in parabolas. And that's good. And I'm going to do all my transport calculation with drift diffusion, Boltzmann transport, and even at the time, any quantum transport simulator would have 2 bands or 1 band. That's it, effective mass. Because that's what's being taught in basic quantum mechanics. You just have a free particle with 1 effective mass. And I want to assert that that fails when you actually have real heterostructures that have material variations on the nanometer scale. It is absolutely critical that you do not take that step. So the essence is I can explain a Mickey Mouse stick diagram device like this with a double barrier structure, but in order to get experimental data right, I actually have to put the atoms back with their atomic potentials, with basis states. And the question you really have is, did I have now a new material or a new device? Because those things are actually related. You created a structure that doesn't exist in nature. It's on variations of 5 nanometer. You change the material properties of the whole thing. And if you throw that out in the beginning, you're not going to get to a final result. Now, the multiband effect that I like to share with you is a very simple one. There's 2 actually. So here's your man-made resonator, your double barrier structure, and there's the dispersion on the right. The ground state of that resonator is at pi over L. I can grab a pi over L K0 and I can map it into a ground state there. I can double my, for the second state to get a 2 pi over L, I can map it and I get a ground state. Now, if your real material is actually not parabolic, but more like the real materials that we deal with, indium arsenide, et cetera, they're non-parabolic to a very high degree. So your ground state might roughly be at the same energy, but your excited state is a couple of kT lower, 100 millielectron volt lower or more. That's a huge difference. That is e to the -4 or e to the +4 difference in the current you're going to get out. It's a huge difference. So while everybody was doing effective mass calculations, they couldn't get the valley current right, and that's why they said it must be scattering. So, and it was so bad that you have to put it on a log scale. The valley current was completely off and completely wrong. And anybody doing effective mass was stumbling over the same thing. Now, you can ask, well, why is the peak still wrong? And that's the second effect. So when you inject carriers through barriers, you have these evanescent waves you calculate. And if you're in a single band model, you have a parabolic dispersion in the imaginary plane as well. And you get a decay rate. So, but if you connect the bands together properly, your evanescent wave in the band gap is actually much, much smaller. So these barriers are actually much more transparent than you think they are. Much more transparent to the point that the current that flows can be actually orders of magnitude larger. In this case, it's just a factor of 5 or so. So it's actually very important to know about complex dispersions in these materials, because we design devices in the energy range of tens of millectron volt. That's really critical. All right, and we didn't just do that for one device, but we built hundreds of devices experimentally. And the real crown jewel at the time was we proved to the experimentalists that they are consistently off by 2 monolayers in their design of the device. They thought they grow a certain layer stack, and they were always off by 2 monolayers. So they actually adjusted their growth recipes because the theory was actually predicting it well, and we broke it apart. Now, why do I care about these resonant tunneling diodes? I kind of don't anymore, but I want to draw to your attention that these things look rather similar in their dispersions and in their electronic behavior to what I would call modern FinFETs. You just turn this thing sideways, and all of the band structure effects are going to be there. The current flow direction is different, but the fundamental science of how to treat electronic structure in a device that's 5 nanometers must be done in this tight binding mechanism or in a methodology that's similar. All right, so what's common here? In this device, it's out of equilibrium. We segmented it off into two domains and two equilibrium domains that are fully quantum mechanical. and a non-equilibrium region. This partitioning of the device was the key element to actually run something at a decent time. And I would argue that even if your scattering is really important here in these notches, we would have never had the compute power to calculate scattering properly. So scattering actually turned out not to be important in the central device. It's actually incredibly important in the contacts. All right, so what else can you then do? You can also partition the device and actually look at contacts that are not perfectly ordered. If you look at most quantum transport simulations or any quantum simulations at all, you assume some perfect contacts, but they're not. They're either disordered, they're an alloy, or they have other doping in it. I mean, they're never just perfect wires that are attached and run to infinity. So you really have to tackle that well. So we can do that now. You can also inject, like in tunneling transistors, out of complicated states. You can also string together many quantum wells and calculate a laser or an LED device on doing quantum transport in a really complex structure like that. All right. So it's really the partitioning between strong scattering and weak scattering in a device like that when you have almost thermalization of these quantum states. But you need to know where the quantum states are and how they're occupied. All right, let me get to the smart choices of basis sets here. This is what we typically do. We either go to experiments to get the right gaps and masses, or we try to resort to empirical tight bind, to ab initio calculations and map them to tight binding. The issue is really that most ab initio codes are not out of equilibrium. They're all in equilibrium. And most ab initio codes actually use plane waves. Well, if you have a heterostructure and you know a little bit about Fourier transforms, a heterostructure with a step function will have an infinite amount of k points that you need to resolve that thing. It's a bad choice. So plane waves for finite size heterostructures is a fundamentally bad choice. You want a local orbital. You want to look at the chemists. They know about local orbitals. The physicists don't, in general. So you need to change your view of the world. And so I don't want to have infinite waves because my computers are not infinite if I want to get a decent accuracy. And then you need to put other things together like positioning of the atoms and strain, and I'll highlight some of this. So we in a variety of structures, self-assembled quantum dots and nanowire strain is actually very important, and you need to calculate it as an extended phenomenon. So you might have a couple million atoms, 10 to 15 or even 50 million atoms. And just to give you an idea how important that can be or what that might mean, if you take a chunk of indium gallium arsenide and you look at experimental data and X-ray data and you look at the bonds of indium arsenide and gallium arsenide, you actually find a bimodal distribution. There is this black line here is actually from experiments. So the gallium will put the arsenide closer. The indium will push the arsenide further away. So it's actually very disordered. This thing is not, strictly speaking, a crystal. And if you have a model that can represent this material well, you would have a distribution around here, and you would roughly get the experimental data. And this is the model we use to really describe an alloy, a disordered alloy that is disordered atom by atom. So if you do that, you can then have a structure, and then you can calculate quantum mechanical states. You can have electric fields, etc. I'll show you a result of an optical quantum dot. And then you can do more electrical things like electrostatics and Coulomb blockade and other things in devices like this. So here's an example of an optical quantum dot where strain is actually important. The goal here was to tune the optical emission to roughly 1,500 1.5 micrometer, 1,500 nanometers by changing the capping layer on these quantum dots and really tune the emission of these quantum dots. And this is one of my first results here at Purdue when I came back from JPL, and the student walked in and said, "I'm overlapping experiment, let's publish." Then it took us about a half a year to figure out why are we overlaying experiments and why does that make sense and why is it so non-linear. And it turns out this capping layer actually changes ever so slightly the shape and the structure of this quantum dot. It squeezes in different directions in a different way. And that gets you this nonlinearity. And it came out of, for us for free out of the simulation, but we still had to understand it. So it's actually a result I rather like, because we didn't quite understand why the computer said it, but it came out, and then we had to develop auxiliary models to extract it. So you can do it. And remember, this is now 9 million atoms electronic strain relaxation and 2 million atoms electronic structure calculation. There is no other tool out there that can do that, not even today. It's a very huge electronic structure calculation for a semiconductor. All right, then roughly the same time in 2008, we began a collaboration with people that looked at effects in FinFETs. So this was an experimental FinFET that came out of a IMEC in Belgium, that's their national lab. And a physicist I was working with did what physicists do. They cooled it down, right, to 4 Kelvin, not room temperature operation. And they see these crazy spikes in the current voltage characteristics. And they can then map it to what's called Coulomb diamond. And I'll show you what we did at the time then with them is we can identify that these structures have actually arsenide impurities in it, not phosphorus. We can pinpoint where they are and how many there are in individual devices, because each device had like a fingerprint. So you can do metrology in a structure like this. And then we began a collaboration with people in Sydney, where Michelle Simmons built structures with single phosphor impurities. And I'll talk a little bit about that here. So the questions were, if you build a wire that's 1 atom tall and 4 atoms wide and is metallic, is it still ohmic? Can you get conduction out of such a structure? And then can you get tunneling into a single phosphor impurity? And is it really 1 phosphor atom? And why would a single phosphor atom actually hold 2 electrons? Because that would be unusual, right? It's a very shallow donor. Why would a single phosphor impurity hold 2 electrons? And can we exchange it tune it to exchange qubits? So just for the young folks here that don't know what Coulomb blockade is, so here's a simple way of looking at this. It's basically my friend resonant tunneling diode, but it's a physical dot, very small. It can hold 1 electron at a given time. So you apply a bias, you have a gate bias, and then you allow electrons to flow through. So you open 1 channel, you get 1 quantum of conductance. If you apply a higher gate voltage, you basically trap an electron, and it sits there, and the current goes down. There's no current going left or right. And if you increase the gate bias further, you open the 2nd channel, and a 2nd electron can flow. And you go down, then the current stops. And it's experimentally much easier to measure differentials. So you actually measure the conductance differentials, you get spikes. And depending what your source drain voltage is, you get different spots in a diagram like this. And if you change different gate voltages and biases, you get something that looks like a Coulomb or like a diamond. And it's called a Coulomb diamond. And basically, you have fields in which there's no electron or 1 electron in the structure. And at the hash mark, that is where conductance changes. All right, so that's cool, right? But if somebody actually builds a device that looks like this, there's a single phosphor impurity here sitting in the middle. There's metallic wires leading up to it at 9 nanometer distance or 10. And these wires are literally 1 atom tall. That's a pretty cool small nano device. That is really nano at its limit, and it's fully quantum. And they measure these diamonds, and we wanted to explain what these Coulomb diamonds really are. Experimentally, what Michelle does is she does what one would call STM lithography with hydrogen passivation. So they dig little holes in a hydrogen passivated surface with an STM. They expose it to phosphine, and the phosphor begins to embed itself on the surface, and then they cap it. So they can make very, very thin layers of very highly dense phosphor atoms. So you can imagine a sheet like this. You can also imagine that you can lithography make wires, and then you can also imagine between the wires, you might have a single phosphor atom that sits embedded in silicon. And the questions that emerged were, is this sheet here really metallic? And how many states are available? Is this nanowire really ohmic? Can it really conduct current? And if we build a device like that, can we really measure and simulate quantum transport through a single phosphor atom? So in a calculation like this, DFT can touch it. It needs about 1,000 atoms. But if you ever wanted to study anything with disorder, even the smaller structure here, you go into 1,000, 10,000 atoms to look at anything that has disorder. And if you're worried about or interested in silicon band structure, because we're embedding all of this in silicon, so silicon has these 6 valleys. If you project the 3D Brillouin zone down into 2 dimensions, you basically have this 2-dimensional Brillouin zone. And in the center, these gray valleys project down into the gamma point, and they split, and that's called valley splitting. Now, there's a lot of people that worry about valley splitting, and they started out with effective masses, and they put the valley splitting parameter in as a coefficient. And after the fact fitting, we can get that from our original band structure by choosing the bases right. And then if we do this self-consistently, we can actually calculate the Fermi level, and there's a bunch of states at the Fermi level that can conduct electricity. So this wire turns out to be indeed ohmic. The interesting thing is if you look at the sheet and look at a different direction, the projection is quite different, but even in that direction, you do have filling up to a Fermi level, and you have states at the Fermi level that can conduct. And if you ever want to learn about band structure in thin silicon bodies, you can go on NanoHub, launch this tool called Band Structure Lab. You can put in silicon, you can examine band structure, etc. So it's quite powerful. Many people have done so. There's some on the NEMO tools, it's over 30,000 users now that use NEMO on NanoHub. Now, I mentioned we wanted to look at wires. That calculation, you need a much larger unit cell. It's about 30,000 atoms, and that got us to this science paper. But really, if you want to do this single electron calculation, you need to be able to have at least 1 million atoms in your simulation domain. And again, that's something DFT cannot touch. It can't even get close to that. All right, so how do you model a device like this? You actually have to have a very large domain where you have all of these contacts and all of the electrostatics. It's 100 by 50 by 10 nanometers. It's huge. It's a huge simulation domain to just capture one lonely phosphor atom that's embedded in the middle. But you need the electrostatics to properly do the gating. So when you do the electrostatics right, you get a potential that looks like this. So you have source and drain, and with the representation of these atomistic wires, and here's the gate, left and right, and we can take cuts through the gate in different directions, and that gets you an idea what the potential looks like. So this is a cut from gate to gate on the left, and in the middle, there's the source to drain cut. So the electrostatic potential is actually spatially varying in a wide degree. It varies over a domain of 100 nanometers plus and 50 nanometers plus. And you need to be pretty accurate to be looking at this state here to get the occupation of these states. So here is actually the ground state of this single phosphor atom is actually sitting above the Fermi level. So this quantum dot is actually empty. There's no electrons sitting in it. So that's why the Coulomb diamond starts out with an empty set, not with an occupied set. And now let's look at what happens under bias. So if I have this gate bias now, I'm basically dragging the state down, and until it hits the Fermi level, that's when I get a conductance peak. That's when I can start to conduct. And I jump up in energy due to Coulomb blockade, and then I drag the next state down until I hit the Fermi level again. And those energy scales define the Coulomb diamond in the system. So these are the energies that we simulate, and these are the energies that come out in the experiment. And there's not much free parameter fussing around. All of these wires, all of these electrostatics are literally just quote unquote simple electrostatics with quantum mechanical calculations as to where are the states. So quite powerful. And so we also then, by the way, can explain why a single phosphor impurity can hold two electrons, because the energy is pushed up, right? So you basically create the electrostatics around the structure, creates another potential well. So you can actually shuffle more electrons into it than what you normally would have gotten out of a stick diagram. All right, so here's this potential. And then the question is, well, you talked about this Coulomb diamond, right? So, but what about all this other junk here? So I know somebody that worked on Coulomb blockade a long time ago. And I started to look at quantum states in a quantum dot like this, but also modes in the wires that are going to be different, and gating and mixing of modes and asymmetries. So what turns out, we can basically calculate a Coulomb diamond based on that theory some 20 years later that actually makes sense. And they come from the following. So the central Coulomb diamond is dominated by these states that I explained here in red and green. But then there's excited states. A true phosphor impurity, actually, it doesn't just have a ground state, it has a set of excited states. And they will result in additional lines next to the Coulomb diamond. And then there's also the states in the wire, meaning the wire is not a homogeneous density of states. You actually, in your central filter, you actually filter what's in the wire. And that gives you all this crud and this hash mark stuff here in the middle of the Coulomb diamond. And you can't get rid of it because your wires have dispersions. Your wires have electronic structure. All right, so that's kind of this stuff. But what really is the key message here, in order to do this, we really had to have a multi-scale approach where you model the contacts separately, where you model the electrostatic potential over hundreds of nanometers. You string it together, you do a calculation of charge filling with a single electron, two electrons, and then you stick it into a rate equation formalism that you can do quantum transport like this. And stringing all of this together got us to the publications that we got. So the key element here is really that it's multi-physics, multi-scale, and partitioning and segmentations in smart ways, but really tying it together. And lastly, on this segment, what I want to talk about is compute scaling. So some of these calculations, especially in non-equilibrium green function calculations, can run a long time. In 2011, we could keep the biggest supercomputer in the United States busy for a couple of hours. And that meant if you run for about an hour on this machine that has 221,000 cores, so that's roughly 100,000 pizza boxes like this strung together in a room that has massive cooling. That was the Jaguar machine at Oak Ridge. Or you can run on this for 25 years on a single CPU. That gives you an idea how intensive these calculations can be. And at the time, and it's still true now, NeMo is one of the 5 codes that can actually run full-fledged on that whole machine or on a machine like that. Most other codes peter out at 10,000 or 50,000 cores, and they just don't perform. All right, so now I want to get into another boat and talking about usability and access. To really make this useful, you got to put it into people's hands. You got to make it useful. And that has been sort of another passion of mine that I've been pursuing. So I want to talk a little bit about this nano-up stuff. So this NeMo code has a bunch of apps. And I came back to Purdue actually to help build NanoHub up to an infrastructure that can be used globally. I could build my NeMo code at JPL, but I didn't have a venue to really disseminate it and to reach more people. So it was good for me, but I think it could be also good for a larger audience. So I'll go in there in a minute. I actually forgot I had this slide in here. So I want to show you that there were several generations of this NeMo code. We started out from one-dimensional system where we strung together, say, 1,000 atoms in one string. And we made it in 3D, but no transport. Couldn't afford it, couldn't fit it. Those were running on the first Beowulf computers. And then two students of mine actually parallelized it very well, and we got this version. Then Mathieu Lerosier came to the group, and he began 3D transport on a relatively small system and only in zinc blended, only one crystal type structure. And then this NeMo 5 version really can do any very large systems. It can do a variety of carriers, not just electrons, and it scales well. And the impact, I mean, all these codes have 100,000 lines to 500,000 lines of code. These are not things you just build for one PhD thesis, right? These are modularized. They can do a lot of things. This was the first NEGF tool that was really run in industry. And it was predictive. This tool was the first million atom electronic structure code. The parallelization and doing this with electrostatics really got us to the single phosphor piece. This code was the first petascale engineering code. All the other codes that ran at the petascale are science codes, designed for specific problems, not a specific tool. And then this code is now running at Intel. I'll talk about it, and it's being commercialized with Silvaco. So it's these first four were kind of written by a few individuals and small teams. The NeMo 5 group had at some point some 40, 35 people working on it in a almost industrial size group, right? So what does Intel do? So I started out from this paper by Mark Stettler. So they now in 2019 publicly state that they're using this code. It started in 2009 by industrial engagement. In 2015, they actually bought a dedicated supercomputer inside Intel to run NeMo, which was kind of cool. It was also kind of funny. They didn't want to run on an external supercomputer that might have had AMD processors on it, right? It would have been really bad publicity, right? In 2019, they integrate this or announced the NeMo integration. And at that time, they had designed now at least 2 transistor generations with it. So it's kind of cool that academic code can really develop and really make impact on industry as well. So what's next? So I mentioned this stuff should be transferable. So we've worked for a long time, and I'm not going to highlight that, really on the replacement switch. What is not coming after CMOS? We worked on tunnel FETs. There's something called negative capacitance FETs. They might have a chance. But really, this field is petering out. It's really CMOS is it. We're there. And in that sense, I feel it's like steel or airplanes, where improvements will be very, very small. They won't be big anymore. It's marginal improvements. So there's still a lot of fundamental research that's curiosity driven, but there's now also more application device research driven, application driven device research. And really our methods can transition into other fields, and I want to highlight that. And then I want to conclude with NeMo, NanoHub type stuff, where we really put this into users' hands and maybe can drive it with machine learning. So there's certainly curiosity-driven work here on 2D material. I highlight that a little bit here. We have groups at Purdue that look at 2D materials for a variety of applications. It's really connecting materials to devices to circuits. There is something called back end of line, BEOL, where you build devices on top of the existing high performance transistors. So that's going on. It's 3D integration. That's certainly coming. And there's lots of stuff going on. There's still a lot of work in MEMS and making MEMS more sensitive and better. And really the key element is now, in my head at least, and that is what a colleague of mine is pursuing, is really introducing what we've learned in these open systems to material science and chemistry. So Tillman qubit, let me highlight this here real quick. So I do this actually in my graduate class. This is my good friend resonant tunneling diode. I teach how to calculate a transmission through that, and I also teach particle in a box, right? And there the students can see that the eigenstates in a closed system are quite different from the eigenstates in an open system. And that is a key element to actually understanding open systems and doing transport in it. And so these systems are non-Hermitian. And let me remind you again that most DFT, density functional codes, and ab initio codes have periodic systems. They're not finite. My devices are all finite. They're disordered and they're non-periodic. And really transferring this kind of methodology of what we learned in 25 years in quantum devices into chemistry is actually a great way to fertilize other areas and to work with other areas. And that is what Tillman is doing. He is a faculty member here at Purdue. He used to be the key person in my group in NEMO 5 and develops NEMO 5, and he's taking it over and looking at material science type problems where systems are disordered. And finally, now I want to get to this piece of NanoHub. So I'm switching gears, but I'm going to reconnect it to this nano modeling in a minute. So here you see an animation of NanoHub users on, I think it's old, 2016 or so. But this thing doesn't sleep. Like, people in the world are looking at nanotechnology, nanoelectronics. We do a lot of semiconductor type stuff on the site. To give you a perspective, this is a picture of an annual NanoHub user view. So basically, where there is people in the world interested in science and nanotechnology, they're coming to NanoHub, right? If there's a civilization with enough power to light up the night sky, they seem to be also going on NanoHub to look at this site. Now, what was the inspiration? The inspiration, in a way, was as follows. The United States invests over $2 billion in research, in nano research. And a lot of software, a lot of results are being, and data is being generated. But in general, this stuff is not accessible. You can't even reproduce it most of the time. And therefore, we created NanoHub to really enable these resources to be usable by other people, to really convert research results, research insights, and research software and make them useful to a broader population. So to give you an idea, this is NanoHub in a nutshell. There's over 700 apps now. There's over 7,000 lectures and tutorials. There's 170 courses plus. We have about over 2 million users. It's operational 24/7. And we measure impact by impacting research. And I'll talk about that. We have papers that cite us. I'll summarize that a little later. And the key message of the slide I wanted to send is, we were told early on, nobody will use a research code in a classroom. People were wrong. We can prove it now. We were told nobody else will use your research code for their own research. They were wrong. We can prove it. Those are shifts in expectations of what people expect. And that's called a paradigm shift. When people change their perspective, that is, or the underlying assumption. So we did achieve that. And NanoHub apps are actually now listed in the Web of Science as a proper publication. It has a DOI, it's listed. It's a new type of publication. That was unimaginable 15 years ago. All right. And the key element to our success, I think, had been to go beyond specialized capabilities. And what I mean by that is, I show it in a very simple picture. Look at this beautiful invention, the first car. And it was quite sophisticated, right? But it had a couple of problems. You had to be pretty rich to have one, and rich enough to actually have a driver. And the driver was also likely the mechanic that fixes it, and the gasoline fetcher when you ran out of gas. So a very specialized vehicle. But what really brought a difference there to this world was to make it usable and accessible. That was truly impact, making it cheap enough, reliable enough that somebody else that wasn't rich could also use it. We had something similar like this. Most of you are too young to remember the picture with Bill Gates, right? Tablet PCs are cool. You had to read a 200-page manual to use it for the first time. An iPad is used by 2-year-olds. What's the reading ability of 2-year-olds? There's certainly no 200-page manual. It's the usability. And I remember when these iPads came out, same with the iPhone, people said, ARM processor, not powerful, we have much more powerful phones, or my tablet PC is much more powerful. Sure, true, but it's not usable. So then who cares? So similar, we have all these tools. NEMO is in that category too. Abinet, games, lamps. If you're in material science, these words mean something to you. And these things are really like this car. You know, the car is the supercomputer that these things run on. This is me, the fat professor, telling graduate students what to do. That's the grad students with an X term on their fingertip. Things didn't change that way, okay? So what NanoHub did is we made it such that we had apps that wrap around these complicated things and make them useful. And we came up with apps in 2004, 2005. They came alive in 2006, end of 2005. We saw a dramatic growth in NanoHub users once we appified it. iPhone came out with apps in 2007. We were before the iPhone with the concept of apps. For science, for sure. All right, and then the NEMO stuff runs in there as well. And I want to highlight usability again. So here is a tool that we have on NanoHub in an accrued form. So you have to, this is Padre. It's actually a Fortran code we were donated by Bell Labs. That code actually designed transistors for Bell Labs, an honest to goodness industrial strength tool. In order to operate it, you have to speak its gobbledygook language, okay? And learn about meshing and all that. All right, so we put that on, we put an interface, at least the results you can visualize nicely. But then we did this. We'd take the same code, embed it under an app, and you can design a simple transistor with its various geometries. And we took that and did that for couple of apps, for MOSFETs, for multi-gate FETs, MOS capacitors, PN junctions, bipolar junction transistors, drift diffusion. If you took my 606 class, you know all about it, unless you failed, right? All right, but look at the numbers, 2010 data, 900 users on the Geek app, 6,000 users on the app-based user base. Looking 9 years ahead, 40,000 users in these apps versus some 2,500. The number of people that have to learn about MOSFETs, PN junctions, those kind of things is much, much larger than the people that need to truly design them and need to speak those languages. So making science tools available to undergrads, grad students in a simple way where you only have 20 parameters, 10 parameters is way more powerful in reaching and educating people than just making this whole Formula One car available. Most people need a Volkswagen or like. All right, I can also measure this in a different way. So this is how tools looked on NanoHub before we appified them. It was basically web forms, like what your bank still has today. And you say go, and it goes for a query, right? All right, so very few users, tens, and then some classes took it. Those poor suckers had to use this tool in some classes. And then we appified it, made it interactive, and we saw user growth. Didn't do much marketing. What was even cooler is the number of downloads of this open source package dropped. People are really not that interested in installing software. They just want to use it. You don't necessarily want to muck with the software. And again, I would say that is similar, usability versus capability, as I said in the iPhone and the iPads. People will buy a slower processor that gives you more capability by usability. You trade it all the time. You're used to it. So in apps, it's similar. This tool is an app. It can't do everything that fundamental tool can do, but it can do serve a whole lot more people. So usability is a key. And with that, people started to also use it in research. And I was told by my peer reviewers that come every year with NSF, we are an ERC-like center. There's 6 reviewers, 7 reviewers, and it's a one-day thing where you do a dog and pony show and describe how great you are and what you've done for a year and what you're going to do next. They told us, as I said, nobody will ever use these tools for research. And when I showed them 2008 or so, 9, I showed them the first 200 papers that cited NanoHub, and I drew a social network chart. You know what their response was? Fine, but it can't be good research. Their perception, culture change is so hard to change what people perceive and want to do and can do. And now we keep track of these papers. We're actually over 2,500 now. And of course, then I had to measure the secondary citations to these papers because I was told it's bad research, right? So NanoHub, if it were truly a co-author, H-index would be 106. That's not bad. So now let me show you the social network chart here. Oh, there's one more point here. So in 2016, 17, Thomson Reuters, who own Web of Science, approached us and said, we want to put your apps into digital assets in the Web of Science. So we worked with them for a while. They probe us like a publisher. What tools are published on NanoHub? Similarly, they go to APS and probe their website. What publications have you released? And then Google Scholar followed suit within a couple of months. And we really changed expectations, right? And then I can dive in that, yes, it's not just us that are publishing. 65% of the papers are outside of our core. And what the coolest thing is educators now publishing with NanoHub on how they teach with NanoHub. Completely different group of people. The red dots are nano researchers. About 7% of the authors are in industry. All right. So we also categorize those papers by whether or not they include experimental data or an experimentalist is a co-author. That was one of the key elements. We wanted to have this stuff leave from computational science and put it into experimentalists' hands. That was a goal. We can measure whether we achieved that or not. So yes, 38% of the papers that cite us have experimental data on it. And if we can say, well, there's actually a bona fide experimentalist, 17% of the papers have experimentalists on them. It's kind of cool. So the point is, we have really been translational. We translated from one research into other people's research. We enabled other people to do research in a form that they couldn't have done before. All right, so the next question is, can we do impact on education? So imagine you have a user in time. On one day, that person comes and uses the green tool. The next day, he doesn't or she doesn't come back. And then he or she uses the orange tool 2 days in a row and then the green tool again, right? So I can have a time sequence of data of users, right? And I can do that for a lot of users. And here's sort of a string of data that I'm letting rush by and looks like really scattered, but then you see some patterns, some chunks, sometimes big chunks. And you can run analytics on that. So we were one of the first that run this kind of analytics since 2009, 8. We can actually measure classroom size by people behavior. They don't tell us that they're in the class, but here's one, right? Use the same tool roughly at the same time. Here's a class that uses it throughout a whole semester. This is spring break. And here is a class that uses 1, 2, 3, 4, 5, 6 different tools in a rhythmic pattern, right? We were told nobody will ever use research codes to educate somebody, which is, of course, must be wrong. But can you show it? Can you show it that it's systematically wrong? Or can you have a system which actually can use research codes for education? All right. Oh, the other punchline I tell some NSF folks is, we were always told, you know, assessment, you do that with surveys, like send people surveys. Who likes to answer surveys? Thank you for the show of no hands. This is an assessment that actually measures what people do while they do it. That's assessment, not sending a survey out every now and then. All right. Now, we can do this systematically. We had a couple of sets where we checked with the faculty members that was teaching. I want to drive home the point, we are translational, going from research to education. We truly take research results and migrate them into education. And we can measure that up to 89,000 students now. in some 3,400 courses, 185 institutions. Now, there's other users that look like this, really scattered. Some of those we can identify as researchers, right? Because they have cited us, so we know who the user is and we know what they're doing. Again, this is translational research to research. And then we have a huge group of what I would call self-study users. I don't know what they're doing. I'm just going to claim they study something. All right. Now, these were the users. Those were the classes, right? The tools, purple tool, green tool, etc., are obviously now used in a class. I can develop a ranking for tools in a class, right? I can rank these tools from 0 to 1 in terms of educational use, right? 1 means lots of classes. 0 means very few. Some arbitrary 0 to 1 scale. Also showed you the social network chart, right, of papers citing us. So I can rank the research tools or the tools that are used by self-study people on this category here, right? And people think that these two scales are orthogonal. On one of my site visits, I don't remember the year, but I do remember this. The question was the overnight question they give us, where they give you a question at 6, and then they want an answer by 8:30 in the morning when you present. So the question was, you have 121 tools on NanoHub. Which ones are educational and which ones are research? And I'm like, I'm not the author. How would I know? Right? So you take a wild guess and give them an answer, right? And once you have analytics, you can actually show that a lot of tools bridge education and research. And of course, we knew that. The question is it systematic? Now, the real cute thing, I think, is that imagine I now sit on data of some, say, 20 years of data. And I can go back to the early usage of these tools, and I can measure. In the beginning, I don't know what they're going to be. I put them in the origin, and I'm going to measure how many people use it in classes, how many people use it in research. And then I start the clock. So in the beginning, we had a few tools. We had 500 users to 1,000 users. So it was kind of not really user-friendly, hard to use, web forms. And then we began to create these apps in what we call Rapture. So suddenly, it was much easier to create them. They were more interactive. And look at this. The tools grow and the users grow. So each dot now is a tool, right? And you can see what these tools do. They come from the research axis and go where? This is translational work animated. It shows how outputs from research go into education. Some tools actually make it back too. It's harder to tell, but there's some vectors of actually tools coming from the research side and then being used for education, coming from education then in research. Now, these tools have a DOI, digital object identifier, so they have a birth date. I can measure the time between their birthday and their first adoption in a classroom. Time to market, if you want to call it that. So you might compare that to average time to write a second edition of a book I saw somewhere, 3.8 years. Writing a textbook takes a lot of dedication. Compare that time to having a research tool come over from research into classroom in a week, in a month, or 3 months. The median time for adoption at the time when we measured it was less than 6 months. You can change curriculum and how you educate people in less than 6 months with tools that we have on NanoHub. It's pretty cool. All right. Now, what would one of these tools look like? And what can we measure about it? So this is one of the early tools. It's called a PN Junction Lab. And this also runs this Padre tool under the hood that I mentioned. So here's a highlight. So it was developed at Bell Labs, and it has 16,000 users. I made the slide 2 or 3 years ago. And it's a publication. It has a DOI. Now, if I go here and I click simulate here, I might get a PN junction band edge diagram. To many of you, This may not mean much, but if you're really closer to devices, it might mean something to you. Now I can go in here and change the doping. Set it to 1E17. I run this again, and I get a different conduction band, valence band, okay? I can click on all and actually now compare. This ability to run multiple simulations and compare them across different cases is built into this Rapture toolset. Most of these tools look the same, whether you design a quantum dot or a nanowire or a simple p-n junction. Now, what I demonstrated to you are two simulations in a single session, right? I launched the tool and I hit simulate twice. So I ran two simulations. That's important because I want to show you what classes do. The question is, what do people actually do? So I'm taking two different classes that we detected, 19 users in a class, 20 sessions. So that means they came once, more or less, a single person came twice, and they ran 10 simulations in each session. That's what the number roughly says, right? Maybe 12. Then the other class has 18 users, 29 sessions. So the class, half the class came back and ran a second time. And in total, there's 289 runs or simulations. Now, in this tool, it's a very simple tool. There's actually 17 parameters you can change. This group of people changed 10. And it ranges from the material, p-type, intrinsic, n-type, the biases, temperatures, right? All right, so let's look at what this group of yellow students did, or beige. So here's a Sankey diagram of all the simulations they ran. I can actually see what the class ran. And what did they do? They looked at, here we go, temperature and doping effects, more or less. So the teacher instructed them, most likely, figure out temperature and doping effects in a p-n junction. Quite reasonable. Now here's the other class, and it behaves quite differently. So these guys looked at actually domain sizes. What happens when you change the scale of the length scales in your p-n junction? What if you include an intrinsic region, etc.? All right, and you can compare these now, and I've gotten requests from faculty, what are my students really doing? So I want to integrate NanoOp into a learning management system so I can actually report that back. All right, and you can see that the classes do look quite different. Now, that's a class, but let's look at an individual. How do individuals behave? Can you look into the behavior, the simulation behavior of what people do? So that's again, imagine you have an n-dimensional space. Let's assume you flatten it down into 2 dimensions so I can visualize it nicely. So a person might start from a starting point and then vary parameters, maybe just one parameter go in one direction, then change 3 parameters. That would be a big dot like this, and then a small, and a couple more small changes, right? So I could have a pictogram of how a person behaves in this design space, right? They go from start to finish. Now, this one is actually a specific user in this p-n junction lab. Took like a specific tour through this design space. And we call those wanderers or searchers. Here's another person. From the start, takes a big jump, local explore, big jump, local explore, big jump with a local explore, and then they home in on something. From this diagram, I can't tell what they home in, but it's just a visualization, right? So we also call that person a searcher. Now, you might say, well, how about this guy? This person is just jumping wildly in this design space, right? Changing 2 parameters, and we measure the distance. There's a distance metric between these dots, right? How far these parameters are from each other. So we call that person a wildcatter because they jump all over the place. Now, if you had a class or if you had a population of people that are researchers or educators, what do you think, how many of them are searchers and how many of them are wildcatters? Modi, what do you think? They're jumping like wild. So most people in the total population on this tool when we ran this were jumping. But there's differences from one class to the next. If I take a subset, for example, of a class, they have a slightly different distribution. And if I look at another class, I have a different distribution. So educational material might make quite a big difference of how you guide people through this process. So now, imagine now you actually, well, let me back up. So how do we do these simulations, right? We start out with a set of input parameters and we simulate something, right? Click, give me a result. And we wait for a certain time and then click, get another result, right? And we understand something and then we begin to home in on something, right? It's a very iterative process, right? And it takes a while. That's how we design things, right? It's an iterative approach. The first thing is never quite right anyways. Now, imagine you sit on a ton of data of what people actually have simulated. And you could explore that visibly. Could you reduce the number of new simulations that are needed? So we're working on prototypes now that actually accumulate the simulation data we have for these different tools. And you can explore not just the output, also the inputs. You can actually see what people have varied in terms of input and then home in on outputs. Hopefully, we can actually shorten design cycles or the way you look at data. And of course, you can then drive that with machine learning, actually preemptively compute certain things towards certain designs. All right, so that's one of the goals. So to me, it's really derive reduced order models and propagate these lower level models into higher level models, into circuits, etc. So here's again the summary and I'm on NanoHub. And I would argue that really we have changed people's expectations and assumptions. Assumption was nobody will use your research code to do their research. Assumption was nobody will use a research code in education. Assumption was the software is worthless, it's the papers that are what are important. And it's becoming clearer and clearer that actually the tools that generate these computational papers and data are actually just as important, if not more important, than the paper, the PDF that comes out. Because a lot of that work is not duplicatable. So we have made progress in there. So that's the item I wanted to highlight with the nanoelectronics, with user and machine learning. And I have a few minutes left, so I'm going to highlight what I think might happen next. As I mentioned, on the CMOS side, I think we're really done. There's going to be, there will be improvements, but they're not on the individual device size as much as doing really custom hardware to design things for custom hardware for certain purposes, given the Legos that you have. The Legos won't get smaller and faster, but the design you can do with them will be better and better. And there's other devices that are really use-inspired. For example, stochastic switching, usually used for random number generators, but there's other approaches now with neural networks and triggers. So Suprio Data here has a couple of nice patents that deal with these metal junction devices that are random in noise, and they harness that with their p-bit. So the p-bit might be something that comes out much faster than the quantum computer, and it can tackle similarly stochastic problems. And it's really use-inspired, right? What can we do with it? Same here with, now they have it with nanomagnets and spin currents. And again, a use-inspired patent that can really be a spin switch. I mentioned that these resonant tunneling diodes I worked on a long time ago, we really couldn't get the valley current to go down. So then we knew that. We could then generate some patents that knew that and utilized it and made memory cells that were aware that you can't get the valley current down, but you can do something else with it. And you would get the valley current down in different ways. You make a really complicated structure. So I would argue here really the conclusion is that these innovations are not driven by modeling per se. They're driven by fundamental insight into these devices. And really a physicist or a device physicist really have an understanding of these devices, and it's derived and validated by modeling, maybe built first in a model. And it's really understanding the higher level circuit needs. We would not have patented this memory cell if we didn't know you couldn't get memory cells in 3.5 at the time. It was application driven. Now that patent is long expired, doesn't matter. But that's an example of what can you do with a novel device when you talk with other people. So that's the key element, right? Custom circuits with custom devices and custom problems, and you collaborate with people. And quantum computing is in many ways just like that, right? You have a new tool set, so custom sets. All right, so earlier on, Susanna mentioned, right, GPUs, we program for GPUs all the time already. So we have specialized hardware, quantum communication, quantum computers. To me, that's in the same category, right? And I mentioned in the panel, my pitch to Arda in 2002 was, if you want to build a silicon-based quantum computer, you better start modeling what the devices would look like, not stick diagrams of two-level stick diagrams. That just doesn't do it. All right. So I think this is pretty much it. So I gave you my overview of how I see modeling, what I thought was good to do. And the key element, it was transferable. I never was interested in building just one tool for one paper, one student, another paper, and another tool. It should go beyond that. And this is now transferable into other areas as well, on device-driven research. And really, I think the key chance we have is to have this non-equilibrium transport and the non-equilibrium approaches of open systems transfer into other fields that have not yet seen or appreciated the need for it. And then on the results side with NanoHub, really doing this with user data and machine learning and reducing complexity. So that's basically it. And if that doesn't work for me, my plan B is ski instructor. And so with that, I thank you. And whether or not you ski well depends on who's looking. And sometimes you don't do so well, right? So with that, I'll thank also my family for putting up with me. So thanks.
I think we have time for one question, one short question, if anybody has a.
Oh.
Yeah, thank you so much. There was a beautiful overview of the quantum transport for the last 25 years. This is my question now. We're discussing a new tool, which is quantum information and quantum computing. And my question, I mean, this morning we saw the beautiful experiment with the quantum spin liquid. And this comes after 40 years when the theorists put together this, with Anderson, the theory. So from your experience with the quantum transport, do you see some like a fundamental thing or some phenomena there that a quantum machine or quantum computer or quantum algorithms will make a difference?
Oh, to calculate things with a quantum computer. Oh, yeah. I mean,
some unique system that like we have this spin liquid phase that took 40 years to do it. I mean, is there something there from your experience that is sitting there for young people to look at it and see if we can, with these new tools, we can make a difference?
I haven't thought about it this way, but certainly the computing problems of doing true quantum transport or electronic structure are so large that they should lend themselves to a quantum computer, right? The issue is we're interested in non-Hermitian systems, right? So the quantum computing I see all the time are Hermitian most of the time, right?
Actually, first off, quantum computers can certainly model non-Hermitian systems, actually not that hard.
Okay.
It's hard to keep them Hermitian. But I have a question. So I think this is actually very cool and kind of inspiring about how this all developed. So do you have kind of a plan to maybe, for example, add like quantum simulators? Or have you ever thought that these new sort of quantum machines, which for scientific applications, they produce some useful results already? Do you think there is a possibility to maybe integrate it into your system? Because this would be interesting for researchers.
Sure.
You know.
Yeah, definitely. I mean, the complication, I mean, similar to what Sabri said, right? Can you map your electronics problem into a quantum computer? Sure, certainly.
And it's certainly, I mean, like this will not, this quantum simulators and computers, they are not going to substitute it because it's not like we don't have systems big enough. But if you identify, for example, the problem which is really hard, like for example, some critical, problem or spin liquid or some, this could potentially really be added as a kind of subroutine, as accelerator to it.
Yeah. Yeah, I agree. Building accelerators is of course hard, right? Integrate. Well, what I think is that the other opportunity is putting actually tools in apps in NanoHub that deal with quantum computing. Yeah, exactly. So let's do that. That I think is a huge opportunity.
All right, I think that's all the time we have for today. Let's thank Professor Kumar one more time.
Great.
I'd like to remind any students that have not from Purdue, that have not talked to our staff about reimbursement to go ahead and do that during this break. But otherwise, we'll be back here at 3:45.
Overview, perfect, very nice.
Yeah, okay, good.
That's beautiful. A lot of work, very nice.
Yeah. But it came together, right?
Yeah, no, my student was thinking like to do transport and how to write a quantum algorithm to do the green function. And I'm new in the field, so I looked.
Okay, superior stuff.
But nobody have run quantum algorithm. Nobody have designed a quantum computing algorithm. Somehow, maybe I'm missing something, but I didn't see any in the literature. There's a quantum algorithm to do
NEGF.
Yeah. So we thought to start looking at this.
Not yet.
subject.
That would be new, right?
I thought we start looking at this issue, and this is why I'm asking.
Test, test.
Ready? All right, good evening. It is my pleasure to introduce Maria Mihalova. Maria is a principal software engineer at Microsoft Quantum. She drives the developer outreach and education work for Microsoft Quantum Developer Kit and Azure Quantum. Maria is a champion for quantum outreach and education and develops tools for hands-on learning through Microsoft Quantum. Please join me in welcoming Maria.
Hello, everybody. It's so exciting to be talking here in person, see and meet all the lovely three-dimensional people. Today, I'm going to give you an introduction to Microsoft Quantum Development Kit and Azure Quantum. Basically, I'm going to walk you through the quantum software development process step by step and show you how Microsoft Quantum Development Kit and Azure Quantum support it on all steps. And there are not going to be a lot of slides, just a couple, and then it's going to be all live demos. So to start with, allow me to introduce Azure Quantum. You might have heard about it, probably haven't played with it, possibly you have. So Azure Quantum is a project that Microsoft released a little over a year ago now. And it's basically a cloud ecosystem that allows you to run quantum workloads in a cloud enabled by a variety of providers. Azure Quantum combines both purely quantum offerings and quantum optimization workloads that run on classical hardware. So here you can see the ecosystem behind Azure Quantum. One of the frequently asked questions is what hardware providers are available via Azure Quantum. And we have IonQ and Quantinuum available right now for public consumption. I'm going to show them in the demos later today. And Pasquale, Rigetti, and QCI are all in the process of getting plugged into Azure Quantum. I cannot say which one of them is going to hit the private preview first. Now, let's take a quick look at quantum software development process and the tools that Quantum Development Kit offers for its steps. So I'm assuming you all folks are familiar with quantum computing to some extent. So you're familiar with the idea that quantum programs don't exist in a vacuum. Instead, they are going to be integrated with classical software, both for preparing inputs for the quantum programs, which can be fairly sophisticated, and for analyzing the results produced by the quantum programs. For example, if we are looking at Shor's algorithm, it's a purely quantum program. The input is pretty straightforward, and the output is also pretty straightforward. But if you're looking at, for example, chemistry, you're going to have inputs that you're not going to be entering by hand, and the results produced by quantum programs are also going to be useful for you only when analyzed automatically, not just something a human's going to consume directly. With this in mind, here is the quantum software development workflow we have in mind. So the first step is not on this picture, of course, it's identifying the problem you want to solve and figuring out the algorithm to solve it. That one is done possibly on a blackboard, possibly on paper, but you might not need software for that. Once you have identified the problem you want to solve and the way you want to approach it, your first step is going to be writing quantum code. Quantum Development Kit supports originally C# and recently, just in the past year, since the last time I presented at a summer school, we added support for Qiskit and Circ. So now you can run your existing Qiskit and Circ codes via Azure Quantum. To help you write your quantum code in C#, we include integration with the editors. Visual Studio if you're on Windows, Visual Studio Code if you're on other platforms, or on Windows as well, for that matter, and Jupyter Notebooks. I'm going to be showing you all of these environments later today. The next quantum development kit component for the next step is quantum development kit libraries that are created to help you keep your code high level. Well, technically speaking, keeping your code high level is part of how you write your code. So it's a sub-step of the previous step. But that didn't look great on the picture. So the libraries offer you standard functionality that appears in a lot of quantum programs that you don't want to re-implement again and again every time you implement a program. For example, a lot of quantum algorithms rely on quantum arithmetic or on Fourier transform. These are not the kind of primitives you want to develop from scratch every time. You want to have a library for that. The next step is integrating the quantum components with classical software. C# allows you to integrate it with Python or with .NET languages, such as C#, F#. I have done it with Visual Basic.NET. It's not something I recommend people to do. I'm probably the only person in the world who did it, but it is possible. And of course, if you are using Qiskit or Circ, you're going to be integrating them with Python. The next step is running your program in simulation. Again, as you probably know, quantum hardware is right now a scarce resource. Long queues to get access to it. It's also noisy and not really scalable. So in most cases, you want to run your program on simulator first to figure out that it's correct before you hit the hardware. So things like unit tests, approaches that we can borrow from classical software engineering can be very helpful when doing quantum software engineering as well. So for this, Quantum Development Kit offers a number of simulators, from the full state simulator, the kind of standard one that performs accurate simulation of a quantum system, to a number of specialized simulators, such as TOEFL simulator to test arithmetic and other kinds of reversible computations. Noise simulators, and that's actually a question that was asked at the last summer school. Does Quantum Development Kit have noise simulation? At that point, a year ago, we didn't have it, but we released it a little less than a year ago. If we have time today, I will show you how it works. The next step, once you have written the unit tests for your code and convinced yourself that it is correct, it's not yet the time to hit the hardware. Next step you want to do is to estimate the resources needed to run this program on hardware to make sure that it makes sense to do this. If your program requires more qubits than your device has, it's not going to be a big success running it on hardware. And the same thing if your program is too long. The longer it is, the more noise is going to be introduced during the computation, and effectively, at some point, your computation is going to be overtaken by noise. So not much point running it as well. So resource estimator allows you to estimate the resources necessary to run your program and figure out whether you need to work on optimizing it or whether it's good right now. And finally, after that step, you're good to go to Azure Quantum and run your code on actual hardware. And the point to emphasize here is that all these steps use the same quantum code for running them. it would be really inconvenient to run unit tests on one code, but then rewrite it completely when you run it on hardware. Those unit tests are not going to be very helpful. So you can use the same code and let your system transform it into the form required for running on simulation or on hardware automatically. Next, a couple words about Q#. I'm going to show you how to work with Qiskit later today as well, but most of the demo shows you the workflow of working with Q#. So Q# is Microsoft's domain-specific quantum programming language designed for implementing high-level algorithms in a manner that is hardware agnostic. If you look at this little code snippet, I'm going to show you a lot more Q# later, but this one allows you to see the basic things about Q# already. Now, this is a small code that shows you random number generation, random bit generation, if we are being accurate. So one thing you see is that, of course, since it's a quantum domain-specific language, it has quantum concepts and data types built in. Here you see that we are allocating a qubit, and qubit is a built-in data type. We can apply a Hadamard gate to it, and then we can perform measurement on it and compare measurement results to built-in constants. Other quantum concepts are modeled implicitly in this language. For example, you see that here we are never thinking about the quantum state throughout this program. We are just thinking about the operations we want to do on the qubit. We want to allocate it, apply gates or measurements, but at no point we reason about the state itself, which is actually physically accurate. If you're working with a quantum device, you cannot reason about its state when you're in the process of working with it either. You can only issue it instructions and get results back. Next, Q# offers language constructs and compiler capabilities that are specific for quantum computing. They didn't make it to this code snippet because it's too small for them, but things such as conjugation, implementation of uncompute pattern automatically, generating of adjoint and control variants of operations, repeat until success loop are all things that are very frequently used in expressing algorithms. And this means this is something you want to have in a language. And then this language is designed for running programs on quantum computers. You see here that the language doesn't describe any details about where it is running. You can run this same code either on a simulator or on one of the Azure Quantum backends without modifying the code itself. Oops, too early for this slide. Okay, and this is it for the slides. Now we're going to move on to the demos. The rest of it is going to be live demos. I like to live dangerously. So to start with, let's okay, let me check if I can switch to another window now. Okay. Well, new mode of presentations, new kind of technical issues. Okay, where was I? Right, now let's go back to the quantum software development process I described earlier and see how it actually looks like when executed with our tools. So our first step was writing quantum code. And again, we need to take a step back and think about step 0. What is the problem we're going to try and solve here? Here, I'm going to be solving a very simple problem, solving a modular equation, an equation of the form a times x plus b equals 0 modulo c. Now, this is not exactly a complicated problem, but it is a little better than Deutsch-Joss algorithm. And I have a thing about not talking about Grover search, looking for a fixed hard-coded thing solution. So this is the reasonable balance between an algorithm that is understandable and something that is sophisticated enough to show enough interesting behaviors. So this is the problem we're solving. Our step 1 is to implement the algorithm. Here I'm going to be using Grover search. And as you all know, Grover search consists of 2 main components. The quantum oracle for identifying whether the given quantum state is the solution to a problem, and the standard building blocks that work with this oracle. Here I'm in a C# project that implements the end-to-end solution. I'm using Visual Studio here. On my other computer, I have Visual Studio Code. So it's a choice for a Windows user. You can see here that the project consists of 3 separate parts. The main one is the quantum library, the quantum code that solves this specific problem. The other 2, we'll see in a little bit, are the unit tests for this code and the classical host that interacts with this quantum code and allows us to solve an application that is practical for the user. Let's start with looking at the quantum library itself. So here is the quantum oracle itself. A quantum operation that, given 3 integer parameters, a, b, and c, a register of qubits, and a target qubit, flips the state of the target qubit if the qubit register is in the state that is solution to this equation. So a normal marking oracle. And here is what's happening inside this oracle. It's very short, it fits on one screen. Here I'm taking advantage of the libraries in the quantum development kit to make this solution short and not particularly hard to write. So here I'm using modular integer multiplication and addition to modify the state of the register X in place. First, I multiply it by A to get this part. Then I add B to it to get the whole part of the equation that is supposed to be 0. And these are modular actions. I'm doing them all modulo C. You can imagine that actually spelling out these operations on a gate level would take us longer than a screen. But here I'm using libraries, so I'm free to go on and do something interesting with my algorithm instead of thinking how to do addition step by step. Once I have transformed the input register to this state, I check whether it is 0 using another library operation that flips the state of the target qubit if the control register is in a specific integer state, in this case, state 0. And then I'm using this conjugation construct within apply that implements a computation pattern. Remember that for quantum oracles, we need to make sure that we don't modify their input register as we do the computations, because that would mess up our later algorithm. So we need to uncompute whatever changes we did to the input register. And this within apply construct does exactly this. It applies the within block, then it applies the apply block, and then it applies a joint of the within block to uncompute that part of the computation. So again, the less code you write by hand, the less chance is to get it wrong. You don't need to write a joint of this block by hand. Save yourself some space for errors. The rest of the blocks are implementation of a more or less standard Grover search. This one applies marking oracle as phase oracle, so effectively implements phase kickback trick, allocates a qubit temporarily, prepares it into the minus state, applies the marking oracle, and uncomputes as a state before releasing the qubit. The next one is another interesting step, preparing the average of all states that are the search space of the algorithm. And again, here I'm not doing this by hand. I'm using a library operation that prepares an arbitrary quantum state. In this case, a state that is an equal superposition of a certain set of basis states. Again, not something I would like to do by hand. The next one, running Grover search. The normal thing, allocate qubits, convert marking oracle to the phase oracle, prepare equal superposition of all input states, and then run Grover search iterations. Measure and get the result. And the final piece is the operation that interfaces between the user who is going to be using this library and the library itself. So it takes the coefficients of the equation and produces the result. This operation is the one that's going to be called from C#, from Python, when we want to use this library as part of our application. This part was our steps 1 and 2, writing the quantum code and using the libraries. Now let's take a look at our step 3, writing the classical code to interface with the quantum one. Here I'm going to be using C# for a little bit. I'm going to show you how to use C# from Python later on in the next part. But for now, it's going to be C# because I want to run it from Visual Studio. So here, I'm going to think about this problem at a broader point of view. Let's look at what a user might want to do with this library. And here, what the user wants me as a quantum developer to do is the user has an SBN 10 string with 1 digit missing. And they want me to recover this missing digit so that they can go and look up the book by this SBN. It's kind of a very common problem for quantum computing, happens to me all the time. But it shows us the steps the classical code is going to perform when working with quantum code. So we get input from the user. We could also be getting it from a database or from some kind of service that invokes our library. And then we do classical preprocessing to get this user query and to convert it into something that our quantum program is going to take as input.
In this case, we are taking this ISBN number with one missing digit and figure out to which equation it boils down. It's based on how ISBN numbers process their checksums. If you're curious, but it really becomes this kind of modular equation with fixed module. The next step is that this classical program is going to run the quantum code. When you do it from C#, the syntax looks like this. You start by creating an instance of a simulator. In this case, we're using quantum simulator, which is the full state or state vector simulator, which performs an accurate simulation of the quantum system. And then you use this simulator as an argument to a method that looks like this. Every C# operation becomes a C# class, which has a run method. And this run method accepts a simulator as the first parameter. And then any parameters that this original C# operation took. In this case, 3 integer parameters as the coefficients of the equation. So you call this .run method of this C# operation, you get the result, and you convert it into an array. That's it for the quantum part of the classical code. After this, a classical code does post-processing. It takes the result produced by the quantum component and converts it into a result that is going to be useful for the user. In this case, a recovered ISBN. Let's see this program running. You see that the quantum component reported which equation it was solving. It reported the parameters of grower search it used. In this case, we're using 2 iterations to solve the equation. And then the classical component of the program reported the recovered ISBN. So now you can go back to the user and show them the book they have been looking for. Great. Now we have gone through the first 4 steps of our process. We did the integration with the classical program and the running on simulator. But let's spend a little bit more time on running on simulator. So that I can show you how to write unit tests for the quantum program. Here, C# allows you basically 2 ways to run unit tests. One is the same as you write regular programs, basically define classical host program, run quantum code from it, and do any checks you want in the classical code. And the other way is this one. You can write a test that is just the C# code and annotate it properly so that it gets recognized by unit testing frameworks. This operation is actually a unit test. This add_test attribute tells XUnit testing framework that this is a unit test that should run on quantum simulator, this parameter. And when the tests are executed, XUnit runs them, and if there are any exceptions, the test fails. If there are none, the test passes. The logic for the testing is here. What I'm doing here, basically, I'm testing just the quantum oracle because it's the trickier part to implement of a Grover search algorithm. And I'm basically iterating over all possible input strings and checking that the results of applying a marking oracle that we're testing match the results of applying the classical function that we expect to match, because this is an oracle that implements this classical function. So since I know I'm not using any measurements in my oracle, if it matches on all inputs for the basis, on all basis states that describe valid inputs, it's going to be correct on superposition states as well. And here, if you look at Test Explorer in Visual Studio, you're going to see those operations represented as unit tests, and you can run them from Test Explorer. If you're using Visual Studio Code or Test Explorer or command line, you can use the normal ways to run unit tests, .NET run to run the program, .NET test to test the unit tests that are found. And you can see that the unit tests pass, so the solution seems to be correct, not just on one specific scenario that I used in the demo, but also on the scenarios I used in the unit test. Now, I think we spent enough time in Visual Studio. Let's switch to the next environment. Yes. And now I'm going to look at our next step. Step 5, resource estimation. Let's see what kind of resources are required to run this program on hardware and whether we do possess this kind of resources. I'm also going to take a little detour and show you some visualization tools you can use when running Q# code. So here I switched to a Q# notebook. And you can see it here in the top right corner that the kernel is Q#. And from here in Q# notebooks, you can do all kinds of things. You can define Q# code. You can run it on a variety of simulators, and you can use specialized visualization tools here. Some of those tools are not actually available from Visual Studio or Visual Studio Code. So Jupyter Notebook is the nicest way to do visualizations for Q# code. Here, I'm not going to be defining any Q# code here, but instead I'm using Jupyter Notebook as a front end for the backend project that I showed you in Visual Studio. If I put the Q# notebook in the same folder, it has access to all Q# code in that folder as a backend. So here, let's run the same find equation solution operation with smaller parameters. I'm working my way towards running this code on a quantum device. And for this, we know the code needs to be small enough and simple enough. So the first step is, well, solving the problem for smaller coefficients. You can see that when we run the simulation for these parameters, we get raw results not converted into a single integer. Because converting the results to a single integer was something that was done by our classical post-processing code. And here we are just running the quantum code. But this is a very small example, so we can figure it out ourselves. Our results for our x are 0, 1. It's a binary notation. It's a binary notation in little endian. So the least significant bit goes first, which means that it's 1, 0 in normal binary, which means it's x equal 2. And indeed, if we look at this equation, x plus 2 should be divisible by 4, which we all know that 2 plus 2 is divisible by 4, in fact. So now that we have convinced ourselves that we're running the same code and it gives us correct result, let's see what resources are needed to run this algorithm. Now, this percent estimate magic runs general purpose resource estimation, not tailored to a specific device, such as IonQ device or Quantinuum device. It's a generic estimation that evaluates the resources required in general terms, such as the number of T gates, the number of C0 gates, and the depth and width of the circuit. Now, looking at these parameters, we see that circuit width looks okay. 8 qubits is within capabilities of IonQ or Quantinuum devices. But the part that doesn't look good is the number of T gates and the number of C0 gates. Anything around 1,000 gates is probably too much for the current devices. Things are going to get really noisy before we get our useful computation result. And for such a small result, we really want to get it with high confidence. So let's see where this kind of complexity of the circuit comes from. I think we know this. So the next tool is percent trace, the magic command that builds the circuit of the quantum operation with the given parameters. But it doesn't build the circuit all in terms of primitive gates right away. Instead, it gives you a trace with this default depth. So it goes from the parent operation several levels of depth down, and it shows you that level of abstraction. So here you can see the library functions and operations that this circuit uses. You can see that it uses arbitrary state preparation, multiply and add by modular integer several times in the oracle, then phase operations, and then uncomputation of this. Now, if we want to break this circuit down even further, we can do it manually by clicking on the blocks and drilling down into what's going on there. You can see that those operations are quite deep. They call each other a lot of times. And then we got to the point at which there are getting more and more of those steps. New gates are appearing. Okay, I'm too lazy to actually click down to all the way down to the bottom of the circuit. So I'm going to change the depth of unrolling this circuit to make it deeper. And then the percent trace command is going to build the circuit in more detail right away. And you can see that here there are a lot of controlled rotations. Yeah, a lot of rotations. Those are expensive. So what are we going to do if we want to run this program on a quantum device? Well, I'm a person with a mission, and I am going to run it on a quantum device. So what I'm going to do is I'm going to rewrite this code for a specific simplified case. It's going to still keep the structure of the Grover search algorithm and all the necessary steps, but two things are going to be greatly simplified. One is the quantum oracle, of course, since this is where all those modular additions and multiplications are coming from. And the second one is going to be our average state preparation routine. So for the oracle, I'm going to simplify the problem that we are solving. I'm going to remove the parameter a, the multiplier at x. I'm going to say that it's always 1. I'm going to say that the modulo we use for computations is always 4. And so I'm going to keep only one integer parameter, this parameter b. And I'm going to be solving this kind of equation x plus b equals 0 modulo 4. So this way, I'm not quite hard coding the answer because the answer is different for different parameters. But I'm simplifying it enough that I can do computations modulo 4, since it's just addition of a single number. I can write it out in simple gates. And the second step, when I use a library operation for preparing the average of all states in our search space, I'm going to say that actually for modulo 4, all the states are our search space. So I'm going to prepare superposition of all states. And you know that's just applying Hallmark's gate to each qubit. Again, much easier than preparing an arbitrary superposition state. Once I have done this simplification, well, remember how I told you that if you rewrite your code between you run unit tests and you run it on hardware, you're running the chance of introducing bugs. And here is exactly what I'm doing. I'm writing unit tests and then rewriting the code. But I'm pretty self-aware, so I add a unit test to cover this rewritten code. I'm changing the unit test as well to account for the fact that my equation is described in a different manner. So I don't need all those parameters. I need to test just one parameter. But I'm using the same logic to test the solution. I'm still comparing it to a classical function that performs the same computation. So when this unit test passes, I know that this solution is also reasonable. Now that I have optimized my code and ran the unit test for it, let's go back to our tool for resource estimation and see what it tells now. We can still run this code in simulation, getting the same result, which is always nice. But now when we do resource estimation, our resource estimation is much nicer. We went down from 8 qubits to 3 qubits, and our number of T nodes went down an order of 2 orders of magnitude actually. And you can see that our circuit, this time unrolled all the way down, became a lot smaller as well. It also doesn't have arbitrary rotations any longer, which is also nice. You see that trace simulator doesn't do some optimizations like gate cancellations. For example, those 2 X gates and those 2 adjoint X gates are going to just cancel each other. But trace simulator doesn't do it. It dutifully reports all the gates that have been applied during execution of this program. So now our code is optimized and we have convinced ourselves that we can actually run it on Azure Quantum. And we can go ahead and do just that. Now another change of environment. This time show some projection. So this is what Azure Quantum looks like from Azure Portal. One of the environments that you can use to run quantum jobs and manage your jobs and set up your providers. Question? Yes, but you need to make it a little louder.
Hello. So obviously the simplified solution is just using the more general solution with A and C bound to 1 and 4, I guess. Do you think it's capable of just having the general function there and then maybe assigning some constants and simplifying the function automatically, or you have to rewrite this manually?
So is the question whether the library I'm using capable of realizing itself that when I'm providing smaller parameters, the circuit can be simpler?
Yes, yes. So, let's say we have the general function and I'll tell it, okay, I'm going to define a new function with A equals to 1 always and C equals to 4 always. And then, it might be able to propagate and simplify.
Yeah, so the specific library function I'm using, I think, cannot realize it itself. There are ways, kind of things you can do to implement operations so that they use different implementations in different scenarios. For example, one way is to use different implementations depending on which simulator or which target you're using. So for example, if you have different gate sets available, it's going to use different implementations that take advantage of this or that gate set. Another trick you can do, come on, I know that there were two. Yeah, I mean, obviously you can write an optimizer that is a lot better, or you can write your code so that it figures it out depending on the parameters. Oh, right. As the second automated trick you can do is you can use automated Oracle generator that takes an Oracle, a function for which you need to implement an Oracle described in a specialized way. And it's going to generate this logic automatically. So I'm not sure if what it would generate for this kind of ask would be better than a modular arithmetic implementation or worse. I haven't tried it for this specific thing, but it's one of the things that is possible. Okay, so Azure Quantum Workspace. This is a workspace I created actually, especially for this talk yesterday, brand new. So this is something you're going to see if you create a workspace using our free credits program. Azure Quantum has a program that allows you to run some simple programs on IonQ and Quantinuum without paying for it. So nice for education and some small experimentation. So this is what you get if you create a workspace using that setup. So you see the parameters here, such as subscription and storage account. These are the parameters you're going to need to connect to this workspace and submit jobs to it. If we look into the settings for this workspace, as a sort of spoiler for what I'm going to show you in the rest of the demo, one thing you see is the list of providers that are available in this workspace. You can see that it has 3 providers, default ones: IonQ, Quantinuum, and Microsoft Quantum Inspired Optimization that I'm not going to be talking about today. And each provider has several targets. For IonQ, it has IonQ simulator that is effectively a full state simulator running in the cloud, and QPU, an actual quantum device. And the interesting thing for them is the average Q time, this last column. You can see that simulator jobs run really fast because it's classical compute and can be scaled up really fast. But for QPU, we have a wait time of something like an hour and a half. Don't worry, I'm not going to submit a live job to the QPU with that kind of queue time. I know we have a dinner to get to and plans for the evening, but a live job for a simulator is perfectly viable. For Quantinuum, it actually has more targets. So Quantinuum targets come in 3 flavors. The ones that are ending in API wow are actually the validation of your program. When you submit this kind of a job, it checks that this program is going to be able to run on a simulator or a hardware device, but it doesn't actually run it. So an advanced syntax checker. The targets that end up with SIM are emulators, accurate simulations of quantum devices, but still it's classical compute. And the ones that don't have any of those suffixes, S1 and S2, are actual hardware targets. You can see that the hardware targets are offline right now, but the API validation and the simulations have both really nice queue times, less than a minute. So that's actually what I'm going to use today. This tab, credits and quotas, shows you the benefits you get from creating this workspace via Azure Quantum Credit. So you can see that you get some resources to run on IonQ and then on Quantinuum without actually putting hard-won cache in there. IonQ and Quantinuum have different billing models, and I'm really not going to go in there. But this is the usage I did when preparing for this demo, basically running through all the jobs in the demo. And it used a couple % of the total credit I got. So you can do a lot more than I do in the demo and still not have to pay for it. Now, the job management tab shows you the jobs that I ran. And the notebooks gives you another way to run jobs. So now that I gave you a quick tour of Azure Quantum environment, let's see how to actually run jobs from several environments, because why not? So here I'm switching environments again. This is a Python notebook, as you can see by this Python 3 kernel, that is going to work with C# quantum code. Again, this Python notebook is a front end for C# backend. So it sits in the same folder as our quantum library and has access to all C# code in that library. The same as the C# code did, but the syntax of doing it is different for this language. So the first cell I already executed, it did the imports to set up the environment. Next, again, let's retrace a couple of our steps to make sure that our code still makes sense and still gives us a reasonable answer. So here I'm defining a function that will do the post-processing for us, conversion of the little endian to a number. And here is a Python code calling the C# code and getting the results. You can see that in Python it's slightly different. You don't create the simulator explicitly, but instead you call the .simulate method of the C# program, and it figures out by the method you call which simulator to use. .simulate is a full state simulator. And then you pass it the parameters, you get your answer bits, and then you do your classical post-processing. So here we get our result x equals 2. And then the next step we retrace is resource estimation. To do it from Python, you call estimate resources with the right parameters. And you see it gives you the same numbers, just in a slightly different format. So we're still good for the circuit widths and number of gates. So we're ready to connect to Azure Quantum and run the code. The next step is you connect to Azure Quantum. You provide to this method these parameters that were listed in the portal overview. Then you do some kind of authentication. Depending on what your settings are, it can be as simple as entering this code, or it can require two-factor authentication, which my Microsoft account does require. But once you have done this exciting part, you're going to get a message that you're connected to a workspace, and here are the targets available for you. You can see that we have IonQ targets available here, and the average queue time is also reported. Once you're connected to Azure Quantum, the next step is to choose the target of the available ones here. I'm going to start with running on a simulator. Again, always better to run on a simulator first. And after the notebook has loaded the right packages, the active target is going to be the simulator, which means that any job I submit now is going to go to the simulator. And this is exactly what I'm going to do now. I'm going to run a job using the Azure submit. I'm going to submit it to target simulator because that's our active target. I'm going to give it a nice descriptive name so that when I have a bunch of jobs after this demo, I know which ones of them ran on simulator and which ones were on hardware. And you can see that job submission succeeded. I got a job ID back. If we look at job management here, you see that this job appeared in the list. It has the name that I provided it. It has an ID that is not human readable, but that's how you operate with your jobs. That's how you query their statuses and their results. Yeah, here, 2 simulator jobs. One waiting from today and one succeeded from yesterday. You can see the submission time. You can actually confirm that this job was submitted right now. And this is a job that was submitted a little earlier today. And now we go back here, which can check the job status, see whether it completed or not. And since it's a job running on a simulator, and queue time for the simulator is seconds, not even minutes, the status is already succeeded. Now we can fetch the results, and we can see what they are. Now, when running on IonQ simulator, the job results are going to be a histogram. And the funny thing is, somebody asked me a couple of weeks ago, even if you run just a single shot on IonQ simulator, you're still going to get a histogram because it doesn't actually run your job multiple times and aggregate shots from each run, but instead it runs the job up until the measurements are done and then builds a histogram of the probabilities of the results you get in that measurement. But here, we're not running into this. We ran for multiple shots and we actually have a nice deterministic algorithm, Grover search for searching for one state out of 4 is not going to get any normal random fluctuations. So our histogram consists of one state, 0, 1, which is the same 0, 1 we have seen in little Endian encoding before. But just to be systematic, we can plot a bar chart or a histogram of this result, and we can find its most frequent key that corresponds to the answer. And yet again, we can confirm that 2 plus 2 is divisible by 4. But now that we have done this, we can run this job on hardware. If you switch the target to QPU, now any jobs you submit are going to go to the QPU. But you can see that average queue time is even worse than when I ran the connection to Azure Quantum this morning. So I'm not going to submit this job live. Instead, I'm going to do a baking show trick and say, and here is what this cake is going to look like when it's baked. So I did submit a job last night. And you can see this, actually this job running on hardware. You can see that it succeeded. And you can see that while this job was running very little time, less than a minute in physical time, the time from submission time to completion time was almost 3 hours. And that's on a Monday night. I guess somebody else has a demo to show today. Or maybe tomorrow if they're more organized than I am. So I'm going to pull up the results of this job. And those are very similar to the results you would get if I ran a job right now, but we get this sooner than 3 hours from now. So I'm using the hard-coded job ID here to extract those results. And you can see that it's a job that was running earlier today and it succeeded. Now, when we get the results are going to be more interesting. We get a distribution of all 4 possible answers. So our correct answer still has the probability of 82% appearing. But the other 3 results also have non-zero probabilities for them. And if we plot this in a histogram, this is going to look like a proper histogram with all values present with different probabilities. So you can see that for this circuit, we still can figure out the answer by just looking at what is the most frequent key in this histogram and saying that this is the result. But this was a very shallow circuit. If we go back to our resource estimation, it's 3 qubits and it's like 2 dozen gates. It's not a lot. So if we try and run more complicated circuits, things are going to get really noisy really fast. It's actually something on my to-do list. Give a try to scaling up a similar program and see at what point it actually does get overwhelmed by noise. And this concludes this part of the demo. I have more to show, but if anybody has any questions, it's probably a good moment. Okay, crystal clear. That's how I like my talks to go. Okay, what did I have in mind next? All right. Next, I want to switch gears again, because why have all those lovely environments set up and not use all of them in a demo? So now I'm going to show you how to run Azure Quantum jobs from hosted notebooks right in the environment. This is one of the ways you can get started with a quantum development kit without setting it up on your machine like I did. You can create a workspace, go to the notebooks, and here you have actually a bunch of predefined notebooks that you can start with. That's really helpful to do this step-by-step management for Azure Quantum jobs, because this can be a little tricky to figure out when you do it for the first time. Here, I'm going to show you a notebook that is actually this example, running Hello World in Qiskit using Quantinum, that I already copied over. Now let me give ourselves a little more space to work with. Awesome. And these Hello World notebooks for all languages are designed on purpose so that you can run very simple code without thinking about the code itself, but rather they walk you through all the steps of using Azure Quantum. What happens here? So the logic is going to be the same for all languages and all environments. You have to start by connecting to the Azure Quantum workspace. The syntax is slightly different than we did in a Python C# notebook. But here, if you're running from a Python with Qiskit environment, you need to extract the list of backends separately. And it looks like this. You can see that here's the list of the backend results is longer. It contains both IonQ targets, which we have already used, so not going to go through them again, but also Quantinum targets. One thing that's slightly inconvenient is that it shows you both targets that are available right now and targets that are not available. So basically the thinking is that you can, in principle, submit a job to a target that it's not available. And once it comes back online, the job is going to actually run. Now for Quantinum, when we're running on their targets, there is an extra step of running the job through API validation. So here is going to be the Qiskit code we're going to run in this demo. Come on. I know I did that. Okay. I think I need to be honest and rerun all the cells. Right, because I left the notebook and got back to it, of course. So rerunning all the cells, no shortcuts. And now when I run this program, it's going to create this circuit and actually draw a little picture of this circuit. Now we can submit the program to one of Quantinum targets. The first of them is going to be the API val target. So we're going to submit this job. We're going to get the job ID back. And then we need to wait for the job to get results. We can monitor the results and get them like this. Again, since it's just API validation, not actually running the job, and it's very fast, the results make sense once you read up in the documentation that API validation doesn't do any simulation, but instead it always returns 0 as a result of execution. So basically, this reports us that yes, indeed, your program is going to run on Quantinum, and you can move on to the next steps. The next step is to do kind of sort of resource estimation, but a slightly different here. For Quantinum, you can actually estimate how many credits it's going to take to run your program, which at some point converts to the dollar cost of this program. So now let's run this job on the emulator. Let me, okay, emulator. Yeah, actually, I think I'm going to pull up the results from yesterday's emulator run as well. Or maybe be adventurous and actually run it. Let's actually run it. So S2Sim is the emulator, the noisy emulator of the Quantinum H12 device. So we can run the job on emulator and get the job results. And now we're going to be monitoring this job. So right now the job is queued. Let's see if I can take a peek at job management without leaving this notebook. Yeah, so you can see here the jobs I submitted right now for API validation that succeeded and for simulation that is still running. You can see that the previous simulation job I submitted ran from 17, so a bit over a minute. So we're going to have to wait a little for this result. But, you know, that's what you have with quantum computing in a cloud. And it's not like I would be able to bring up a quantum computer and put it right here for the demo. I actually went really fast through this demo. Usually it takes me a little more time, which means that on one hand, our job actually executed successfully. And you can see that I got a lot more zeros than ones. Could be noise, could be the results of randomness, could be the system trying to tell me something. But this is the workflow of how you can use Qiskit on Azure Quantum. So looks the same as using C# on Azure Quantum. Syntax is slightly different. Any questions so far? Okay, in this case, I think I'm going to take maybe 5-10 more minutes to show one more demo. That time when somebody at last year's summer school asked me about noise simulation in the QDK. For some reason, was a particularly memorable question. I don't remember all questions I get asked. So I'm going to really quickly show you how to run the noisy simulator with C#. And then, unless you will come up with some questions at that point, then we'll call it a day. Sounds good? Okay, so one of the simulators in Quantum Development Kit is Open System Simulator that allows you to use a QTIP library to simulate noisy systems and their impact on execution of C# programs. So this is again a Python notebook that's going to run C# as a language as a quantum programs. So here is how you can define channels using QTIP. So basically, a channel is something that may or may not introduce the error into the computation. I'm pretty sure that if you worked with QTIP at any point in your life, you know more about it than I do. So let's see how to set up different noise models with this noise simulator and how these noise models are going to affect Q-sharp programs. We'll start with a slightly more complicated program, actually, teleportation. Here, I'm showing you yet another way to work with Q-sharp. You can actually embed Q-sharp code in Python notebooks. It's not something I do often because it doesn't allow you all the nice tools that can be used for Q-sharp development. But if you really need to have all your demo in a single place, it's a good way to do it. So once we have defined the teleportation program, let's see if my kernel is still alive here. Yep. So it's not going to tell you anything as a result, but it has actually defined the Q-sharp program for you. Now, if you run teleportation without any noise using the .simulate method, like I showed you earlier in the demo, it's going to run the full state simulation for you. Perfect results, success is always happening. But now, let's say that all our gates are perfect except the Hadamard gate. And the Hadamard gate has bit flip noise with some probability. So how we do that? We say enable noisy simulation. And then we define the noise model we're going to use. Get noise model is the default noise model, which is no noise. But then for the H gate, we're going to change the definition. It's going to do the normal Hadamard transform. But after that, it's going to apply an X gate in 1% of the cases and leave the gate alone in 99% of the cases. And once you have defined this noise model, you set this noise model, and now the open system simulator is going to use it when it runs. And now when you do run the noise simulator using this .simulate noise method, when you run this cell, you see that you're running it more times to see the results in a more pronounced manner. Now you see that you don't get 100% success rate for teleportation. Instead, you get like 85% success. But this was a complicated model. And we can see some noise models on smaller programs that show us better how to, that allow us to observe impacts of different types of noise closer. So here is an example of dephasing noise, the noise that applies the Z gate with some probability instead of the X gate. So here you do it the same way. You get noise model, the ideal computation. Then you say that again with the pool Hadamard gate, it gets applied a C gate now in 10% of the cases. And then you set this noise model. Now you define a simpler program, Deutsch algorithm, which still has 4 Hadamard gates. And then you compare the results of running without noise. 100 runs out of 100, you get correct answers Okay, I think I messed up the operation names here. Oh, right. So you're asking if the oracle is balanced, and here you're checking if the answer is false for the oracle no op that implements the function equals 0. So the correct answer is false. Okay, nothing messed up here. But now if you run it with noise, you're going to get a failure rate of something around 10%. Another noise you can define is that you can define amplitude damping noise that with certain probability replaces any state with the 0 state. And for this kind of noise, here you spell out the matrix that defines the channel of this that implements this noise manually. And a good example to show of this example, this kind of noise, is the program that checks whether the result is 0 or not, so random number generation. And when we run the random number generation normally, we should get something like 50-50 split between zeros and ones. But since our Hadamard gate is now followed by the noise that in 30% of the cases converts your result into 0, you see that we're not going to get a result close to 50, let alone more than 50. It hangs around 30 something, doesn't even reach 40. Now the final one, let's try and set up different noise models for different gates. We're going to define a Q-sharp code that allocates 2 qubits and prepares the Bell state on them, 0, 0, plus 1, 1, and then measures the results. Now, if you're running this code perfectly on the simulation, you're going to get perfectly correlated results of measurements. They're going to be 0, 0 or 1, 1. And you're going to get both of them with approximately the same results. But now let's try and run and use 2 noise models. One for Hadamard gate that's going to do the amplitude damping, the converting of the state into the 0 state with some probability. And the other one for the CNOT gate that's going to do the bit flip on the second qubit after the CNOT gate runs. And we can run those separately. So let's first define just the amplitude damping channel on the Hadamard gate and see what happens. So since the Hadamard gate is applied before the CNOT gate, if the error happens, it means that the 0, 0 measurement, it means the system, instead of becoming 0 plus 1 before applying the CNOT, it remains in the 0 state. And this means that in these cases, the CNOT gate isn't going to change the state of the system. So 0, 0 measurement results are going to become more frequent than 1, 1 measurement results, which is what we see here on the plot. Now, if instead we use a different noise model, the CNOT noise only, the bit flip on the second bit, when this happens, it means that we get not just 0, 0 and 1, 1 results, but also ones in which the bits are different. And indeed, this is what we see. We got those 1, 0 and 0, 1 results with some probabilities. And now, if we enable both noise models, we're going to see both of these results. On one hand, 0, 0 is going to have higher probabilities than 1, 1. And on the other hand, 1, 0 and 0, 1 are going to make an appearance with the probability of 0, 1 being higher than that of 1, 0, which is still that part of Hadamard gate result. Noise on the Hadamard gate result. So this is, well, a very belated answer to the question I was asked a year ago. I'm probably not encouraging you to ask me questions, am I? And this is actually the end of the demos I had for you today. One last thing I have is a bunch of resources if you want to follow up, learn about our program, the work we're doing, the news we're pushing out. And there is my Twitter account if you're curious what else I'm working on. And that's it. Thank you for listening, and let me know if you have any questions.
Hi. So for the noise model, it seems like you're attaching the channel to a gate. Is there an option to, let's say, model dephasing over time, like just like, you know, attach it to the identity, I guess, or attach it to some time?
Yeah, I'm not actually sure what different kinds of models are implemented right now. This demo is a little old, and I didn't plan actually to go over it today. The quantum development kit documentation should list the things that are possible and not possible to do with it.
The experimental here points to that it's in some beta phase, I guess. It was in the experimental package.
Sorry, I'm not catching it.
It mentioned that it was experimental in the imports or something. Does that mean it's still in development?
It basically means that it's less mature, and as we work on it, it can break in unexpected ways. So basically, the APIs can change for interacting with it.
Okay, thanks.
Question?
You can also follow up with me off the record. I will be here for some more minutes.
All right, seeing no more questions, let's thank our speaker one more time. I think dinner's set to come at 5:30, 5:45. So it looks like we have a short break until 5:45. See you then.
It's in here.
There's like 50 people.
I know. We can all like take them.
Yeah. That'll be my food.
Are you in need of milk? So I'm about to leave for like 3 weeks, and I have a full jug of milk, full jug of 1% milk.
I'm leaving on Friday and I still have my fridge. So
I keep meaning to eat cereal, but and then I come here and eat whatever's on.
I was telling David, I have a fridge full of food. All my meals are provided by QSC this week, so it's all going to come back.
Yep.
Okay, it says full batteries.
Just getting set up. But in the meantime, we are being encouraged to coalesce within the first 4 to 5 rows. So those of you up at the top, welcome to scooch in and get comfortable. Should be a more intimate little dinner storytelling seminar.
I mean, in person, we've had 70 people actually in the lecture hall. Yeah. Yeah.
You got it. Hello. Am I on? All right.
Hello? Am I hot? Am I on? Yeah.
Is he?
Hello?
Yeah, I think we can
Good,
hear you.
good, thank
Okay,
you.
A little bit of reverb going on.
The acoustics.
It is a bit odd. Yeah. Okay. All right. All right. Okay. So, want to start page one?
Sure.
Go back to page one. All right.
Yeah.
Okay. So we'll just introduce ourselves. I'm going to title and then.
I'll be back another.
Okay. All right. Good evening and welcome. Do you want me to start right now?
I said we wait
1 minute. Okay.
Oh.
Oh, you'll introduce. Thank you. All right. That's perfect. Yeah, it's always awkward to introduce oneself. All right. Yeah, thank you. Oh, appreciate it. Yeah, of course.
All right, I think we can begin now. Welcome everyone to the dinner workshop on the Quantum Science Center Summer School on Science Communication Workshop. And workshop is given by two special guests, by Professor Zoran Matei. Professor Zoran Matei is a professor at the College of Liberal Arts and Associated Dean of Research and Graduate Education and Professor of Communication of the Brian Lamb School of Communication at Purdue University. Professor Matei studies the relationship between information technology, group behavior, and social structures. And also with him today is Dr. Neil Dilley. He's a physicist specializing in cryogenic measurements and design. And his current research interests are in magnetic materials discovery, spintronics, and nanomagnetism. So welcome to the summer school, and we're looking forward to your workshop. Thank you.
Thank you.
Thank you very much. Yeah, so I'm Neil, and we're here with Soren and also Blake Wilson, who's a QSC graduate student. And here you are, you got your mic there. Wonderful. And we'll all be taking turns here. We all have our own specialties, and this narrative engaged science storytelling is something that is Soren's specialty. And I'm really honored to be able to be up here and sharing the stage as a scientist and sharing my experiences and my perspective. And we have the benefit of having Blake, who's going to demonstrate some of these principles in a sort of a vignette, a portion of his research in a new talk. And so we call this seeing your research as a dramatic narrative. And we're going to compel you guys to feel that this is a very important thing. And we're going to show how the storytelling elements that we know as storytelling are very relevant in our research in going forward. So we're going to Start off with a science story. Soren's going to tell one that he often tells, which is a great example of how science stories work. And then I'll talk about finding your story. You know, where is the story in your research? And that's not always obvious. And simple question, why? Why are you presenting at any given point? It has to do with you and your audience. And then about the story structure. This is something that Soren studied a lot. We are going to have a presentation of the narrative structure of a story and how to fit this together. And the idea of a transformative metaphor, we'll explore that. And then another science story, and that's going to be from Blake. So it will be close to home for the QSC. We'll continue on. Soren will explore some science metaphors in the field of computing and have some fun with this. And I'd like to wrap up with a reference to Aristotle's rhetoric and as a toolbox, because you want to go away from this with some tools, some ideas to how practically do it. We're not going to be storytellers of Soren's caliber at the end of this. It's a rare talent. And but we can learn these crafts, and that's one of the things that we're trying to learn how to convey in these talks. And my overarching message here that we all want to share is that stories deliver us to new heights with better explanations, and that really is the key to driving it. So let's talk about a story, a science story.
All right, Neil, thank you so very much. My key proposition to you today is this: science is storytelling ready. Let me put it this other way. The scientific process has all the elements needed to tell a story. Now, why is that so? Because, and I'll give it all away right now, because stories, all good stories, work their magic by violating expectations and then putting something else instead. Think about any mystery crime movie we've ever watched. I don't know if you're old enough to remember Columbo, right? The Columbo series always started with a crime that's been committed where, you're given some clues, and by the end of the day, you'll learn that all your clues were wrong. That's why you watch the story, the episode, kind of figure out how you were wrong, right? All good stories violate expectations and put something in place. All good science, and you probably know this better than I do, all good science that gives you tenure, right, and grants and all that, works by violating expectations. You don't violate anybody's expectation, your science is not as meritorious as the science of somebody who did violate expectations. Now, I'm talking here about the scientific process that works at the highest level, right? Not just about, the drudgery everyday life. There's that too, I understand. And that's about making your boss, your PI happy. I understand that. Not violating her expectations, I understand that. But when it comes to getting the grant, to moving science, to getting published in Science and Nature, you better have some expectations to violate. Now, let me illustrate to you how this idea works in the real world. Let's recount, and I'll try to make it quick, although it's a great story and I like to tell it. Maybe I'll take a little bit of time. Let's recount the story of understanding the universe, the story of astronomy as a science. And let's start way, way back in prehistoric times, not historic times, prehistoric times, when the first observer of the sky asked the question, what does the sun do and why does it do what it does? Right? And asked this question not in a mystical, mythical, religious way, the way his ancestors asked it, and they answer because it's a god, because it's spirit, because it's not your business to meddle with things you cannot understand. But, this person asked this question in a way in which he or she wanted to answer it in a rational way, in a way that is satisfying and is self-sufficient. There was a time in the history of humanity when people wanted to know things just for the sake of knowing them, rather than, running to religion and to other things. What did this person do, you think? So, observe, right? What did she do? She decided to wake up in the morning, look, see the sky, draw a line in the sand, right? And look again. A couple of hours later, did not have hours. She went gathering something, came back, look, okay, sun is about that high, drew another line, and maybe another sign to show how high the sun is in the sky. Went one more period and the other period, and ended up having a very nice semicircle drawn in on the ground, right? So this, again, the question of this person was, what does the sun do? And let's answer the question without any recourse to what we already know, which is that some God, some spirit, something doing something. The person looks, conclusion. What is the conclusion, you think? The sun moves around the earth, correct? It's what your empirical evidence tells you. The person behaved like a scientist and he got back a scientific answer. There's a thing up in the sky that's hot and round and moves around the earth. From here, this person thinking a little bit more is like, what does the sun do at night? Maybe it goes around the earth, right? Maybe the earth is around itself. Then, it means that there's, in this universe of ours, has the earth in its center and the sun moving around it. Is this rational, reasonable? Well, let's look at the sky at night. Now look at the sky at night. What do you see there? These stars, right? And they all seem to kind of be moving in the same way from one side to another. It's like this. So the sun and the skies of the night, I don't know why those flickering things are up there. They kind of move around the earth in a regular way that assumes that the earth is in the center of the universe. What did the moon do? Well, that was a little bit more complicated, but somehow they reconciled with them with the idea that if the sun does this and if the skies do that, and the moon, is just kind of following along. There's a problem here because the moon doesn't exactly move the same way as the sun. But somehow they said, let's call this the error term. It's like our equation did not account for it yet. However, after some hundreds or thousands of years of observations, some very, very, very anal retentive scribes in Babylonia had a little bit more time because they did not have to hunt all day. All they had to do is just observe the sky and propitiate the gods and all that, right? They have a lot of time on their hands. Our colleagues, our ancient colleagues, right? Paid to think. They looked at the sky and looked at the sky and looked at the skies. Then they noticed that actually not only the moon moves, this bizarre way. There are some pinpoints of light in the sky that half of the year move this way, and then all of a sudden they turn around as if it were a cartoon. And they down and came up with some theories which led later to astrology. Their theory was that these stars that move this bizarre way, actually, they are not stars at all. They are spirits. They brought religion back into it. This is now, human reason alone cannot explain. We need to bring some spirituality, as they call it. And these stars that move like this, these are spirits. And the way in which these spirits align with each other, guess what? They have an influence on us. And if you are born under a certain configuration of these wandering stars, your fate will be like this and all that. They build a whole entire, quasi-scientific method of predicting the future called astrology, right? And, that kind of worked for a while. We had, the scientific explanation. We had a pseudoscientific explanation. It was all suffused with religion and all that. And it kind of worked for everybody in a good way. Until somebody was really not happy with this. They had the same aha moment as our deep ancestors. Like, listen, religion is good. But, is there a really reasonable way to explain what's going on? Let me look again at the sky. So what's our assumption? Again, our assumption is that the Earth is in the center of the universe and everything revolves around it. except for these planets and except for the moon. If I were to use my mind alone, would there be any way to explain this wandering movement of these stars and of the moon by reason alone? And by the way, these wandering stars in the language of the time, which was Greek, was wanderers, which in Greek is planet. So this person thought and thought, and we don't know if it was an aha moment or it was some other type of reasoning, but it was as if solving a Rubik cube problem, right? And you kind of figure out that if you just look at the problem this way, everything falls into place. It's actually that bench moment, right? When you say, man, I'm doing something wrong here. You know, it's not the instrumentation. It's not the experiment itself. It's just the way I'm looking at it. And this person said, you know what the problem is? The problem is that I'm trying too hard to fit all the available data within the same assumptions. Maybe my problem is not the data. Maybe the problem is the assumption. So what is the assumption I need to meddle with? With a fundamental assumption. Why should the Earth be in the center of the universe when so many things don't fit around it? How about we put the thing that seems to be the most important in the sky, the sun, in the center of the universe, and with the Earth moving around it, then we consider those planets as a type of Earth. With the observations now mapped onto a orbit system where the Earth and the planets move around the Earth, and as the Earth moves at a certain speed, you know, it sometimes passes, sometimes lags the planets, which explains the retrograde movement. Bingo. Yes, it does. If we build astronomical charts out of this model, all of a sudden things start kind of falling into place. There will still be some error terms, right? Not all the planets ran at the same course. What was the problem? Do you know what the problem was? This model was a circular orbit model, right? What did that person miss? The fact that the orbits are elliptical, right? And it took actually Kepler and their friends to kind of fix the mistake, right? So, you know, we changed one assumption, we got a better model. Our model wasn't good enough still because we used an assumption about the orbits. The moment we changed that with the elliptical orbit, we had an even better one, right? Now, I'll go no further than this, because then we start with quantum mechanics, which is a different story. But you see how science as a process of thinking about the world, of observing, of trying to fit data within assumptions, right? And it leads to stories, right? Which is the story of explaining that which doesn't quite fit in yet, which once you create the story, opens up the possibility of another story, because not all the data will actually fit in the new story either. That's why I'm saying that science as a process is storytelling ready, because it relies on the assumption that nothing is known forever and for good. And it invites you to violate expectations. When you do this, you actually trigger a series of explanations. And these explanations should always take the form of a story, because all stories work the same way. Now, I'm not going to give you an example of a good story that violates expectations, because we don't have enough time. But I have a YouTube channel, who doesn't nowadays, where I have a story of a queen who does something that's unexpected, which I hope you recognize as a story, okay? I'll stop here, and I'll come back with a few more insights about how stories really work, other than violating expectations. But I'll turn it into to Neil for now.
Thank you, Soren. So there you see a story that we know the beginning, we know where we are now. And in retrospect, we can see very clearly, well, this makes more sense. We are in science stories that are in the process of developing. We're somewhere in that arrow. And so the question is, where is your research story? Right? You have a research story. That's what research is, as Soren has so nicely explained. And I was thinking about this and how we're going to get this across. And I came across this a few weeks ago, this New Yorker cartoon You know, there's this guy, you can see what's going on here, right? He thinks he's got something to show and wait a minute. There's something else going on there that he hadn't even thought about. Where's the story there, right? And so in looking for that, something that might be obvious to you, or you think that this is the contribution, you may need to dig deeper. And you always need to look for this sign of what is threatening to violate expectations. What might turn things over, not maybe in my work this week, but in the field. What direction are we going? How is quantum computing going to overthrow things? And to see ourselves in this process. So finding that research story, looking deeper, and of course, you know, we're always telling you here in this whole thing about telling stories, you know, and I could believe it if you look at us and you say, well, I'm not sure I'm supposed to be a storyteller up there. I'm a scientist or an engineer. I'm conveying information to a learned audience. I'm trying to convey certainty and nail down some things in progress. But let me tell you why I think stories are so important. And those are the things that drive what you're doing, the reason why you're presenting. You know, why are you talking to this audience? Well, first of all, you need to know what your audience is. And you really, in the end, I would claim, want to have your message received and remembered and your story to be taken on. And you know, the things that make up memorable and received things are messages that educate, that stir new thought, and inspire delight. And I don't use that word lightly because it is, in fact, so important in the sense that a story or a research effort is a product of someone's imagination. You know, science is a process of eliminating things. And we get so caught up in this aspect of elimination and ruling out and negation that we forget sometimes that the creative moment that is the source of all of this is the imagination of one person, and your ability to connect your imagination with that of somebody else in a presentation is this golden thread. And that's what we're kind of getting at. And so I think we all relate to it because we all relate to stories as people. And the audience you're going to talk to is not computers, they are also people. So they need to have their imaginations stirred by this. And
So
so,
I may add one word here.
go ahead.
Now, education, stirring new thoughts, delighting. All those things demand that you first shake the audience up a little bit. How do you do that? By violating the expectations, right? So all these verbs, educate, stir, they're kind of positive, you know, connect, imagination, they're positive things. But you cannot do that unless you start by grabbing the audience, right? By the lapels. You can only do it by telling them what you thought was wrong. Let me tell you how it is. And that's where the education process starts.
Yes, yeah, right. Grab them gently by the lapels. Maybe not gently, I don't know. So now we get into the how. You know, how are you going to do this? What's the mechanism for this? And this is where Soren will take it and show you an idea about a story narrative. So you can take this diagram from here.
So, just as I said, science is a journey, right? It's a journey. It's a journey from what we know to things that we want to know, things that we don't quite know yet, but we want to provide a better explanation for. Right? Science is a quest for answers regarding things that we can't quite explain yet. Now, when we start today, you know, with our mature, more advanced scientific knowledge than our ancestors had. I don't know if we'll reach maturity yet. You know, I watch a lot of Star Trek, you know, there's probably a lot more into it. But, you know, right, we do have a body of scientific knowledge, right? So we have a body of established scientific knowledge, right? So when you engage in science communication and science storytelling, you as advanced scientists, and I'm talking here not to teachers, elementary school teachers who do a fantastic job. I'm talking about people who do high science, right? When you engage in, you know, neuroscience, you deal in highly technical matters, highly technical concepts and cutting edge research that's kind of known to you and your peers. And you feel like, you are kind of in the bubble, in the zone, right? And your journey is kind of limited what everybody knows. However, we live in an era where, there's accumulated knowledge that led to your knowledge. And most people actually don't work at your level. Most people out there work at a common science knowledge, right? So when you want to tell them a story about what you do, about the interesting cutting edge things you do, what should you do? Well, the very first thing you need to determine is where the audience is and start the journey there, right? So what I'm trying to say is that there are two paths for traveling the scientific, to take two paths on which you can take the scientific journey. There is the A to B, the common scientific knowledge path, where people know some things in certain ways, where they have some assumptions, some of them which you don't think are quite okay, but they're good enough for the masses, and they work. And then there's the C to D. It's your world, right? Where you know that we know some things, and we want to get to D, which is where we'll know even more. And it's all technical, all very bubbly, all very gauzy, and all that. And in explaining what's going on to you and your peers, you only think about C and D. You forget about A and B. When you are invited to tell the story of your research to the world, right? What you typically do, you're high up there, perched on that hill, right? C to D, and just dispense to people, scientific, specialized knowledge, maybe translated, trying that they will catch up with you. That's not the way to do it. The way to do it is this. You start at A, where everybody is. You're not there in your work. You're actually at C. But the story doesn't start at C. The story starts at A. Start at A, where everybody is. And you recount with everybody, you're like, on the train station, tell everybody, we're going to take you on a great science journey. And you all want to get to B, right? It's where you think we'll go, because, this journey is about knowing these things that you kind of know about, and you think that I'll reconfirm them. Yeah, sure, maybe. Let's get on the train and let's see what we discover, right? I know that you know this. I know what you know. I know you want to get to B. I kind of agree with you, but let's get on the train and I'll explain to you what's going on. I'll play tour guide to you. So get on the train, you travel a short distance, and then all of a sudden, you pull the lever. You switch tracks, and instead of keep going on the trodden path where everybody knows where the story will end, you switch from A to B on this path that goes up the hill and takes you the hill of discovery, where you violate expectations and switch gears. Basically, you tell the audience, you knew this much, but actually it's more like this rather than like that. Now, no, don't get scared. What I'm going to show you still fits in that model, but it's a new way of understanding things. And I'll explain to you how this new way is by storytelling through, we did not put it there, and we're going to get to it in a second, storytelling through a transformative metaphor. So I'm going to tell you how what we will see and will do can fit into this metaphor that will change the way you think about things, right? And then you get, the audience engaged in the transformative metaphor storytelling. They'll ask you more questions, and before they know it, they are at D, where you want them to be.
Sorry.
Now, so that I don't lose you here, a typical good explanation for this, or a good example of this, would be explaining to high school students the model of the atom, right? Yeah, all your students, depends what schools they went to. Maybe they went to some genius schools, they'll know. But very many of them will come in with a solar system model of the atom, right? There's the protons and neutrons in the center, and then the electrons, like the planets moving around and all that. Makes all the sense in the world, right? So yeah, it is like that. It's just that, although they are electrons and we can measure them and they have, characteristics that we can't quite put our finger on it. We don't know exactly where they are. And actually, they're not exactly things that you can touch. They're more like little clouds. So, and then you get to your other, energy bands explanation of how, the atom works. I don't know what your transformative metaphor will be, maybe you'll say it's actually, our atoms are not like the solar system. Maybe they're maybe like Jupiter, right? A very small core and a lot of clouds around it, where the electrons could be any of the swirls that move around the planet, and that will help you tell the story. Okay, all right. This is one little example of how you can use violation of expectations to switch people from what they know to something that they need to know. And in doing so, you engage, excite, and also allow you to bring in this transformative metaphor, which is very important in this model of storytelling. Now, Blake here will give you an example of a transformative metaphor that would work in this context. Okay, and I'll let him tell us more about it.
Hey guys. Some of you know what's about to happen. I've given this talk a couple times. The story behind this talk, Vahag and I were talking one night several months ago. Wave Vahag so people know who you are. We were talking a couple months ago about the nature of the universe, or the Quantum Science Center, where the heck does quantum mechanics come from, all of that fun stuff, right? And we'd had a thought, and I silently kind of worked on this thought for a little bit, and then recruited Ethan over here to help me work on it a little bit, and an undergraduate student in our group. Basically, we kind of had the idea of, if quantum mechanics seems to happen so quickly, what if it happened, what if there was a way to freeze the universe, perform quantum mechanics classically, and then restart the universe again? And you kind of keep iterating forward, and there's no notion of this weirdness of quantum mechanics. So essentially, is the universe simulated by a classical computer? Could you ever prove that it wasn't, right? And the pop culture reference for this is The Matrix. How many of you have seen The Matrix and know what it's about? It's very popular, right? The idea is Neo, our protagonist, and the rest of humanity, except for a small group of people, are essentially stuck in this philosophical idea called a brain in a vat. Basically, your brain is in a vat, and you're hooked up to some computer that's simulating your interaction with the rest of the world, right? Does anybody know what the issue with this philosophical interpretation is? Off the top of your head. There are several. One, it's not really mathematically rigorous by any means. You're putting a brain in a vat. Two, what happens if an error happens? Can you detect it? Probably. They call them glitches in the Matrix in the movie, right? You see a black cat walk across, and you see it happen again, or deja vu, things we experience, right? And the main problem is oftentimes when people have this kind of simulation theory idea, they're thinking about a classical computer, okay? What if quantum computing works out, as we all hope it does, right? And we get these amazing speedups. Could a classical computer actually simulate these quantum speedups from our perspective, okay? Even if it's classical. And it turns out that yes, it can. And how you arrive at that is actually using special relativity. Imagine time dilation so extreme that 1 second of your time is a gajillion seconds of some other frame. And in that gajillion seconds, you could perform quantum mechanics classically on a classical computer. And then in that 1 second, you can't perceive the gajillion seconds happening around you because in your inertial frame, only 1 second has gone by, right? That's the generic idea. In the actual work that we did, it's not quite that hand-wavy at all. We prove it with classical Turing machines. Essentially, you have two separate machines. You have an AI and a classical computer. And we don't include quantum mechanics really at all until the end, right? But we were kind of looking at it from an AI perspective, more on the simulation theory side, but it applies well to quantum mechanics too. Can an AI perceive the amount of time that's happening around it, or the space that's happening around it, or the error it's being computed with? Turns out all of these are undecidable problems in the same sense as the halting problem. And so from that perspective, special relativity can kind of emerge from this relative Turing machine classical computers.
Right. Yeah. Thank you, Blake.
Now, so that we ensure continuity. The transformative metaphor here, by the way, was the universe as a simulation, right? Which was meant to help you reimagine how the universe works, right? Now, he went one step further, said there's actually an even better transformative metaphor, which is this speeded up universe as seen as a simulation, right? So we're at two levels of transformative metaphors, which were kind of posed to the idea that the universe is something that is, objective. There are objects that are there that exist in different of our existence, right? The universe as a simulation says, no, actually, the observability of the universe and how it works is a part of it, which begs the question of who observes and, what's going on and what's the difference between information and representation. All right.
Great. So that gives us a segue back to Soren, who will explore other metaphors in the field of computing. And so this is a sort of a sandbox time. We're going to try out some other ideas of transformative metaphors, sort of to loosen up ideas. And we're interested in getting feedback. So let's let you riff on this a little bit.
Okay. Now, I know you know all about computers much more than I do. Right? Who here writes code? Good. All right. You know CPUs and all that, right? Now, pretend for a minute that you knew about computers what everyday Joe, Jane knows about, right? Which is something magical, mystical. It has some chip inside that does stuff. My job now is to explain to you how a computer really works. To work with you and everybody else, I need to come up with a good transformative metaphor, right? And also violate some expectations. Right? And what I will tell you is this: a computer is no more, no less complex than a set of chained out water closets, toilets. A computer performs the same functions that an equal number of toilets connected to each other could perform. If the water coming from a toilet connects to the lever to the next toilet. Make sense? What's a toilet in this example? Toilet is a what? It's a gate. It's a transistor, right? A toilet is a transistor that stores one bit of information, right? There's water or no water in the tank, right? Pressed or not the lever, right? And we can calculate, and actually, literally, you can calculate stuff with a sufficient number of toilets, right? If you think about it. Well, this is the other way put, that actually digital computers that rely on Boolean binary logic, right? And numeric systems can be implemented in non-electronic devices, correct? Or non-electronic the way we have them today. I don't know if anybody's old enough from Eastern Europe here to remember that there was a time where people dabbled and tried their luck at creating electromechanical computers. Did you know that? Before we had these computers today, we had electromechanical computers, right? Right? We actually had a steam-powered computer, if you can believe it or not. You know that? You know that, right? Who was the fellow who invented that? It's famous. You go to Palo Alto, San Jose, right? The Computing Museum, they have a reconstruction. Babbage, right? And you know that the first programmer of that computer was a woman who wrote the code on cards that looks like ours, only that she stole the cards from the looms that they used to weave very complex patterns. So the idea of encoding information as wholes, of punches, zeros, and ones did not appear in 1950s. It preceded the IBM computers by about 150 years and was first used in the textile industry. So computing using gates, logical gates, can be imagined as any collection of physical objects that can physically store in them one of two states, whatever those states might be, right? Makes sense? And then, you can explain how it works, how you can create a not gate, or gate, whatever gate. Read Bill Gates's book. What was it? the road ahead, if I remember correctly, you'll get a good education. No, you don't need it. You give it to your kids, if you ever struggle with their love for computing, right? All right, makes sense. All everything works, accessible on the line. Good transformative metaphor, right? Chained out toilets, right? And by the way, this metaphor also works well for explaining to people why the first principle of computing is GIGO. GIGO, remember that principle? Remember that? What does it mean? Garbage in, garbage, right? You know what I mean? Toilets, garbage in, garbage out, right? Yeah, makes sense, right? Crap in, crap out. Right? Okay, how about quantum computing? Now, I don't know if you remember, Trudeau, the Prime Minister of Canada, right? Actually, he kind of pretended he's smart. He knows what a qubit is, and it's either 0 or 1 or 0 and 1. So you remember? Do you remember that little incident? He was asked what a qubit is, and he riffed. Well, the problem is that him and as many other people who are trying to explain quantum computing, they fall back on our present transformative metaphor, and they try to fit it in and say, well, it's all computers. There are logic gates that can be 0, that can be 1, that can be everything. But actually that, and you probably know it better than I do, that makes absolutely no sense, zero sense, either from an engineering or a scientific perspective, right? Actually, it is not true that the gates in and by themselves can store all possible information in the moment, right? If that were true, then the first law of logic that anything should be, 0 or 1, yes or no, or none other would break down. You cannot have anything. So quantum computing requires a very different way of thinking, first of all about the substratum, the thing that collects and instruments the information, which is not our logic gates. There are no logic gates the way I understand it in a quantum computer, right? That is well designed. What you have are states of energy, right? These wave patterns that store the information. And it is their movement in time. There's a time dimension to what they do that allows them to store all that information, right? Without the time dimension, you would not be able to do the magic of superposition, right? So I offer to you a better metaphor for explaining what quantum computing is. And my metaphor is the kaleidoscope. Familiar with kaleidoscopes? Have you played with one of these? Now, a kaleidoscope is a very physical object, right? It's made of a tube. Inside, there are intersecting walls plated by mirrors. And in the cells created by intersecting walls, mirror walls, there are beads, color beads. And if you hold the kaleidoscope in place, you have a configuration. Basically, your kaleidoscope holds a certain amount of information about the state of the beads and how the light comes and all that, right? Which is just, incontrovertible and deterministic, right? However, if you start moving the kaleidoscope, right? The information in the kaleidoscope, the information of what the light does, where the light is, changes every single moment. Actually, for the same beads, you have multiple types of light refractions. You have multiple types of information, right? So now imagine that this, the refractions, the light that is so moved is, your qubit information, right? That is all these various superposed states, right? And these will exist only as long as you move the kaleidoscope, right? Right? And that's where you store information. Now, there are much more complicated processes. You kind of keep track of what that does and instrument that as it works. And then to read your result, you do what? You stop the kaleidoscope and look at it, you observe, right? And you have your answer, right? Now, I don't pretend that this is a perfect explanation for what quantum computing as a computing solution is. But I propose that this is different enough from what we had before, and it's imaginative enough, and it violates enough expectations, right, to make people think at the very least, right? Now, I think that there's a little bit more to it. I think that there's some value in what I'm offering here. I think the time dimension is something that actually many people who try to explain quantum computing are blinded to. They don't think about it that way. They don't realize that many of us the people out here cannot even think, in terms of, things that change over time. And then we don't try to explain it to them. Right? But that being said, I think that this is a very good way to think about it. And Julie, we're going to come back at it, and I would like to hear your opinion about it and see if this holds water, or if not, can you provide a better transformative metaphor for quantum computing, right? That would be as elegant, but probably better, more accurate, more scientific than what we have.
Yeah, great.
Now,
Yes.
to recount a little bit. So what I offer to you here is a method of storytelling that relies on these steps. A, violate expectations. No, start from what people know. Start with A, station A. Recount with the audience what they know. Invite them to follow you on a journey toward what they thought they know. And then violate the expectations. Tell them that what they thought they knew is not so. Immediately offer them a better explanation. Offer this explanation in terms of a transformative metaphor. Now, a transformative metaphor is not just a fancy term. As I was trying to explain to you, a transformative metaphor starts with something that people can grasp, that people have interacted with, that people know of, right? Even for quantum computing, I try to offer you an object that you recognize, anybody on this planet recognizes. I have people I bet from everywhere, Africa, Asia, right? Everybody here has heard and seen our kaleidoscope. I hope I did not use some culturally charged metaphor, right? Yeah. So you need to connect with the audience by offering them something that they understand, that they can connect with, and then build on top of that your explanation. That should never forget to put a better causal explanation in it. So basically, there was the. Can you go back to the first one? You start.
Oh, this one?
There. You start with what people know. You take them on a gentle slope. You tell them you're taking them a place of comfort, and in time, as you explain, you actually end up here at point D, which gives you a much better view of everything, including where they started, including where high science is, including what is to be known.
Anyone know where this is? Recognize that? Switzerland. Brilliant. Thank you, Soren.
Thank you.
So a little bit about the toolkit. The principles of Aristotle's rhetoric, which people brought by us, our teachers did in school at some point in persuasive writing, are in fact really critical for these understanding the mechanisms here. Soren talks about these concepts of a transformative metaphor, but we need to appeal to all aspects of the person in conveying an idea. Of course, logos, a logical explanation that works and works better, given the data that we have, is critical, but pathos too. The feelings and understanding what people are prepared to receive and what not. And that's what some of this craft is coming in. And of course, the last element of rhetoric is ethos, is compelling them to do something. So you could say it like this. What do you want people to think, feel, and do after your presentation? And that should be a core element of when you're going to get up and give a talk. Yeah, I understand you have a group meeting talks every week to your group and you have incremental data. But when you're talking about delivering the substance of your research, of your progress, we do need to think about all these elements. And as scientists, we tend to be very heavy on the logos. But understanding that preparing the ground for a new idea, if it's going to be transformative, needs to be done in a way that is catalyzed by something. This transformative metaphor is one that brings that into focus, into reach. So did you want to add anything more while I'm on this topic of rhetoric?
To connect all the dots. You know what I was trying to communicate to you with my transformative metaphors? I was trying to reach all three goals. First of all, I was trying to talk to your mind, right? When the toilet example, I was trying to talk to your mind. I was like, a computer is a series of chained out logic gates. A logic gate is a very simple thing. It's a thing that could be an on or off, which a toilet is as well. And it's no more and no less complex than that. When I brought the toilet in, I started working on your pathos, on your feelings a little bit. I know that, it felt a little bit icky right? Like toilets and all, but this disconnect, this ick factor, right? Actually helped us a little bit. It made you perk up. So what's this guy talk? What's this toilet talk about? And I was working a little bit on your reverse psychology, right? I was trying to induce your sort of arousal by using, something that, you did not expect. The kaleidoscope as well used pathos a little bit. I don't know if you watch Mad Men. Have you watched Mad Men? There's a great episode there where, the guy, the salesperson reveals how a good salesperson really finds the best pitch. And that is working on people's emotions. In his case, he was going back to childhood nostalgia. That I can sell you this thing on account of the nostalgia that inspires. He was selling carousel projectors, right? With the kaleidoscope, I was trying to do the same thing. I was trying to bring out the nostalgia of being 3 or 2 and discovering the wonder of things that change shapes and forms in your hand. Maybe not. Maybe for some of you did, but I tried, right? So, transformative metaphors carry with them both cognitive and emotional load. The ethical aspect of it, I did not have as much in what I said. But there, every scientist, once she puts aside the things that she's discovered, needs to really think about the implications of what she's discovered and try to figure out if those implications can be used in a way that is detrimental to her fellow people. And she needs not to make the science fit anybody's values, and she needs to make sure that the science is not used to fit anybody's values. For example, I'll give you an example here, really quick. Evolutionary theory, you all believe in it, right? I don't know, many of you believe it. I hope, I don't. Yeah, but it's established theory, right? Big theory. We know how it works, right? And it says something very simple. All organisms adapt in time to better fit their environment, some better and some less adapted. And the ones that are less adapted go by the wayside, and better adapted, transform themselves, turn into niche species, and that's how we got here, basically, right? If you follow this logic, and there's nothing wrong in following this logic this way, scientifically, you'll come to the conclusion that there are better people than others, right? You will. Well, by the logic of science, better. This is called social Darwinism, right? Social Darwinism. It was used actually by people in the 20th century to kill other people. Because, science told us, we better, you worse, right? Now, the problem here is that this discovery, even if it were true, we don't know exactly. You can really put some people in one category by their adaptability. But even if it were true, it has nothing to do with our ethics, because our ethics is not rooted in that theory. Our ethics is rooted in the theory of equal dignity of all human life. That is what I hope we all believe as humans, right? We are all the same. We are all humans. We're all made of the same blood and flesh and genetic material. There's no difference between me and you. Now, maybe you are better adapted than I am in some sort of ways. And maybe, even if you are smarter than me, maybe I'm more polite than you. Maybe I'm better with people. Maybe I can take care of kids better than you do. I don't know. It's very hard to make direct ethical inferences about people on the basis of measuring, some physical abilities, physical cognitive ability. You know what I mean? So ethics has a very important role to play, and it's not something that's shoved in. It's something that should be part of what you do.
All right, thank you. Thank you for that. Not thank you for stopping. This is really, really great. I'm going to put in a brief plug for both of our programs here. I'm a research scientist at Berkeley Nanotechnology, and I work with many of you and really enjoy it. This stuff of what we're talking about are going to be tried out in the summer in workshops that I'm doing together with our NSAC colleagues, those Nanoscience Student Advisory Council. And I look forward to more of this. Being a research scientist, being very close to what you do, I'm trying to be a catalyst toward this and to show you that the storytelling act is something so important for our enterprise, and especially as we go out into spreading this, because the world needs to understand quantum better. And we really need to message that and find creative new ways of bringing that to people and helping them receive it. And that's my plug for what I'm doing. And I also wanted to mention Soren's program on data storytelling. You can talk more about that.
Well, you can find me online 3 different ways. You can search for me on YouTube and you're going to find the playlist there about data storytelling. About 13 videos, 3 minutes each is with fun animations. More of this stuff, funnier too. Okay. Second, I wrote the paper. It's called Data Storytelling is Not Storytelling with Data. I hope it's fun as my presentation. It has a great example from the history of medicine. It speaks mostly about data science, but it's science still. And third, we have created on non-credit online program that certifies us as data and science storytellers at Purdue Online. And that's a 3-mini course program that will walk you through some of this stuff, will give you an opportunity to practice this art of storytelling, transformative metaphors, and all that kind of stuff.
Thank you. All right. So we want to now just pause right now and thank you for all your attention. And we hope you enjoyed this and we'll start a discussion here. So thank you very much for your discussion. And to go back, if you are willing to give us some of your ideas and bounce your own thoughts off us about our attempts at these metaphors, these transformative metaphors. Blake had a very interesting one, his relativistic speed up idea. I'd love to hear more about that. And the quantum computing metaphor, the kaleidoscope, I think is really interesting and compelling. And to me, it gets to that core element that you wanted to convey, and that's the time dimension. And so every metaphor you use is going to be limited. But you think about how is this metaphor going to clarify one aspect that I want to bring and I want to catalyze and bring it to people. And so I'm sure you all have a lot of thoughts about quantum computing. And if you don't agree with us, that's exciting too. So please let us know what your, if anyone has any other models for the quantum computer metaphor.
Yeah, actually, I would really like to hear a better metaphor that explains it even better. What a quantum computer is, or a qubit is, and how it works, and how it's different. Actually, what it is, it's okay. But how it's different, that's where the real money is.
It may not be just one model. It could be many different kinds of quantum computers.
Yours, or hers, or his, or hers, or whoever.
So it's after dinner, though.
Or any other thought.
Blake, any other thoughts you wanted to share with us?
Quantum computing metaphors? Honestly, this is like the hardest part of our jobs, right? Explaining what a quantum computer is and why it's useful.
Balls, like glass balls? Boxes.
Balls in a box, yeah.
Solid or hollow? Solid, very important. Okay.
And then it's the state, basically. Each start mixing them. Yeah. You shake them and before measuring, before taking them out from the box and measuring, you don't know what's the temperature of each of your bits. So they're in a superposition state. So you can think about superposition at least in this method. You don't know which ball is what because they're identical unless you touch them, unless you measure them. So that's the notion of the measurement basically. Before you measure, you don't know what's the state, what's the arrangement of your temperature in the box.
So the average person would ask us, what good is it?
And where are the balls?
How are you
Do you really guys use balls? Do you use balls? Are they balls?
It's the qubits, basically. The qubits,
yes.
yes,
Qubits.
right,
But
yeah.
how do you obtain those qubits?
What do you mean? You just initially prepare them. You heat them up separately. Each one has specific state. Then you mix them up.
No, I'm playing the game here. Okay, so I'm just playing. So when you have, when a physical quantum computer has a way to heat things up in a different way and.
Mhm. Using temperature as a proxy for something else,
Okay.
some other kind
Okay,
of.
so there's some temperature involved.
Yes.
Okay.
Initially, you know the temperature, basically, and then you mix them so they can exchange the information, and then you have to measure to know what's the outcome after this mixing, this interaction.
Okay, yeah.
Before that, you don't know anything about the system. So they're in this superposition state. They're in the box.
Now, I like this very much, but this is an explanation of how computing as a process works. You know, this is like trying to explain how, you know, binary, you know, logic works.
It's information. You know something about that being this way or not being this way.
No. What I'm trying to say is that when people ask you or ask me or anybody what a quantum computer is, they want to start from the ground up. They really want to put their arms around it completely, right? Before they get, and especially around the thing, you know, because they see all these pictures on TV and all these, you know, alien stalactites, you know, the D wave, you know, looks like the stalactite, you know, that's just hanging from the ceiling. And it's like, where is the computer? Where did the computer, is it there? Is it there? Is it there? You know what I mean? So that's where we need to kind of, you know, wrap our arms around it. And where did they store it? You know, where
What's the temperature?
In the temperature, yeah, you're talking about the temperature as a state. So the magic is this superposition, entanglement.
Yes.
And how do we get this visualized for people so that they can see the magic of quantum computing? They're able to solve a problem in this time through some is it the fact that these balls are all interacting with each
They're
other?
in the box and you don't know anything about them without opening the box and measuring.
Yeah, right.
Okay.
Right.
That's
so
good now, but so that we don't monopolize the exercise. I've been
Yeah.
teaching college for
Yeah,
20
yeah.
years.
That's
You know,
great. Thank you.
I'll play
That's
my favorite game. How about you? Yeah. 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 Let's do it. So what's that decoherence business about again? Yeah.
So when the quantum state of bits is destroyed by interactions with the environment, building up what he was saying.
And if you have a box full of metallic balls all at different temperatures, they're going to interact with each other and thermalize and eventually all reach the same temperature, at which point you've lost all the information. And so that's similar to the decoherence you get.
Okay. Now, you know, just to play the game. So, you know, let's imagine that I have a problem. You know, I want to add up, you know, 2 with 2. How would I do that using this decoherence business?
Decoherence is what you're trying to avoid. It ruins all the
Oh, okay.
Yeah.
Okay.
You want to keep coherence. Right.
So trying again. So where's 2 and where's 2 and how do I add them up? You see, this is what ordinary people worry about. This is what they worry about. There again, station A. I feel that we're still traveling C to D, right? You understand each other, what's going on. I know that. I kind of understand some things you say. I have a PhD after all. But I'm still probably halfway up the road, right?
I think this is pretty much about assignment problem. Like you assign something, some meaning, right? Like what's the temperature in this case? It's basically the number. Temperature equal this is 1, temperature is equal this is 2.
Okay.
And you let the two balls with temperature equal 1 into the box, let them interact, and then you measure the temperature of the balls after they interact. And you will know if the assignment is basically this, we agree scientifically or society agrees that what is 1, what is number basically, what are these quantities? Those are something that we agreed on, right? When we take 2 things, it's 2. So we agree first, what are these measures, right? What's the 2? What's the number 2? Then we assign this something. Right? The temperature, this is equal 1. The temperature is this is equal 2. Absence of something is 0. Presence of something is 1. That's the qubit. And you let them interact. And then if it happens to be after interaction that you find 2 of this quantity, then you did the summation operation. You got from 2 ones, you got 2 in one of them. So that's how you can think.
You know, and here is where you need to the time dimension and all that. Okay, good. This is very good. Anyone else? Yeah.
All right.
Yeah,
I want to riff off of what was just said. I mean, let's play with this idea of balls in a box. What if the balls in a box were squishy, or squishy, or maybe not squishy, but like they can rub against each other and mix with each other. Think like chalk, and they rub against each other. So you mix them up, and when they come out, there's going to be different colors on every ball, as if they were entangled, so to speak.
Yeah. Okay. Yeah. That's what stores the information, basically.
Right. So I mean, I think what was confusing about this particular metaphor, it seems like what was miscommunicating was what is difference between this and a qubit? Like this seems like bits moving around.
Yeah.
But you need some way to reference that there's some property of entanglement or interference. Like one thing the kaleidoscope does really well is that it's literally interference, right? It's like but I think that actually confounds classical information theory and quantum information theory, right? Like it doesn't actually capture what's special about quantum information.
Yeah, about the excitement.
That's the hard part, yeah.
But let's get, I don't know. Any ideas there? You guys have any ideas, any metaphors? No, you two.
Oh,
ladies
Sam's
there.
got an idea.
I'm looking at you. Or, no? Not even a smidgen of a metaphor? No one around you ever asked you a question, the question about quantum computing? No? Let me see. Anyone else?
Sam's up here.
Yeah. Yes, sir.
Okay, so I think actually one of the big problems with all kind of analogies or metaphors is that we try to explain it using classical physics, which this is not a classical phenomenon. So I think a better way to do it is you actually want to get people to get out of the mindset of classical physics. And so the easiest way to do that is you started off as saying it's a kind of a fairy tale, right? Let's imagine this object, like that bottle on that table, the red bottle, right? And it turns out that when you close your eyes, that it's a magical object. And what it does is it tends to expand out into space. And it is the same object, but it just sort of blows up like a balloon and it just keeps expanding and expanding. And then as soon as you open your eyes, the bottle will appear somewhere inside of that gigantic version of itself. Let's imagine that for a second. So imagine it's like a liquid which is slowly flowing over the entire room. And then as soon as you open your eyes, it will appear somewhere where it has spread out as a liquid into the room. So this is like this magical thing. It's a magical object. And then you can have two of them, right? So now as soon as you have two of them and they start to mix together, it's no longer just a red bottle or just a blue bottle. And as soon as you look at it, you can find the object somewhere or other, but it might have a mixed color. And this is called superposition. It's now no longer just one object. There are two objects that are mixed together. And so when you do quantum computing, basically what you're doing is you have let's say a series of pipes, Al Gore style. So you have a series of pipes, right? And what you're doing is you're saying, if this blob expands and it flows into the two pipes, and then you open your eyes, where does this magical object appear in the pipe? In the left pipe or the right pipe? And that's what a qubit is, basically. It's an object that whenever you don't observe it, it expands out into the two pipes. Now what you can do is you can have a valve. These are called gates. And you can literally pick which way it flows, into the left gate, into the right gate, but you can only control how much it goes in the left gate or how much it goes in the right gate. So sometimes, even though you turn the valve all the way, sometimes it will still appear in the other gate, even though most of it has flowed into that gate. But that's the magical part of quantum, is that that object, it literally goes into both gates at the same time. It's only when you open your eyes and you look that it magically appears in one of the pipes.
Yeah, I love this. I love this explanation. However, you are not taking advantage of something, which is that in my recipe, which is the violation of expectation. You're still trying to make peace with the audience and give them something by calling this magical. It's not magical. It is what it is, right? People don't know, they don't know that at the quantum level, things do expand, right? And they do appear somewhere else when you start observing them, right? You don't have to call them magical. Actually, what you have to tell them is like, what you thought it was magical, it ain't magical. And I'm violating your expectation that things can expand and appear somewhere suddenly. It might not do so in your immediate life, existence, but in quantum phenomena, they do, right? And that's where you grab them. See what I mean? If you tell them it's magic, You don't grab them. They go like, oh, I don't know. He's telling me a story. Is the fairy tale really? I mean, it's like, what kind of science is this? I know science is science and stories are stories. But another thing here, when you tell science stories, especially when you violate expectations, hold your ground. Don't try to make amends with the audience. You know, be the person that you are at that point, is the changer of the universe. You really are changing something in your universe. Yeah, assume it. It's yours. You're doing it, right? You just invented something new, right? Okay. Any other takers? Any other? Yes, sir.
By saying that if objects are large, we can clearly see them and define their position. For example, I can see Neil and where he's standing and how big he appears. But if I start making Neil smaller and smaller and smaller, then at some point I will not be able to define where his position is. And if he's too small at the level of a single electron, then I'll not be able to tell what his energy is, how fast he's moving, or what his position is. However, if I try to observe him, that's when I'll fix his position. And by making a metaphor like this, I think I'm still passing on the information while challenging the belief.
Well, we actually bring up another very important point. Actually explaining what and how quantum computers work doesn't make much sense if you allow people to still think that the universe works according to their naive balls attached to each other by strings, right? Idea, right? You really have to say, listen, the world, we have a conventional idea that the world is made of bodies that have mass, that are attracted by each other, and this and that, mechanical properties, all good stuff. You know, we put stuff on the moon with it and works perfectly okay. However, at another level of reality, things work in a very different way. And actually, you start the story of quantum computing by violating the first expectation, which is that there are things with mass, position, and deterministic properties, right? And then you bring it up from that level. Maybe this is not possible in a parlor, right? But actually, when you teach your first class, quantum computing, it's probably a good idea to start from quantum mechanics, right? Don't let people imagine stuff, give it to them straight from the very beginning.
I would have one comment on, first, if there are any other wonderful.
Yes.
Hi.
I'm a clinical psychologist, and I understood about 40% of this presentation. But hearing all of you talk made me think about moods and how people who have depression or anxiety, they wake up every morning and they don't know what kind of mood they're going to be in. And so every morning is this snapshot of time. And then you have infinite number of snapshots of time. And then somebody else next to you wakes up and they don't know what their mood is in. And then you guys have breakfast. And so who knows what you're going to be thinking and feeling after that.
Right.
And then you wake up the next morning.
Complex state, right? You have interactions, you have entanglement.
Yes.
Right. And you have a conversation. And through that conversation, things happen that wouldn't have happened if one of those was alone. So you have this idea. I wanted to get to one concept that I think is very important, and it's so challenging. And I have a provocative statement to make that may or may not be, hopefully is not true, is this. We have come up with analogies for quantum mechanics, functional metaphors for a computer, the operational things. Those are things that we can attack and we can describe, but they don't get at the transformational aspect of quantum computing. Why is it different than a classical computer? And you're getting at mood, which is a very interesting, complex human state, and how humans interact. We can I almost feel like we're getting at somewhere close to this sense of a complex problem solving. That's what I would challenge you all to think about, is how would you distinguish this? What is the transformational aspect of this that causes it to be able to solve problems that weren't solvable before? And I've seen a lot of, some papers, I've not read deeply on it. it's very hard to do. And this is my provocative statement that I hope I'm proved wrong in, is that it doesn't exist, that metaphor doesn't exist because that computer doesn't exist. It doesn't actually do it. And that's my zinger. Yes, please go.
Hi. So I think that's an important point that you brought up about the distinction between explaining quantum mechanics. Like, there's a lot of analogies for explaining measurement and, like, the physics part of things. But I think what should be emphasized when teaching quantum computing is the reason behind the speed up that you see when simulating things. So one analogy that I found that captures that really well, and I hope this disproves your point, is there's this website that there's a puzzle solving thing called brilliant.org, which
brilliant.org, I've heard
you can
of it,
solve
yeah.
like math puzzles on it in your free time. But they have a course on quantum computing, and I found this specific exercise in the first part of that very enlightening, because it's essentially, the setup is, if you've seen a Galton board, it's this setup where you have you throw balls down this. It's like a game machine, and it has like an even powers of 2 number of points. Like, let's say on the first row you have 1, then you have 2, 4.
Ding, 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 ding. Yeah, thanks. Yeah.
And then you pass a ball down it, and then it just like scatters off of these, and then it ends up at like different boxes where you collect these balls. And this is also something you could like give to students who have no experience with physics, and they can just like try it out and see where the balls go.
Right.
And there's a lot of classical reasoning for like figuring out where the balls are most likely to end up. For example, naively, you would think, most likely they end up in the middle because for symmetry. But the quantum computing aspect, and this I found through this brilliant.org thing, was if you look at the time taken for for a normal person, you could give this to them and ask them to really figure out the distribution of the balls at the bottom, like how many balls go where, like how likely a ball is to end up where. And they could do this by simulating all the possible paths and like summing them up, and then that would take a certain amount of time.
Yeah.
And then the point is, if you do this, and the key point here is interference between possible paths, which you cannot account for if you count them in this manner.
Right.
Whereas if you were to map this into a quantum mechanical problem, the analogy is if you have photons and you pass them, and each point on the board is a beam splitter.
Yeah.
So if this were actually done on a quantum machine, which would capture all these interference effects, then you would see proportionately much shorter amount of time being taken. So my point is, you could pose this as a problem to people and they could try to solve it, and they wouldn't be able to beat the time it would take for the quantum computer to solve this. And that's something that I think would stick in people's minds. If they're not able to beat this device, then they're like amazed at, oh, this is something actually revolutionary.
Great.
If I may add one more thing here. Any transformative metaphor should be good, should be effective, not only at explaining how something works, but also why something doesn't work as well as it should, or what its limitations are. For example, my toilet, a chained out toilets, right, metaphor, can explain how computers work, but it can also provide an explanation for why computers, as computers, are actually dumb, right? They cannot solve problems of meaning per se, unless you have very complex software built on top of them that basically need to get around the limitations of the computer as such. Because by the end of the day, a computer stores, the same ones and the same zeros. They have no qualitative meaning attached to them. Now, I'm only using this as an intro to this big question, and we don't have to answer it right now, but in your examples of quantum computing or quantum computers, can you use those same metaphors to explain why quantum computers are not yet, or cannot, or are limited in some sort of way, right? Those are the most effective metaphors that can not only tell you how it is, but why it isn't, or why it doesn't, or why it hasn't, right? And for quantum computing, this is very, very important, because we've had the first workable model, whatever you want to call it, by the 1990s, I'd say, right? And these commercial contraptions, they've been with us for about, 10, 15, 20 years now, right? And they are still trying to work out some of the limitations, right? Like error correction and, temperature, right?
Yeah.
Right? It's a major limitations, right? So you need to explain with your quantum metaphor, right? And with your transform metaphor, why, what we have right now only works in this way or doesn't work in that way and all that kind of stuff.
Interesting point. Yeah, that's a very good.
Interference and decoherence. In order to have interference, you need to preserve information.
Yeah.
There is a mechanism that loses your information before you read that information. Then your information will not work. Your interference will not.
Right.
So yeah, but again, in this example with the balls or all the other, or the blobs, that expand and all that. So what is the problem with that? How is that process that seems to work so wonderfully, right? Not actually quite ready yet for what we need to turn a principle into workable machine.
So with this ball example, when you have fixed temperature for the balls or some temperature for the balls and you let them interact, if the balls give some of this heat to the walls of the box where you are mixing these things together, then in the output you will not have the same information as you had in the input. So
there you go.
Lost some of the information. You cannot reconstruct the calculation you wanted to do. You had one you wanted to sum up, but in the output you got one because the other one was lost in the walls. Right?
Yeah, but again, the idea here is to be very careful with the metaphors. The metaphors need to do double duty: explain the excitement and account for difficulties.
So I can tell you what I use so far. This is my best so far. Is I have a lot of friends in California, so people are familiar with the idea of programming a machine. And a quantum computer is another kind of machine, and you're going to do some coding on it. And you see these like big objects, and you're wondering, is the machine really big? The most common question I get is like, how big is the quantum computer? And I think emphasizing that the quantum computer is actually small, what you're doing is you're controlling a molecule, and you're coding on a molecule. And this is like a bit misleading with the particular hardware, but I think it gets at the point of the quantum computer is small, and it offloads what's weird about quantum computing to what's weird about quantum mechanics. You're saying when things are really, really small, then we can control like molecules. We can program a molecule to be anything we want. And I think that also motivates a near-term application like variational quantum algorithms. And so I think emphasizing the fact that you are controlling and coding on a molecule, and that's a completely different thing than coding on a machine that you've seen before.
By the way, now that we are talking about molecules and all that kind of stuff, is the brain a quantum or a classical computer? Well, maybe just maybe it is done the quantum level. Maybe just maybe it's it's chemistry and subtle physics.
But there are studies that show that the migration of birds are kind of dictated by the little spins that they have in their heads.
Could be.
Right.
It could be.
Yeah,
and if we crack that nut, we can get to the ultimate explanation of what the quantum computer is. Maybe it's our brain. God knows. All right.
This has been wonderful. I know that at 7:30 there is a bus leaving though for a few people, so I do want to give people time to do that. Takes 30 seconds, but get there. Thank you so much again. Thank you. Also to you. This is great. Thank you so much. It was wonderful. I hope you enjoyed the way it was put together.
I know it was perfect. I enjoyed it very much.
I think we're a good team.
Yeah, there you go.
Did you need a